we start. I will start the recording right now. Let me start the recording. Okay, very good. So, perfect. Thank you, everybody, for being here. And today is the first day of the 4th edition of High-Performance Computing and Quantum Computing, CINECA and CNRI IFN event that we organize every year, and for the 4th year, this one. And today, I want to show you a little quickly my the agenda for today. Today, we will talk about, we will have 2 different sessions. This year, this event will be in 2 different days, today and tomorrow. And today we will see in the morning the part with the quantum hardware and software providers, all the news in the field of the realization of new quantum hardwares and new software strictly related to quantum computing. And we will resume in the afternoon after lunch with a very interesting session regarding the relationship between quantum computing and HPC in all Europe. So we will listen to a lot of European supercomputing centers that will explain us their relationship with quantum computing, their vision of the relationships between quantum computing and HPC. So let me leave the floor to our director, Sanzio Bassini, that will introduce our workshop. Thanks a lot, Sanzio, for being here, and the floor is yours.
Thank you very much, Daniele. I'm Sanzio Bassini. I'm the director of the High Performance Computing Department, that by definition says natural and physiological development process would include also the actions related to the quantum computing. I would like to thank very much Professor Apolloni and Professor Di Falco, together with Professor Prati, that would collaborate since a while with the preparation of this annual appointment. As Daniele said, this is the 3rd year that the event took place. The last 2, unfortunately, in video conference, in digital, and not in presence. We had hope since the very last minute to be able to organize the meeting in presence. That is not yet the time. That is, pushing us for working as much as possible, and the science would be the only real answers for facing the pandemic, that it would showing possible new waves of pandemic, which is a concern for all of us. I would like to thank Daniele and to Riccardo that it would organizing a very nice meeting, very dense. I would not taking too much time, but I would like to just remind, or maybe share with all of you that in principle there will be a lot of potentiality with respect of further development processing. You are maybe all aware about the fact that the high performance computing simulations and quantum computing also will be part of the national centers that will be funded in the context of our plan for resiliencies, the national plan for resiliencies, funded by the Next Generation EU funds. That for us, it's a very important opportunity. We're talking about the investment, where the development process related to the sharing of experience in the cost of quantum computing will be one of the pillars of that such national plan. We're talking a very huge investment, and we're talking also about a very strong opportunity in terms of involving the scientific community, and also supporting the inclusions of hundreds of researchers, that it would represent the real asset, apart the development process related to the infrastructures, which would be one of the pillar of the plan. We are continuing to working in the context of prestigiating the technology, but more important in familiarizing with the development process of quantum computing, mostly addressing what would be the development process for use cases and for the methodology that it would combine digital computation with the quantum computations. Indeed, the point related to the integrations of the two technologies will be one of the actions of the next coming years already, that it's in the strategic agenda of the EuroSPC, which is also one of our main drivers for sharing what will be the experience and the further opportunity. So that's for spending a few words for sharing with all of you a sort of scenarios related to what would be the next year's actions. We will continue to address the topics from this point of view, and I would like to conclude these introductions, very brief introductions. We are hiring a new component of our staff to increase the number of people that are be working for high-level support in the domain of quantum computing, for supporting the national and European community for addressing what could be the long way towards the exploitations of these very important technologies. Of course, there will be more and more staffing, and that it's, I think, one of the main point with respect of what could be the vision. So combining the development process of the infrastructures with the inclusions and increasing of the high-level support, that will be, I think, one of the main tasks for CINECA. Thank you very much again for these days. It will be a couple of very dense days. The agenda is really very important, I want to say. I would wishing you a profitable meeting, and I'm enjoying the listening and the sharing the experience that you would put on the table with respect of this important domain. Thank you very much, Daniele. Thank you very much, Riccardo. Thanks you all. Professor Apolloni, very nice that you would open the sessions, and thank you very much to Professor De Falco also, that it would sharing the introduction, just to contextualizing the meeting. I would remain in the back, and I would maybe sharing some opportunity for interactions. Thank you very much.
Thank you, Sanzio. Okay, so now I will leave the floor to the other organizer, Enrico Prati, that I thank for being here. And Enrico, the floor is yours. Thank you.
Hello, everybody. Good morning. Can you hear me?
Yes, we can.
Okay, so I'm sorry for the last minute issue. It looks that my camera is not working this morning, but okay, it doesn't matter. I'm very honored for hosting today the two inventors of quantum annealing. So I think it was a perfect match today for opening our session to have some historical perspective of what happened at those days, let's say about 30, 40 years ago, when the idea came out. So let me just introduce this short session, which is a kind of different, which consists of interview of the two inventors, asking them some historical remarks. I think this is very useful for young people and students who just to create some connection with what has happened in the past, and to better understand what is happening today with the invention of hardware of quantum computers. So welcome to the two professors. I think I would like to ask to both of you, basically, who was working to the concept of quantum computing in the 80s, and how was the world at that time, the research world?
Okay, thank you. I did expect your question. So I went to a fast Google search about the 80s and review search on user modern physics 2018. 80s, I find the following names. Benioff, 1980-1982, quantum Turing machine. Deutsch, 1989, essentially universally of the quantum circuit model. Feynman, 1980. If I go to Abash Leader Review, I found 3 other papers. I cannot say who are the authors of these 3 papers, but Bruno, I think, is showing the reference there. So essentially, in 1988, Bruno and I knew the papers by Feynman, 82, 86. Did not understand the papers by Benioff and Deutsch because there was too much matrix algebra there, and we were not conversant with that. But Feynman paper was 82 paper, was fantastic. It opened a whole quite new horizon. It was just a matter of order of magnitude argument. N quantum spins are able to solve a 2 to the n dimensional problem. Essentially, the solution of their equations of motion. Everyone who has tried to implement n spins as matrices on a classical computer finds that it ends working with 2 to the n dimensional matrices, and its computer very easily blows up. But Feynman said, well, you need not simulating the evolution of quantum spin system. You just let them run, and they will solve their equations of motion. This was the main input for our research. Then there was another paper by Feynman in 1986. In fact, the paper appeared in 1985, and I stole that from the Salerno library in 1985, which was too hard for us at that moment. It was not just an order of magnitude argument, but it was a strictly technical proposal of a machine working with elementary components on its own, including the clocking mechanism. And in 1986, we are not able to answer to the main questions that Feynman posed. Will the clocking apparatus ever reach the end of the program? How long it will take? How do you manage such strange things as subroutine being in a superpositional state or being activated or not being activated? Everything was, how can your computation fill the possibility of taking another route in spite of the fact of that route not being necessary for that computation? It was too hard for us to understand. And in fact, mostly we went to that subject, the 86 paper by Feynman, just after our experience on quantum computing. We tried to understand the 82 papers by Feynman, and our main idea in our first paper was the talk to the Vieti school, was based on the following idea. The ground state is a perfect tool for searching for absolute minima of Boolean functions for 2 reasons. One that is obvious, it is an extended object. One which is, for a computer scientist, less obvious, because in the ground state there is motion. It's not sitting there in the minimum. It has 0-point oscillations, which mean that it can jump, it can tunnel between relative minimum. this was a dream for a computer scientist, says Bruno. This is what we implemented in the stochastic process application paper, in which we were working about the quantum tunneling, and we did that by an unconventional approach, not the well-known Schrödinger approach to quantum mechanics, but via a non-standard approach, the stochastic mechanics approach by Edward Nelson, in which you can talk about trajectory and even picture that in your simulation. So in 88, the situation for us was explosive because of Feynman 1982 papers, and we were well aware that it would take. We had to be fast because the competition was coming on. So your question, how was the world at the time? My answer is very nice, thank you. We were young, with a lot of ideas and a lot of freedom to exploit those ideas. Maybe Bruno can be more explicit about this issue. Bruno, that's your turn.
Yes, just to add some general remark on this point. Let's say that 80 was a sort of cultural revolution like 68 was for the young generations. Essentially, we moved from a symbolic infrastructure framing the scientific tool, scientific thought, were based on two-value logic and embedded programming. In essence, give me a well-formalized goal, give me axioms as environment conditions, and I feature for you the solution to a sub-symbolic environment where the starting point were data, and then I observe them. I look for a local compatible model, and I provide solutions accordingly. Just to remark to quote some points or some facts of that time, probability statistics start pervading the issues, both management and scientific issues in that time, starting to appear in the programs, courses of both in computer science and in other fields. Then NP completeness issue, in the sense that computer science took by hand the limit of their capability of solving problems in a symbolic way because of the curves of the exponential growth of the time to solution. And so that was the time for the revival of neural networks. They was buried in the previous decades because not so general. They revived both because they was proven as a universal computing machine, but mainly because they was the template of a sub-symbolic approach to solution, giving place to the typical attitude of the human. It means experience, intuition, learning. The general idea is no matter why, provided it works. And so it states a new alliance between theory and practice. And simultaneous annealing was the template of the stochastic approach to optimization, where the optimization in turn was the clue of any sub-symbolic solution to problems. And as it is, it represented an alliance between physics and computer science. You feature a proper process, you fire it and wait for an equilibrium distribution that suggests the best solution to the problem. The only drawback was that you should wait. We don't know how long time to get the solution. Here, quantum physics appears as a dream, as a magic wand that, with the necessary caveats, should promise, not at time ensure anything but promise, the possibility of solving in one shot the path to the equilibrium of a stochastic process. At that time, we was not in presence of a quantum machine. That our problem was to simulate it in a conventional machine, getting results that proved to be suitable, having the tunnel effect as the atout of this quantum annealing approach.
Yeah, it's really fascinating to us. Also to hear that the discovery of the first ideas came at the same time where neural networks came out. It's an amazing connection, something deep. Okay. Let me ask another question. At that time, I think it was really difficult to understand which direction looked more promising. So you had some multiple choices. So some of them, maybe they failed, some did prove effective later. And also your idea proved effective. So how did you get the idea, and what happened?
In some sense, I already answered this question, and I told you that in 1988, I did not understand Feynman's paper in 1986. It took me time until 2013 to understand something about Feynman's paper. So that for me was the necessary evolution of my curiosity about quantum computing. Maybe we can speak about that another time. But at that point, in 1988, I had a personal tragedy. I was able to convince people of what Bruno says, that probability and statistics are central not only for mathematics and physics, but also for technology. I convinced the Italian Academy of this point and was punished. I got a chair in probability at Polytechnic School, which meant increase of salary, which was important, but meant also 950 students per year. So immediately after quantum annealing, my attention was drawn to teaching. I had to teach quite a lot for 3 years, but with the feeling that I had to teach not probability, but quantum probability. When I went back to the Nominé, which means the Institute of Computer Science at the University of Milano, I kept this idea. My students, Dario Tomaselli might be in the room, my students had to learn quantum probability to start with, understand Kolmogorian probability as a particular case of a more general theory of states on an algebra. Expectation is a concept prior to probability, which I did in my last days of teaching in Milano, which means I was drawn by quantum annealing to the idea that I had to teach quantum probability not to mathematicians or physicists, but to computer scientists, which was the subject of some experience in computer-aided teaching. Then I had to go back to the work of Feynman, and it's a fascinating machine. The clock is just a single spin excitation traveling as a spin wave along a line with some local deviations. Very elementary. No battery needed. The clock just works because it is on half a line, and being at the leftmost point of the half line, there is some kinetic effect, but by which it must expand to the right, following the program lines. By itself, which of course asks a question, will it reach the end? The answer is, it may be, it might reach the end without any battery. How long? Well, that's quite another question. But you can try this with many copies of the system and overcome this problem. But it is a very slow procedure. So Feynman himself had an idea which was clear, obvious. Plug in a battery to this quantum walk and let it push on the right. But every physicist in solid state and conceptual variable coming from that environment knows that if you put on a lattice a particle in a constant field, it moves a little bit away from the origin and then starts oscillating by block oscillations. So Feynman's idea, which looks very fantastic, you just plug in a battery or position-dependent magnetic field that it goes faster, did not work. Because essentially, if on a lattice, current does not flow unless you have some dissipation. And then back you are to the problem that this very fragile system can suffer from friction, dissipation, and so on. In this respect, we were able to, as far as computation was needed, as far as simulation was concerned, bypass the problem of Monte Carlo simulation approximation of the ground state by Costin equation, too long to speak here, and by the Imler equation, too long to hear. But we were able to implement that and answer a question that a referee had asked already in 1988. How can you do without the complicated algorithm for simulating via Monte Carlo simulation the ground state? That's all.
Yeah, that's very interesting. Let me, so unfortunately, time is running very fast. We are going to start the first final remark by Professor Apolloni. So did you, just a yes or no answer, did you expect that the idea you have worked at that time will become something real in the hardware today?
That is your matter, sir, because you are working now in real quantum computers. I expect, but actually with the same let's say approach of supercomputers, in the sense that initially it was intended as the universal solution to problems. Then they work on a special application field where vectorizing the computation, etc., was possible and suitable. The same expect with quantum computing, where we can be able to solve special classes of problems, nothing to do with the idea of having a mini quantum computer on our table.
Yeah, thank you so much. Thank you, both of you. It was really amazing time spent today with you to launch our event. We are so grateful that you accepted our invitation, and you also gave the perfect starting point for the next session and the next speaker, who is exactly going to talk about adiabatic quantum computing and quantum annealing. So let me leave the floor to the chairman of the next session, which is Riccardo Mengoni, and let's start with event with the first session of today. Thank you so much, professors. Thank you so much.
Thank you for you for your invitation. Bye.
Thank you.
Thank you. Thank you, Enrico. Thank you, Professor Apolloni and Falco, for this historical contribution. Very inspiring. So, let's start with the first session, which is about quantum hardware and software providers. Okay, here we have with us Andy. So we're going to start with D-Wave. Andy is sales director of D-Wave system, and he's going to talk about D-Wave advantage performance updates. So hi, Andy. Welcome to the workshop, to HPC QC workshop. And it's a pleasure to have you here also this year. So I think you can start sharing.
Perfect. Thanks, Riccardo. Let me see if I can get some slides working. Okay.
Yep.
And I want to do a particular window, and I want to.
In the meantime, let me just tell the audience a quick thing. So there's going to be in the chat a file where you can leave your name and surname for those that are interested in having a certificate of attendance for this workshop. Okay, so people that are registered. Okay, so sorry, Andy, so you can
okay.
Go ahead.
Can you see my screen there?
Yes, yes.
Riccardo, perfect, good, super. Well, thanks very much indeed for inviting me. I'm very pleased to attend and be able to participate in this. Must be the fourth HPC quantum computing conference that you're running. So very big thanks to Daniele, Riccardo, and Enrico for organizing this. I must admit, I wasn't expecting such a rousing session from the professors Apolloni and Falco before starting this, particularly since it was such a lead-in to a quantum annealing type approach. And it would have been fantastic if they, back in the 1980s, could actually have looked forward to today, where I'm actually going to talk about quantum annealing and actually hardware that can run quantum annealing problems. So that was very humbling, and I hope I can do them justice in the next 30 minutes with this presentation. So last year, when I was talking to everybody, we had just launched the D-Wave Advantage system, our new quantum processor unit with 5,000 qubits, and as our history shows, then shortly after launching a particular QPU, we then provide an update in terms of performance capabilities. And that's really the subject of today's conversation. I'm going to, for those people who are not that familiar with D-Wave, I'm going to start off just by giving a few introductions into what exactly the D-Wave system is, and then discuss what changes we've made. And there are a number of things we've done, both with the hardware and the software, which I will be talking about. And then obviously allow questions for anybody who has them towards the end. So no introduction of D-Wave is complete without letting everybody know that D-Wave is a full stack quantum computing company. We provide the hardware, we provide the software, and we provide services to go along with that to help our customers in developing the applications that they might be interested in. So we can do everything from start to finish, and the part of this you'll see is part of our cloud offering to provide those services out to our users. And I'm sure that a lot of you are using what we call the Leap developer accounts, whereby you can actually sign up for a free minute per month to gain advantage of the D-Wave services. I always go the wrong way. So this is kind of like our updated roadmap. Last year, it looked relatively similar. There were a couple of additions that I will point out today. But effectively, you can see that we've progressed and increased the number of qubits if we measure the hardware. And down at the bottom of this slope, if you can see my arrow, we joined in this particular progression with our 2000 Q system with 2000 qubits. Prior to that, all of this history was not lost. And this is the part that got us from the ground starting point through 8, 16, 32, 128 qubits to the point that we had 2000 qubits. We were then looking at speed ups, sort of theoretical speed ups on basically classical heuristics that were benchmark problems, nothing particularly real world orientated. So it was fantastic when we were able to show that on certain physics problems, we were able to provide speed ups, and these were actually reported in Nature and Science magazines. Moving along this particular path, we introduced the 2000 Q low noise system. This system is still available. It has a slightly different fabrication to the Advantage system, and uses the original Chimera topology of having unit cells with 8 qubits in each unit cell. At this point, we were then able to demonstrate that we were actually using the D-Wave system on real applications. And then last year, we obviously introduced the Advantage system, as I described back in December 2020. And at the same time, almost overlapping, was the introduction of our cloud service and our hybrid solver services. I'll mention some of these again later in the presentation. But you can see here, this is where we are. And looking forward, the addition to this particular slide is the idea that we're now discussing what we're going to do in the next Advantage systems, Advantage Performance, that I'm going to talk about today, as well as Advantage 2 and Advantage 3. And for those who didn't perhaps attend our Qubits conference back in October, or have not been watching the news, one of probably the most exciting things for for everybody is the fact that we announced that we have started gate model quantum computing developments, and we now have a roadmap known as the Clarity roadmap that you can refer to on our website, that talks about how we are going to integrate gate model systems into our portfolio of quantum computing offerings. So we will be continuing with quantum annealing, as well as developing a quantum a gate model environment and architecture. And the goal is to have an overarching software suite within our tool set that enables us to look at a problem and decide which is the best architecture to run that problem on, or maybe parts of the problem, as you'll see with our hybrid solver services later on in the presentation. So from the hardware perspective, then these are some of the actual parameters, the features of our particular systems. So today we have 5,000 qubits. That's an increase from our 2,000 qubit system. And linking all of those qubits together, we have 35,000 couplers. This means that the degree, as we call it, which is the connectivity, has increased from 6 to 15 in the new Pegasus architecture of the D-Wave Advantage system. This means that each qubit is connected to 15 other qubits. So obviously the performance and the size of problems that we can address has increased from the 2000 Q system through to this Advantage. If we then look at sort of like a measurement in terms of how we look at classical computers, with classical computers, we're always talking about, or not always, but one measure of their size is how many transistors there are, or how the technology is advanced, is how many transistors there are in a particular surface area. Similar sort of thing for superconducting circuit fabrications, and this is looking at Josephson junctions. These are what effectively create our quantum effects and create the qubits. So here we're talking now in our advantage systems of over 1 million Josephson junctions within our quantum processor unit. That's the hardware. As I said, within the lifetime of any D-Wave system, then we introduce both hardware and software improvements and additions as we go along in their lifetime. The one that we introduced at our qubits meeting in October is called the Advantage Performance Update. And effectively, we have increased and improved our fabrication process in a variety of different ways. One of which enables us to account for more qubits. So if you do the maths and work out how many qubits there would be in our Pegasus architecture, then it's in the range of over 5,500. Some of these, when we actually calibrate the systems, we are unable to address. Each qubit needs to be identical, of course. So some of these we can't calibrate to be identical. So we then write them out of the graph. This means that we have to reduce the total number of qubits below the actual physical number. And so hence the name 5,000 rather than a higher number. In our manufacturing process that we've improved to produce the Advantage Performance Update, these new QPUs are actually higher quality in their fabrication, which means we can address more qubits. And by being able to do that, we're then able to look at larger problem sizes because obviously we have more qubits to address those problems. There's also within that hardware, we have enabled a lower energy technology so that we're not actually using so much energy within the problems, and we have more precision by looking at lower energy bounds within the solutions and the way we do the annealing. This higher quality answers faster part here it is an interesting fact. We obviously looked at these not all equal 3 SAT problems, and we actually ran those against certain heuristic samplers and looked at how they were getting on with regards to advantage, as well as our 2000Q systems. And within the majority of cases, then the Advantage Performance Update was actually producing better, higher quality solutions than the other systems. Similarly, looking at 3D lattice problems, the same sort of thing was occurring, and we were getting two times faster solutions from the Advantage system. This system, for those of you who are using Leap, will find that this system is available in the cloud. It's been available since October, and I've often talked about the idea that a D-Wave system is being installed in the Jülich Supercomputer Center, and that is now fully installed, and we're going to be announcing that it will be available to everybody in January. So for that system, it already has one of these Advantage Performance chips or QPUs, has it installed. And so the minute we start in January, everybody will be able to access a European D-Wave node that is in Germany. So really looking forward to that being the case. So I mentioned the idea that we're going to be starting to look at gate model systems and develop that technology to supplement our annealing technology. So we often get asked this question: will the gate model development be replacing the quantum annealing and the D-Wave Advantage systems that are obviously a different technology? And if we see here, this is really giving you the our view on what the future holds in terms of what sort of solutions, what sort of hardware is required for problems that are being faced by people in the real world. And this particular outlook shows that obviously it's easier to see the colors up here in the long term because the numbers are bigger. So if the dark blue is annealing, the turquoise color is problems that can be solved by both annealing and gate model, and the orange represents the sort of problems, the chemistry problems that only can be material science type things that can be addressed by best addressed by gate model systems. So if we look down here, then this is kind of today's analysis. And we can see that the actual division, the split, the quantity of these sort of areas doesn't really change much as we move forward. So there is still a space, primarily in optimization problems, combinatorial optimization problems, that will be best addressed by annealing solutions. So we will continue this annealing line at the same time as developing the gate model environment. And obviously a primary motivation to doing that is the fact that that means we will be able to address all of this marketplace here rather than just a third of it as it looks in the long term. So our future is certainly still going to be fueled by annealing technologies, and we will obviously use the experience that we've had in developing quantum annealing systems in developing gate model systems as well, and look at how to get the best out of both systems to provide the best hybrid environment, including classical systems. So effectively, just to highlight the idea of how powerful optimization problems are and how powerful annealing is within this particular environment. So obviously there's some marketing sentences here, but effectively the important part of what I'm describing is on the right here, where I'm noting a couple of evaluations and problems that have been looked at by a variety of people, and we can see the fact that today the quantum annealing solution is actually providing much better statistics, much better performance than its gate model equivalent, whether that's QAOA or actual gate model itself. So whichever one we look at here, there are VW are being able to have solutions with a much larger number of cars involved in their paint shop scheduling. Jülich themselves have determined that the D-Wave system outperforms current gate QAOA. And this is a Los Alamos National Lab evaluation, which compares 15 seconds with the 30 hours. So some really good proof points about how well quantum annealing is performing compared with gate model solutions today on optimization problems. So that kind of wraps up the idea that D-Wave is producing the hardware in the Advantage system, and we've joined that together with the Leap cloud. So being able to make improvements on both sides of this this particular slide in the hardware areas, which I've just described, and we're also making updates and changes within the software environment from our Leap cloud service. We've talked about our hybrid solvers as a quick recap. Then prior to our latest announcement, we had two different quadratic model solvers, a binary one, which could address up to 1 million variables, and a discrete, a DQM solver, which can address a similar number of variables. And the premise here is the fact that a business application will have a flow, a hybrid environment itself, which might include areas. Unknown call. include areas that should have had that phone off. Include areas where we're going to be talking about classical environment, and this part here highlighted in the middle is where we're going to look at how that could be best applied to technologies that can address harder problems. And so we're within our hybrid environment, we're running this in parallel on classical optimization solvers and on D-Wave quantum ones, and effectively producing a solution which is a hybrid combination of these, which is of a higher quality and higher speed, higher value solutions to the customer's solution. So though neither of those two address constraint type problems, and so with the launch of the D-Wave Advantage performance update, we also produced, or we've launched a new hybrid solver, the Constrained Quadratic Model, CQM, that effectively it makes it easier to address constraint-orientated problems, as well as being able to overcome some of the problems that are normally associated with these types of problems. So we now have 3 hybrid solvers, DQM, BQM, and this CQM. And the whole process of using them is greatly simplified. A user effectively inputs the constraints of the problem into their Python program, and effectively it addresses some of the problems that we can't normally overcome very easily in these types of problems. So with the CQM, we're able to address integer variables, which we haven't been able to do so far. We're able to look at linear and quadratic terms, and within the CQM, we can address up to 1,000 constraints. And again, one of the important parts here is the fact that instead of looking at penalty functions for our constraints, we can actually input inequality and equality constraints as normal parameters, which then don't affect our solution in the same way that they might otherwise be affected. So a very much cleaner and easier solution. And if we look at using the CQM, then the CQM is in the turquoise color on the right. This is compared to the other solvers. And this is when we're looking at a Cubo problem. And this is showing how the performance can be changed. So obviously, in this sense, for Cubos, the BQM is performing slightly better, but not much than the CQM. But in constrained models, then we see how powerful the CQM is in being able to provide higher quality solutions than the other two solvers. So depending upon your solver, then it really depends which is the best choice. And evidently, for constrained quadratic models, this is the best solution. All of these solvers are available on the Leap platform, and they will all be available on the Jülich system when that comes into operation. Lastly, looking at the actual performance of these systems, then I think I've probably showed this slide before, but effectively this is the sort of how we're looking at problems in a non-quantum system, and then when we actually address them using the hybrid solver service, we get much better performance in a lot of the benchmark tests that we've done. Fabulous. And with that, I will end my presentation and ask if there are any questions that need addressing.
Thank you, Andy, for your presentation, for all the amazing updates from the D-Wave side. I think that participant, let me recall that participant can either raise their hands or write questions in the chat. So let's wait. So don't be shy and just raise.
It's early in the day, so we've got to get everybody's enthusiasm's going. I think over the years, I've for one reason or another, been one of the first presenters every time. And normally I have in early years, there's been a sea of faces who are all, you can tell that they really want to ask a question, but are worried they might be the first. So don't be shy.
Let me see if some of the participants. Okay, otherwise, okay, let me ask a quick question. So, more technical question. So, how is it hard to build a device that is natively a DQM? So, it solves natively something that is discrete instead of binary. So, is it much harder, or do you know something in this regard?
So I don't know whether Victoria is available to answer that question, because she would give a much better answer. From my simplistic view, then I see it in terms of the binary. The BQM is very much the sort of the native version. That's what the machine was designed to address. And so it's kind of like a software layer on top of that to actually be able to cope with the discrete variables. But maybe that's too simplistic. Victoria, are you around?
Okay, let's see if Victoria is here, and if yes, we can. Yeah.
Hi, I am here. Yes. Sorry, can you just repeat what the question was again?
So the question was basically, so is it really hard to build a device that is natively discrete solver, so not binary, not qubits, but like qubits with d possible levels?
Yeah, so in our hybrid solvers, we have different ways of handling the different types of variables. But yeah, basically what Andy said is correct. You know, for the hybrid solvers, there's always some component of your problem that will run on the quantum computer, and that's natively binary. So when you have these other variable types, there has to be some way of either converting them or handling them so that when you run these portions of your problem on the quantum computer, it has to get converted somehow into that binary form.
Okay, thank you. I see also one question in the chat, so which says, what could be the reason for the difference in performances for certain application on D-Wave versus gate model quantum computation?
So that's a very good question. I would suggest that there are two reasons really why the performance there are the differences in performance. One is scalability. So we can obviously with our systems, whether it's with the native 5,000 qubits or the actual hybrid solvers, we can address larger problem sizes than can be addressed on today's gate model systems. So that gives us an advantage, because you might have to run the gate model systems multiple times to get the answer, or do some other non-natural way of getting the solution. The other aspect is the fact that these are optimization problems. And so the way that the D-Wave has been designed to actually address optimization problems means that in the same way that gate model have particular sweet spots or areas where they will outperform other technologies, optimization is D-Wave's sweet spot. And that's why we can give the better solutions. Added to that, of course, is the fact there's a third one. It's a Monty Python sketch. I have two answers. No, I have three. So the third one is the fact that, of course, we are less susceptible to the noisy environments that are with quantum computing today, and are a major hurdle that gate model systems that need to get over.
Okay, thank you so much, Andy. Thank you for answering the question.
Perfect.
I think so. It was a pleasure to have you here, you and also Victoria. So thank you again, and let's go to the second speaker of the day. Maybe there are more questions, and Andy or Victoria you can answer in the chat if you like. And the second speaker is going to be Sebastian. Are you here, Sebastian? Okay, I cannot see Sebastian in the cannot see Sebastian. Maybe your name. Oh, okay, yes, I'm online. Okay. Just wait a second, and we can enable you as a. Okay. We couldn't find you, Sebastian, because to us your name was unknown user. So, but now, okay. Okay, now I think you can.
Hello.
Okay. Hi, Sebastian.
Great.
So, just a brief introduction. So, Sebastian Grijalva is from Pasqal. He's a quantum software engineer at Pasqal. And today he's going to talk about their quantum device, the quantum processor. This is a neutral atom quantum processor. He's going to explain us how to program their device and something about applications and the emulation of this device. This is an important thing to take in mind. So please, Sebastian, go ahead.
Thank you, Riccardo, and to the organizers at UNICA for this nice workshop. This morning, I would like to speak a bit about what we do at Pasqal and to discuss some of the updates we have on the applications and emulation side. As you know, Pasqal is a startup. We are a 2-year-old startup that is building neutral atom quantum processors. So these experiments began at the Institut d'Optique at Palaiseau, France, and it was originally an experimental laboratory by Antoine Bourreis and Thierry Laïc, which was dedicated to controlling atomic matter and with the expectation that to eventually move into information processing. Eventually, there was a spin-out, which is Pasqal, and who is now trying to build the processors. As you see here, this is one of the actual prototypes now, which are based on neutral atoms. So the qubits themselves are these atoms, for example, rubidium, which are trapped in optical tweezers. So as you can see here, you have several atomic traps, and each one of these green dots represents an atom, which is guided to move between two electronic levels. It's a Rydberg atom. So this is a particularly scalable technology. You can have hundreds of these atoms in these traps in arbitrary 2D or 3D geometries, as you can see in the picture. As I said, the electronic states of these atoms, the electron, is storing the quantum information. So this can be seen as a qubit. The interactions then happen because of the dipole-dipole force that exists between these Rydberg atoms. So there is a large connectivity inherent in these types of systems. Now, these neutral atoms, besides their potential for many body quantum physics, they are one of the most useful quantum simulators, which means that they can be used to extract information from a quantum system with another quantum system. But besides that, many body quantum physics applications, they can also they hold the promise to be useful for chemistry and then for drug discovery and also for high energy physics. This has been used in several experimental research papers. But it can be also used in hard computational problems. For example, in this case, you see a set of maximal independent sets. So imagine that if the atoms that I showed in the previous picture were either in its excited or ground state, and if this corresponded to a red or white dot, then some of these points would correspond to subsets of a graph that are not connected by a link. So these types of problems are natural for the system that is described by the neutral atoms. They can be used, for example, for approximate optimization, and also for quantum enhanced machine learning. If you try, for example, to characterize the different graphs that are formed with these atoms. Now, from the point of view of numerical simulation in Pascal, we are beginning to attack several interesting issues that arise in the developing of these applications. We can discuss two main features: the few atom emulation, which is based on fundamental testing, studying noise effects, and the design of digital quantum gates. I will precise later how exactly these are built. And then there's also the large atom arrays, in which we are interested in understanding the behavior of quantum algorithms for large arrays, as I said, for graph or combinatorial purposes. And finally, there's the need for quantum-inspired solutions, so optimal control, measurement estimation, and tensor network simulations. So with respect to few atom emulation, I will go into a bit of detail. These transitions, as I said, between a ground and excited or Rydberg state are actually a more complicated two-photon process. So this is it's guided by two lasers, each one driving the atom from an initial state to an intermediate state and then to the desired state, the Rydberg level, and which is subject to imperfections. For example, state preparation and measurement errors. You can have a spontaneous emission from this intermediate level. As you see, there's here another so-called garbage state. You can have Doppler effects induced by the finite temperature of the atoms and the way that the lasers act on during the transition. And of course, you have the imperfections in the laser noise. So one of the goals of the emulation team in Pascal is precisely to have a model of these types of interactions. These effects, these noise effects, can be, for example, witnessed when doing a pulse sequence. As, for example, the simplest one would be to find the Rabi oscillations between these two levels, 0 and 1, and then we extract a model of the noise. There are several techniques for doing, which come from first principles to try to add all of these effects into a big model. There could also be a machine learning model that is learning how these different errors appear. And then whatever the model is, you use this for design and testing of new features. So this, for example, is in red is the results of a model, and then the line is the results of the model, and the dots represent experimental data. Now, the noisy emulation is used to verify and plan the behavior of the pulse sequences that we constitute, for example, quantum algorithms. Here, for example, you see real experimental results in blue from a particular pulse sequence that is a part of an algorithm, and then you have to match it up with the noisy results. So in Pascal, we have developed this first noise model, and now we are collaborating, for example, with ICHEC in order to find different types of approaches to finding these errors, which are expressed as, for example, in the case of spam errors, these are probabilities of having, one of the spins, or in this case, the qubits, flipped to 1 instead of a 0, or a 0 instead of a 1. These are probabilities. And you also have a standard deviation on the laser properties. This can be also used in the case of digital quantum gates. So just to explain a bit the principle behind digital gates in neutral atom devices, the first step is to put your atoms into two hyperfine states. So these are states which are not Rydberg or very excited states. These are just close to the lower energy level states of the atom. You pick two of them and you call them ground and ground 0 and ground 1, if you wish. So this will be your digital basis. And then you use the Rydberg level, this highly excited energy level, as a way of introducing interactions between the atoms. So this is no longer guided by lasers, but this is actually guided by what I call the dipole-dipole interactions of the atoms. So here you have a sequence of 3 steps, which are each one corresponds to a rotation, if you wish, of the qubit in the Bloch sphere, which will make the atom go into the Rydberg level. The first one, I called it a pi pulse because it corresponds to a rotation of pi in the Bloch sphere. Then you have a second one, which is the target. You know, depending on the value of the control, we expect the target to have a different effect. And when it's trying to reach the Rydberg level, then there's this shifting of the energy caused by the dipole-dipole interaction. So basically, the Rydberg level is used as a way of introducing this quantum logic between the qubits. And then, when we are done, we will relax the atom back to the digital basis. So by beginning, for example, here in 0, 0, we end up with a state which has gained a phase because of this rotation of 2 pi. And this is the protocol for all the different combinations of the control and target qubits. This is the protocol for a control Z gate. And from then on, we can build the control NOT gate by using local action, using what is called a Hadamard gate, which is another rotation that we do on the digital basis. But in order to do all of these steps, we have to go back to the 2-photon process and then to the transitions between these ground and hyperfine ground states, which is then it's called a Raman transition. So we are using beginning a model of this that is based on Julia, and we are using this to be as detailed as possible. And as I said, also there's the machine learning approach. Now, when you're satisfied with these transitions, you go into an intermediate level, if you wish, which is called the pulse sequence design level. So for this, Pasqal has devoted some effort into developing an open source project, which is called Pulsar. So this helps you designing the pulse sequences for a neutral atom device. So here I set up an animation of what Pulsar looks like. You can basically design all of the channels that act on your register. So imagine here are your atoms, and then you include the instructions for each of the channels. Some of these channels are local. They act on specific atoms. Some of them will be global. So they act on the entire register. This is going to be the first version out. We are now developing the graphical user interface so that it becomes more easy for pedagogical purposes. Although one of the main objectives of Pulsar is that it allows you to send instructions to an actual quantum processing unit, for example, those that are built by Pasqal, or that is capable of being emulated efficiently. So this is a representation which is in the lower level than the circuit representation, although you could abstract things into quantum gates and then compile them into pulse sequences. So for example, many of the projects that we are doing with Cinica, they used this representation to try to, for example, to find optimal pulse sequences for specific purposes. The original backend was a project that was done with the Unitary Fund and QTIP, and which is based on leveraging on all of the open source packages that are used for simulating quantum systems, which goes from SciPy, then QTIP, and then Pulsar, in order to run these simulations. Everything is open source, and you can access the code, and you can simply run pip install Pulsar, and then you can begin playing with the tutorials that we have put online. Now, associated to all of these simulations, there is what we call the quantum associated or quantum inspired algorithms. And there are many tasks that are related to the actual running of a quantum algorithm. For example, if you have pulses at your disposal, then you might be asking, what is the best way of applying them? What is the best pulse shaping techniques? how can I introduce a good cost function and a good optimizer function that allows me to defeat any variant plateaus or noise, or actually to avoid them. And so this is what is called the quantum optimal control in general. Now we can also leverage on one of the important points of the neutral atom architecture, and that is the freedom that you have in the connectivity of these atoms. So we are not bound to any underlying lattice or any particular positions. So we can choose the connectivity that we want in our system, and you leverage that to, for example, tackle QAUA problems or even to solve quadratic or constrained binary optimization problems, these Kubo problems. You can use the freedom in the embedding of the system to solve approximately and with good success on many of these problems. One of the goals of the emulation team in Pasqal is also to study ways of efficiently simulating the system in these types of problems in small sizes, so that everything is under control, and then verifying it with the machine, just as with the histograms that I showed you some minutes before. For example, truncating the Hilbert space to certain types of transitions, and then studying graphs, particular graphs that are formed under these pulse sequences. So here is, for example, an example of some embedding that it represents a Kubo problem. In this case, it was a 10 by 10 Kubo problem, but this can grow, as you see, to what is the current capabilities of Pasqal, which is 100 atoms. And then we can also use some of the quantum machine learning applications, which is the implementation of a quantum evolution kernel. For example, if you want to classify graphs that are formed with these atoms, you can use some sort of pulse sequence to understand how these graphs behave under the sequence, and then try to find correlations between them. Finally, for the measurement of these systems, we have what is called a projective measurement. So we either see zeros and ones for the Z basis. So this means that we should find clever ways of optimizing the number of shots that we take. Because if, for example, you want to do a tomography of the system, you will need a lot of resources. This takes us to the study of classical shadows and de-randomization for intermediate scale applications. For example, a BQE algorithm, which uses de-randomization and the fact that you can actually do these rotations locally on each of the atoms to choose each of the observables of the molecular Hamiltonian, and then use this to reduce the budget of shots that you require in your system. So the next steps will be for large array simulation. These are examples of hundreds of neutral atoms that are in square or triangular lattice that we produce at Pasqal. But in order to understand better how they behave, we need to have simulation of these. For example, if one was interested in building a particular type of state, preparing a state. One of the ways that you can follow this as your size grows is to use tensor networks, a matrix product state representation. That's the technical name of what you use in a zigzag form, and then to try to understand how the correlation function behaves for these types of systems. Of course, there are many other approaches if you change the geometry, but it's an interesting research and also application problem to understand how the large arrays of qubits behave. Especially because when some company or some group announces that they have some advantage or some supremacy, as in the case of Google, there are many other groups that are trying to put this into test. And some of the main ways of doing this adversarial benchmarking is to try to use tensor network algorithms. Now, as a summary, I guess you could see that the numerical computations in Pasqal depend on the number of qubits you're interested in. So you have a few qubits, you can still do a lot in terms of understanding the fidelities and the errors that are happening in your machine. So it takes a lot of computation in that side. Atomic physics level emulation, and we are working hard in trying to have the most detailed model possible to help with the hardware design. As you grow the number of qubits, you can start designing your pulse sequences. As I said, this idea of using pulsar to design the pulse sequences to shape the pulses, the laser pulses that act on the system. And then try to use some packages, either SciPy or even some lower level code such as C++, based on state vector evolution. Once you go past the very, 16 or 20 or 20 atoms, you are with the problem of having a large array of atoms. So in order to extract some information, you will need tensor networks, and especially as you see in many places, this is the point in which you start needing a large cluster, for example, the GPU backend, or even something larger as the supercomputers that are offered by Jenica. So with respect to GPU, at Pasqal, we have begun a collaboration with NVIDIA, and we have acquired a cluster of the latest DGX A100. This is designed for powering research and development at our company. And we are also using it to research application interactions. Maybe there's some cases in which some applications require a hybrid model, not necessarily just a completely quantum approach, but there is some interaction. For example, in the case of quantum machine learning, also in the case in which you need to optimize parameters in some clever way. And also because Pasqal is interested, in the HPC ecosystem, into interact with all of the different tools that are in this high performance computing. So we have acquired these cluster facilities, these GPU clusters, and we will begin developing from January of next year in the tools provided by NVIDIA. Precisely to do the different tasks that I mentioned during this talk. So to finish this short overview of what we're trying with numerical simulations in Pasqal, here is a bit of the roadmap of our stack. So the Pasqal QPU, we're not seeing it, as an isolated tool that is solving problems by itself alone. But it's part of a roadmap of development. So on top, you may have the applications, the exact, the precise SDKs that allows you to solve different problems, QUBOs, quantum chemistry applications, differential equations, nonlinear. But then we also want to understand how to best design the way that these applications are being performed on a particular type of processor like ours, which is neutral atoms. So this takes just beyond design. Also, there's some compiling between the quantum circuit representation to something that can be performed in the hardware. And then we have this other side, which is based on emulation, which for the moment was just a module in Pulsar, but is now becoming our efforts in understanding what classical computing can give to quantum computing in terms of understanding. And vice versa, what quantum computing teaches us about what classical computers can do. And beyond that, there's the idea of using NVIDIA's tools like Quantum, but also to create some customized tools, code for this liquid architecture. And finally, in the bottom, we might have some cluster of GPUs, or maybe using a supercomputer like those offered by Jenica, like Mengoni 100, or even the new projects that they have ongoing. So this was this concludes my presentation. You can ask me any questions about what happened, but I would like to thank you for the opportunity of showing us what we're doing at Pasqal. Thank you.
Thank you very much, Sebastian, for this great introduction. So let's see if we have some questions. I think you can, if you raise your hand, I would like to recall, you can ask directly the question. Okay, see one question in the chat. Can you explain again why is it possible to reduce the number of short pulses with rotation of atoms? Are you increasing the number of qubits?
Okay, so this is what is called the de-randomization technique. So the idea is that if you, for example, try to measure an observable, a list of observables, so you have a Hamiltonian with many local terms, I don't know, 10 or 100 or hundreds in the case of quantum chemistry, you need to calculate the expectation value of each one. And that's very costly in terms of the number of shots that you need. So what you do is to use some statistical, some estimator of these observables. And there is a result that was done by the group of Presskill and I forgot the other names, but it was the group of John Presskill, in which they studied how to obtain how to predict all of the observables at once. For this, you need actually a logarithmic number of measurements in the number of observables. So it's, if you have 100 observables to measure, you actually need 10, a factor of 10. And then, of course, it increases with the precisions that you want. So this is based on the idea of using randomized measurements. So instead of measuring the exact list of observables, you used randomized Pauli strings. And you can even go further and actually de-randomize them in such a way that your confidence bound, so the thing that tells you that you will achieve a certain precision, in such a way that this value is optimized. So you see there's this idea of using randomized measurements with local rotation on each qubit, and then de-randomizing it in order to obtain the best possible sequence of measurements that give you the best information possible of your list of observables.
Thank you. Okay, let me just ask you one question. So, what's your vision about the integration of the Pasqal QPU with an HPC system? So what do you think are going to be the best way to integrate them, or the best algorithms in the future?
I think that there is many connections now with machine learning at the moment. There is not a clear picture of what exactly the place of a QPU is, but we are seeing that, for example, if you're trying to use some classification task, there's a component of the quantum processor that is useful, but by no means it can work in isolation. So there is necessary some aspect of communication between a GPU facility or even a supercomputer, because the QPU is very specific in the task that it does. So we need to learn how to program with this in mind. You know, how to build a full stack in which we understand what is the precise task that the QPU will perform and what is the type of data that it will receive. You know, there is quantum data in the sense that if you want to prepare a graph with the atoms, so it takes some resources, but there is also just classical data in the sense that you can embed the information on them as you wish. And it's important for us to understand how to best relate these two worlds. The vision is that in the future, you know, the Pasqal or a quantum processor is just a part of a huge computing center for the moment. So it's that is the approach that we're taking at Pasqal.
Okay, yeah. Thank you so much. I think that's it for the moment. Yeah. And so thank you again, Sebastian, for being here. Thank you for your contribution. It's always a pleasure to have you, people from Pasqal, here at our conference. So I think we have the break right now. So we're gonna see again each other in 15 minutes. So at 11:15.
Okay. Thank you, guys. See you in 15 minutes.
Hi, welcome back everyone to the second part of this session. Hi Federico, welcome to the workshop. It's a pleasure to have you here. So let me just briefly introduce Federico. Federico Mattei is technical leader at IBM and also IBM Quantum ambassador. And today he's going to introduce the IBM Quantum environment, the growing quantum performances and the quantum network. So I think Federico, you can start. You can share your screen.
Okay, great. So
perfect. We see it.
Print?
Yeah, we see it.
So thank you very much. I would like to thank all the organizers also for this the meeting of this year. We participated in the last 4 conferences, and it is always a pleasure to be part of this annual meeting. So I'm Federico Mattei. I'm working from IBM, and IBM is studying quantum computation since the early 80s. And we are working to develop superconducting universal quantum computers. And we also developed a software kit called KISS-Kit, Quantum Information Software Kit, which is open source, so is publicly available to program our system. We released on internet, so we public access the first quantum computer in 2016, and now we are growing. Just 1 month ago, we had our annual Quantum Summit meeting, in which we presented all the evolution of our system, of our software stack, and also on our network. So I will go through these announcements so that we can see together how is proceeding the evolution of IBM quantum computers. So let me start from this equation, which is the way in which IBM would like to measure the performance of a quantum system. So we are not speaking just about the hardware or the processor, but we are speaking about the whole machine and also the software which is surrounding quantum computing. And as far as we will see, in particular in the speed part of this equation, we are working strongly to connect the quantum computers with classical computers, because we believe that the real quantum advantage will be achieved as soon as possible if we make quantum computers and classical computers work together at best. So in this equation, you can see that the performance of our computers and our systems are measured with these 3 quantities. The first one is scale, which is measured by the number of qubits. Of course, as I already said, we are working on universal quantum computer or gate-based quantum computers, as you have heard. So these are not annealers qubit, of course, but it's a quantity which is easy to measure and also easy to compare with other approaches. Then we have quality. The quality of our systems are measured by quantum volume, and we will see which kind of quantities are inside this quantum volume contribute to measure this quantum volume. Of course, this is not a standard measurement. It is a proposal which we proposed to the market in 2019 with a scientific paper. And we hope that we will have as soon as possible a standard in order to measure this kind of quantity for all the quantum systems. Aside to this, we measure speed. It is a new quantity what we introduced this here. We measure it in CLOPS, so circuit layer operation per seconds. And we will see in this presentation how software and also classical computation helps to improve this kind of quantity. So in this chart, you can see summed up, which is our achievements in the last years. So about scale, we are growing the number of qubits, and just 1 month ago we announced the Eagle system, which surpasses the number of 100 qubits per processor. It has 127 qubits. Looking at the quality of our processors, at date we have a processor with 128 quantum volume, and our target is to reach 256 quantum volume in this year. So we have few days to reach this goal. Regarding the speed, as I already said, we introduced this quantity just this year, so we can just infer what could be this measurement during the previous years. But for the moment, we have 1,044 clocks, and we hope to improve it year by year in the following one. So let's focus on each of these quantities. Let's focus on scale in particular. And here is the roadmap that we presented last year about the evolution of our hardware processor in terms of number of qubits. So starting from 2019, we are beginning to measure this generation of systems. Of course, I already said that we published our quantum computer since 2016. At date, we had just a 5-qubit system. But now, of course, we are going forward. We achieved the goal of this year, so we presented the Eagle processor 127 qubit, and the next year our goal is to reach 433 qubit with the host rate processor. The most important goal for our side is the Condor processor in 2023, when we will surpass 1,000 qubit, and it will be really an important goal because with more than 1,000 qubit on a processor, we will be able to do error correction, and probably for some kind of algorithms it could be possible to reach quantum advantage. So we hope to reach this target soon. Of course, we will not stop with 1,000 qubits for processor, but our idea is to go forward in order to build 1 million and beyond qubit for each system. As I already said, 1 month ago we announced Eagle. We had the possibility to surpass 100 qubit for processor, building this chip on different layers. So on one layer we have the qubits, and on the other layer we have the resonators, and so we'll have the connection and the readout part. These are the connection and the picture of the sides of our processor. As you can see, we have this something like an hexagonal topology. It seems to be the better trade-off between the connection, the connectivity between the qubits. Qubits are, of course, the circles with the number inside, and the connection are the white slash between one circle and the other. I'm saying that it is the better trade-off because experimenting more connected situations, we will face problems like crosstalk between qubits, and so it seems to be the better situation in order to have a good coherence time and also a good connection between qubits in order to do entanglement for the algorithms. So that's the current situation. Let's turn to quality. So as I already said, we presented our proposal to measure the power of quantum computing using this quantity. This quantity is composed by several measurements that we can do on a quantum system. Of course, the number of qubits is just one component of this quantum volume. Of course, we have coherence time there, we have crosstalk, and we have several kinds of fidelity that we measure in our system, the measurement fidelity, gate fidelity, initiation fidelity, and all the rest. So all these components are summed up in this quantity, which from our point of view is the best way to measure the real power of a quantum computer. From the quantum volume point of view, as I already said, we are waiting for the 2056 processor with quantum volume for processor. But a very interesting announcement has been done in the Quantum Summit. In particular, we announced that we surpassed 1 millisecond for the coherence time on our processors. And we also announced that we surpassed 99.9% in the gate fidelity. So these are two important parameters which are then converted in the quantum volume measurement. This is the plot of our the quantum volume of our system during the last 4 years. As you can see, we doubled the quantum volume each year. Last year, we did 2 steps. And so we hope that we can do something like more slow also for quantum computers, and we hope to be able to double the power of our quantum computers in terms of quantum volume each year. Then let's turn to the speed part, which is the last one that we announced, the last measurement that we announced, but it is very important also from a productive point of view, because when we are going to we will use quantum computers in production, in the business or in the research, the speed component, it will be very important, in particular on some kind of business. For example, the financial services and also the logistics, in which you have to do calculation very quick. So this is the quantity, the secretary operation per second, and it is an important measurement that we will continue to use in the next year. As I already said, it is a crucial component in order to bring quantum computer into a real practical usage. So in order to bring improvements in these speed components, as I said at the beginning of this presentation, we are bringing classical computation near to the quantum computation in order to improve the speed. Here you can see that we have 2 ways of including involving classical computation in a whole computation which involves both. The first one is real-time classical computation, which is inside the QASM, the Open QASM 3, so the quantum assembler language that we use to program our computers. And here we have some classical real-time components which help the quantum computer in order to perform at best. And also very important, this near real-time classical component, which is the Qiskit runtime, which we introduced just from some of our quantum system during last spring. And during the Quantum Summit, we announced that the Qiskit runtime will be available for all the IBM system. What's Qiskit runtime? Qiskit runtime brings classical computation near to the quantum hardware, and it seems to be really useful for some kind of algorithms, for example, variational algorithms. So as you can see here, you do your Qiskit program on your laptop, on your computer, then the program enters the queue of the quantum system, and once it enters the queue, the Qiskit runtimes takes control of the algorithms. It sends the quantum circuit to the quantum hardware. Then it takes the result of the calculation, then do the variation of the classical parameter, and then the computation returns. And only at the end of all the variational process, it returns the result. So with this kind of solution, we are taking away all the time of the latency time of the connection, of the internet connection. And in this way, we have been able to speed up our calculation by 100 20 times the number we used to have before, just with this classical involvement in the process. This is the Nature paper we published in 2017, in which we calculate the basic energy, the ground energy of the lithium hydride. It takes quite a lot of time to do this because this kind of calculation is a variational calculation. And so we have to go to the quantum system and then back, do the variation, and then return to the quantum system. So it takes several days. But with Qiskit runtime, we have been able to do it in a few hours. So the time contracted by 120 times. This is our roadmap. As you can see at the bottom of this chart, you can see the hardware roadmap I already explained in the chart before. But here you can see several other lines, which are the components of our software stack that we are developing for different kind of developers. So we are addressing different kind of developer, not just the assembler developer. Let me say that here are called kernel developers. For them, of course, the circuits, so the possibility to build circuits is available. Since 2016, we didn't put all the years before. It is possible, of course, both using Python, so with Qiskit, and also with Circuit Composer, which is a graphical toolkit, very useful for the education. The step of this year has been Qiskit runtime that I already described in the previous chart, and the next goal that we have programmed for next year are dynamic circuit, which means that I can interact during the execution of the circuit, just reading 1 or 2 qubits of the algorithm, and then depending on the result of this measurement, and I can interact with the rest algorithm of the algorithm that is already running. So some kind of the already known algorithms theoretically use this kind of approach, and in the next we hope to be able to empower our system and our software stack with this kind of capability. We are also addressing algorithm developers with libraries on several fields. Here you can see the 4 fields that we are addressing today are optimization, natural science, in which you have also inside you have high energy physics, quantum chemistry, and material science. Then we have finance, several algorithm developers developed for finance, Monte Carlo-like algorithms, portfolio optimization, and so on. And then we have machine learning. In particular, we started with categorization, so quantum supervector machine and other algorithms for machine learning. All these libraries are already available on Qiskit, so publicly available. During the Quantum Summit, we already introduced some kind of components that we are going to publish in the next years to support developer algorithms. So guys that are not working directly with the hardware, but are working to develop algorithms. So of course, the most important target is the error correction that we will begin to introduce, of course, when we will have enough number of qubits. But we introduced this concept, which is very interesting, of circuit knitting. It means that when the developer algorithms develops one algorithm, the circuit knitting try to decompose this algorithm, if possible, of course, in smaller execution parts. Then it executes all the different parts separately. This is very useful because long algorithms will introduce a lot of noise, but smaller execution will reduce the number of noise. And then the circuit knitting will recompose the complete algorithms in order to give to the algorithm developer the full result. Starting from 2023, we will also introduce modules for model developers for business, and of course with science is a more in a more abstract way of programming. They are not interested in the kind of hardware, so they will match both classical and quantum computation. They will work with several kinds of algorithms in order to build business models or research models. For the moment, we do not have this kind of components because we think it's not useful until we will have error correction and enough number of qubits, but we will start to release this kind of component from 2023. So another important announcement that we did last month, regards the integrated systems. At the end of 2017, we announced IBM Quantum System 1, which is an integrated system which includes the processor, the wiring, the cryogenic platform, and also the control electronics, all in one single object ready for the production. The Quantum System 1 has a limit and the number of qubits for processor. So the Eagle processor we announced this year is the last processor that can run in a Quantum System 1. So we announced the development of a Quantum System 2, which will be able to manage processor with more than 127 qubits. We are developing this kind of platform in partnership with Finnish enterprise which manages cryogenic apparatus, which is Blueforce, and we are working on systems that can be modular, as the one that you can see here developed by Blueforce, and this is just a rendering on what will be the Quantum System 2 that will be available in the next year, ready to host the Horseprey processor, which will be the processor that we will have next year. So aside to the technology and to the software news, we also are developing a really wide network of research centers and enterprises and universities that work together with us. We surpassed the number of 170, and we are working on a lot of use cases with them. For example, just looking at the first line and the first column, which are the partners, so the highest way of becoming member of the IBM Quantum Network. Here you can see, for example, JP Morgan Chase. With them we are working on the pricing of the European stock options. We are working also with, for example, ExxonMobil, working on thermodynamical variable. We are working with Daimler in order to analyze the reactions which are going on inside batteries in order to build batteries with a higher autonomy for electric cars. And all the rest, of course, I'm not going through all of them. Very important are the national partnership that we are developing with some countries all around the world. In particular, here in Europe, we have the partnership with the German government, which is managed by the Fraunhofer Institute. In the last spring, we have seen the previous Chancellor, Angela Merkel, which participated to have the event in which we presented the German system, which is the Quantum System 1, which is installed for the Fraunhofer Institute in Germany, in order to serve the small and medium enterprise of the German market. We have similar agreements in Japan, and last month we also announced that a similar agreement has been done with the South Korea on the Hyonsei University, that will manage the system in Korea. This is my last chart. It's just a chart to show you how you can interact and how you can leverage all the tools that were given open for the community. The first one is the Qiskit textbook. So if you go to qiskit.org, you will find a really deep textbook about quantum computation, which has both the theory and also the exercise that you can run on real quantum computers using Python. The second, you can explore quantum computing website from IBM and also Qiskit in order to have a look to the circuit composer, so the graphic tool for the program part, and also to Qiskit to look at the tutorials and a lot of materials that you can use to develop your use case. Then we also release a couple of certifications. So we have Qiskit Advocate certification and Quantum Developer certification, which are openly available and you can apply. On YouTube, you can find a lot of videos. You can also find the videos of the Quantum Summit. So if you are interested on what I've said today, you can have a deeper look on this kind of presentation video. Then we have research and education programs. So if you are doing research on quantum, you can apply to have access to more powerful quantum computers and dedicated quantum computer for your lessons and for your research. So that's the end of my presentation. We have a couple of minutes for questions. Thank you very much.
Thank you. Thank you, Federico, for this great overview of what IBM is doing in the quantum realm. So let's see if we have questions. Okay. So in the meantime, let me ask you maybe just a curiosity. So you said that you're going to have dynamic circuits in the future. So as far as I understand, let's say intermediate measurement on the system, and do you have in mind some application, a short-term application that will benefit from this new feature, or?
I don't have for the moment any specific use case, but it's something that will allow us to do interaction, which is for the moment quantum algorithms, is quite a black box. So the possibility to have an intermediate measurement and the possibility to interact, introducing other qubits, of course, and other gates, it could be a great improvement on what can be done on a quantum computer.
Okay, thank you. So some questions from the chat. If you can tell more about the researchers and education programs, so probably how can you enter in these programs?
Okay, so these are two programs. I can then share, of course, the link to which you can apply. It's quite important to have a research that is already been developed to some level, because as I've already said, we have open access systems that you can leverage, so you can work on them. You can work, of course, on simulator, also simulators with noise. So after all these kind of studies, if you have publications, also archive publication, you can put them in the application form, and then we will review, IBM Research will review your application and give you access. The systems which are available for the quantum program, for the researcher program, are system of 7 qubits, so just a couple of qubits more, but one of the important things is that they are reserved for the researcher, so they are not public for everybody, so you will not face all the queues that you find on the publicly available one.
Okay, thank you. So another one from the chat. So David is asking if it's possible to get technical support from IBM when you deploy the code for our algorithm, quantum computing algorithm.
So, well, of course, you can ask to IBM. The better thing to do, also from my experience, is to leverage on the Qiskit open source community. On Slack, you can find a Qiskit channel with really a lot of developers, an open source developers that are working on our platform, and they are really efficient to give you support if you have some problems, some issues. Of course, IBM research persons are dedicated clients, and so they take some more time. But the Slack channel for the open source community is great for this.
Okay, probably there are more questions in the chat, but I think we can stop here, and if you want, you can answer directly in the chat. So yeah, thank you again, Federico. It was a pleasure to have you here. And let's go to the next speaker, and the last speaker of this morning session. The next speaker is Fabio Baruffa. Hi, Fabio. Welcome to the workshop. You're muted.
Yes. Hi, good morning. Thanks.
Hi. So just a quick introduction. Fabio Baruffa. He is Senior HPC and Quantum Solution Architect at AWS, so Amazon Web Services. And today he's going to talk about Amazon Braket, which is the software development environment that Amazon has developed for quantum computing in the cloud. So thank you for being here again, Fabio, and yeah, the floor is yours.
Thanks. Let's start to share. I think you can see my slide, right?
Yes.
Perfect. Hi, good morning, everyone. And thanks, Riccardo, for the introduction. And it's very pleasure for me to be here and talking about Amazon Braket and how Amazon is taking the complex problem of providing to customers and researchers quantum computing capabilities. Let's start about what is quantum computing at AWS and how we are making our progresses and what is our main research area. So AWS, quantum computing AWS can be summarized in 4 important pillars that we are moving forward. And the first is the AWS Center for Quantum Computing. That is our lab in Pasadena, where we develop our hardware and our software. And we do research and development in the area of quantum computing and quantum software. Then we have the AWS Partner Network. That is a community of our partners that can help customer research to develop their own solutions. The other pillar is the Quantum Solution Lab. This is a pool of scientists that works hand-to-hand with customers to provide solutions for quantum computing, to develop software. But they have expertise not only in quantum computing, but they have expertise also in high-performance computing, machine learning, AI, so that everything is so all these topics are integrated for providing the best solution for our customers. And then the other pillar is our service, Amazon Braket. That is a fully managed service that runs in the cloud, where you have access to several quantum computers and simulators through AWS cloud infrastructure. So the AWS Center for Quantum Computing, actually, we opened the doors of this building in October 2021. There's also been an announcement recently where we work with the leading experts of quantum computing to develop the processor and the software. This is based on the Pasadena. This is really building close to universities. So this is a pool of hundreds of scientists that are working together to the goal of developing a full tolerant quantum computer based on superconducting qubits and the software. So we try to build directly from the beginning an error corrected qubit. A bit more words about the Quantum Solution Lab. This is as I mentioned, this is a pool of scientists that we have in the AWS. They do collaborative project and engagement with customers. They identify applications, potential use cases, and go deep dive with the customers regarding science and quantum computing. So they are also providing, for example, benchmark algorithms and the dedicated solution that is integrated within the AWS cloud, leveraging all the potential and all the services that we provide. So this Quantum Solution Lab also can be engaged to build the internal expertise. If there are customers that needs to be trained or needs to be find the best strategy to build up a team that works on quantum computing, this is also the team that could help. And the main topic that they are working are machine learning, quantum computing, and HPC, because we think those are all integrated. These are all integrated in the same computing capability. And so this is really a pool of scientists and experts that we can offer to our customers. So here is a selection of our partners and startups that they focus solution with Amazon Web Services. And this list keep expanding month by month, where we find new partners. This means that the list here is all the partners and startups that are building solutions on top of Braket. And some of these names are already known for you. Some might be new, but those are the one we work with, and they provide the best experience to the customers. And then the important pillar here is our service. So the Amazon Braket is a full managed service. So that means we manage all the infrastructure, we manage all the software installation. What we provide is an easy access for scientists and developers to explore and test the quantum computer. So with Amazon Braket, you are able to build your expertise. You are able to build your algorithms in different flavors. So you can use a command line interface. You can install the Amazon Braket SDK to your environment. You can use Jupyter Notebook, and so on and so forth. Underneath of that, you can, after you build your application, then you would like to test it in a noisily free on a noisy environment. And we provide simulators here. So this can help for rapid prototyping and testing of your idea or of the algorithms. We provide also access to several quantum computers, and I'm going to give you a bit more details in a few slides, where with our partners, we provide access to a Niles computer, a Gates quantum computer as well. And in the end, once you run your application, you will be also able to monitor the algorithm and the results and analyzing using the tools from AWS. And let's start with Amazon Braket. So let me give you a brief introduction about that. So Amazon Braket is a service integrated with AWS Cloud. So that means you can leverage, using Amazon Braket, you can leverage also other services that maybe you might be familiar to from AWS. For example, here you see boxes here around that. There is AWS Cloud, and Amazon Braket is one of the services that we offer. It's the service for quantum technology and quantum computing. So this Amazon Braket can be used using with other services as well. For example, you can store your results in the cloud using the Amazon S3. This is the storage access to the cloud. Then you have all the security and all the management of your account, and also for your code. So you have the security in place with the services like AWS Identity and Access Management. And the interesting part is also the notification. So, for example, you run your application and you would like to monitor what's going on or get a notification if the job has been executed or not, then you will get some notification and also monitoring, right? So you could monitor what's going on while your application is running. And in the center box, you see that this managed simulators and this simulator. So on top of that, we have also the quantum hardware that you can have access to. On the left side of these slides, you see the user perspective, how the users interact with Amazon Private. So you could, for example, install your on your local laptop the IDE, so the SDK, the Amazon SDK, and then you can work locally, and at the end you submit your task, you submit your work, and then you will be queued on the Amazon Braket, and you can monitor this through it's an Amazon Braket console. Or if you prefer to use directly the cloud, we offer the managed service notebook, Jupyter Notebook, where everything is already installed and managed by AWS. So you just go there, do your development, and submit your task. Regarding the simulator, we offer local simulator and the managed simulator. The local simulator is the one that we provide in the SDK, and this local simulator is a pre-install on the Braket SDK. I can do state vector simulator with and without noise. Of course, this is a limited simulator because it depends on the number of depends on the hardware that you are running on. So the number of qubits, it really depends on the amount of memory you have. But on the other hand, we have managed simulator that can leverage the HPC capability. So we have the state vector simulator, then we have the tensor network simulator, and the density metric simulator that allow you to play with noise. And this is everything. Everything provided in the same development environment. Regarding the hardware, we have several hardware that we provide. So this is the quantum annealer from D-Wave, from annealing problem, as we have learned today as well. Then we have trapped ions provided by IOQ and superconducting qubits provided by Rigetti. And if you have heard the news, actually, a week ago, we have announced the expansion of our hardware offering. So we are working with the Oxford Quantum Computing, and we are going to provide to our customers and researchers the possibility to use this hardware in integration with Amazon Braket, and the same for the QA-RAD, that is the Rydberg atom out of atoms. Important thing is that from the Oxford Quantum Computing to mention is that this will open up the possibility for Europe as well, because we open up a region in the European time zone. That means you could also use this on your time zone. The interesting part about the integration, and this is just a very synthetic here, is that the integration comes not only from the infrastructure, but from the user's perspective in the simple Python language. Because when you run your circuit or you define your algorithm in a Python script, you could leverage several devices. This device is an abstract object that can be either a simulator or a quantum processor unit. And what you need to do in your application is just to change the line here that is highlighted that specifies the device. You give there the Amazon resource name that allows you to identify the selected device, and then you run it, the same code and the same application on different devices. That means either on the simulator or several QPUs. Another important update that we have recently is the possibility to hybrid job, and this is a new service feature that has been announced a week ago. What is hybrid? Hybrid is the possibility to do classical quantum algorithm in the same environment. As you have learned, variational algorithms can be the QAOA or the variational quantum eigensolver and others. They are algorithms that leverage the classical computing and the QPU for certain calculation. For example, you have a parameterized circuit that needs to change, and this some of the value and some of the encoded can be done directly on a QPU. Then once these parameters are adjusted, then there is an objective function that needs to be evaluated, and this will be done on the CPU. The hybrid algorithm is very it's very promising for the near-term quantum computer now, and this is a similar of what is done, for example, in high-performance computing with offloading computation to GPUs. In this case, you can think a QPU like a coprocessor where you offload some part of the computation. What we have released right now is the possibility to do hybrid job, and let me explain to you a few concepts before you could get what I mean here. So we have definition to understand that you have the definition of shots and tasks. A shot is a single execution of a quantum operation on a device. So there can be a circuit like here on the left part of these slides. Then the task is a series of repeated shots on a particular device. And this is important because this is the way you can leverage and have the results on a quantum computer. So what you do, your task is a series of several shots that collect statistics and collect the results that you are looking for. The hybrid job is a sequence of classical and quantum computer cycles. So what is happening here is that the classical computer is working hand-to-hand with the quantum computer. So what it means at the moment, what is the big difference here? When you submit your task, that is a sequence of shots, then this task will be queued and then will be executed on the quantum computer once it's available. But if you have an hybrid job where the classical computer and quantum computer needs to be working hand to hand, for example, in an optimization process or in a variational problem, then you need to reserve the time for such kind of computation to work together. In this case, you submit, instead of task, you submit a job, and then you reserve the access and the classical computation for this job exactly. And this could reduce the latency of accessing the quantum processor through the task. And this is the way we have leveraged the hybrid jobs. The hybrid jobs allows you to two things. One is to have dedicated resources for classical compute. And second is to have a dedicated resources for quantum computer that works hand-to-hand with your classical approach. And this allows you to do seamlessly the hybrid algorithms. How this actually works, from the user perspective, you create a job instance, and this instance can be this instance is what you define. And this can be, for example, provided by containers, provided by script. And then in this job instance, you specify what you want. If you want a managed simulator, or you might have a QPU or quantum hardware. And everything is integrated through services like Amazon S3, that is the storage, the CloudWatch for monitoring, and the Elastic Container Registry, that is the Amazon service for managing containers. So what you do is the classical compute that manage the hybrid job. What you need to provide is so there are 3 ways to pre-build the containers that we offer. So what you do is you just bring the container with your application. This container will be stored in the Elastic Container Registry. And then while it's done, so you could, in the meantime, monitoring the algorithm through the Amazon Braket console. The important point is the priority access to the hardware, because once you submit your job and the job will be executed, you will be the only one that at this moment, while the job is running, will have access to the quantum computer. So that means you reduce the latency to get access, and then it will be released after your job has been finished. So because as you might have experienced, maybe with some of the workshop or some of the task you have done with Amazon Braket is once you submit your task, the task is queued, and this hardware is may be available by others as well. So in this case, your queue time might be long. On the other hand, once you submit the job, once the job is in the queue and then it is in the running state, you have exclusive access to quantum hardware, and then you can reduce the waiting time for accessing the QPU, and also reducing the time to get your solution done. And the next part is how to build with Amazon Braket. So Amazon Braket is, as I mentioned, is one of the more than 150 services that we have at AWS, and that means you can think beyond that. So it's not only we provide the quantum technology, of course, together with other services. So that means you could prepare your application and integrate with other services as well that could leverage a complete solution hand-to-hand from beginning till the analytics of your results. In the same infrastructure, because in the same infrastructure we managed the quantum resources and the classical resources, and this can be an advantage for all our research and customers, that in one place they can have the classical compute and the quantum compute on top of all the services that we already offer. This is just an example of a custom API that you could build. So you have a service called Amazon Cognito that is the identity for a certain selection of users. For example, you could provide the service itself, and providing a selection of API that could access, for example, the Amazon Braket or the classical compute. So just an example of how you could potentially use other services that we provide from AWS. And the Amazon Braket is also, since the near-term algorithm are also in the space of HPC and machine learning, HPC in terms of simulating quantum circuits and machine learning. So with other services, you might be able, for example, to use the analytics service or the databases to store your results, and also doing machine learning pipelines together in the same environment. And the last part is how do we get started? So if you would like to learn more, or you get it guided with Amazon Braket, so we have several examples through our GitHub repository. So these are Amazon Braket examples that you can download and play with. You can start also to install locally your Amazon Braket SDK to get started and get familiar to the way you could develop your applications. Then we have integrated for easy access to a library called Penny Lane. That is a library for programming quantum computers, quantum machine learning, and also quantum chemistry. And this is you could also see the tutorial from Penny Lane. We have provided a plugin that allows you to work together with to work on Braket SDK together with Penny Lane. In case you would like to start, so there are two ways. So one is you could open the AWS account, and then from that you had 1 free hour per simulation time per month. So you have this is part of the AWS free tier, and this is quite interesting for experimenting if you would like to do that. Or we have also the possibility to apply for cloud research credit. So in this case, if you have a project and you would like to experiment with the quantum computer, so you just go here, apply, and write a small project statement and what you would like to achieve, and the amount of credit that we can grant, and this will be reviewed and then approved by AWS. So these are the ways to access. We have also special partnership with also with Cineca, where we have done several trainings this year, and also the possibility to through Cineca also to access this Amazon credit for research. And then I stop here. So and thank you for your attention, and I'm opening now for Q&A.
Hi, Thank you very much, Fabio, for this great overview and great news from Amazon side.
Thanks.
I see one question in the chat, which says, could this job be submitted to Amazon Braket via Amazon Lambda?
Yes, I think everything is integrated in the same environment. So you could create a solution that triggers a Lambda. So what, for example, you could do is like you upload your, theoretically, right? I just, as a solution architect, I also like building new stuff. In this case, you trigger one idea that could be, for example, you have your circuit, your code you upload to this to S3 bucket. This S3 bucket trigger a Lambda, and this Lambda triggered the job that will be submitted, and then and then at the end you have another Lambda that could trigger the results. I think these are the potential. That's the reason why the integration with other services can give you the potential to really invent solutions that allow to speed up your journey. That yes, I mean the short answer is yes, and this is actually what we are looking after when we want to work with customer research. So that's a nice question.
Great. So other question from the chat, or let me see if there are also on YouTube. Okay. You said, okay, you have this new part, this hybrid part that you developed recently. So I think probably, as Federico said, IBM goes like probably something similar to what he said, what IBM calls IBM runtime, ICHEC runtime. Okay, so but I think, I mean, my idea is that right now a lot of approaches go in the lot of short-term NISC approaches go in the direction of hybrid variational algorithms. So it's like important to reduce as much as possible the latency between classical and quantum. So is it also possible to let's say test this hybrid part, which is it already in bracket?
Is already available. Is already available in the bracket. So I actually I think it was short on time. I wanted to prepare a demo, but for this short time it might be not ideal. But yes, this is already available, and if there is someone interested on that, so that would like to leverage, just keep in touch with us, also with you, right, Riccardo, and then we can follow up later.
Yeah, and
this is available on that. So
yeah, my idea was, okay, maybe let's say we can also use the same software, the same hybrid software to launch something, let's say, that use your QPU and probably the HPC system that we have here at Cineca. So, and like something that mixes the two. Do you think is it something possible to do, or?
Good question. I don't have the answer now, but let's brainstorm. Let's brainstorm and see what can be done. But this is right now. Since this is integrated in the EC2, this is the Elastic Cloud Compute that we have. So you define how much. I mean, you define how many cores, how much memory you want for the classical part, and then which CPU, which quantum processor unit. Then you submit your job, and then the job will be queued. And once it's done, you have the two resources are ready there, and then will be done this job. It's nice to experiment. I think there will be a lot of a great idea, Riccardo, that we can that can be explored. But yes, I think that's it's a good learning. I mean, we just started. You know, everything is of course it's going with different speed and also going in different directions. But again, the journey just started for everyone, and this is interesting to see what can be done in the future. So even if this is the way the researcher would like to see. So we also work very close with researcher to get feedback if this solution or this kind of service is the one that they prefer, or they prefer a new feature or they prefer other things. This also can be part of the work with AWS.
So let me ask you another question from the chat. So is there any work in progress or on standardization across Quantum as a service from different cloud providers?
I don't know. Actually, that's a good question. What we are trying to do in AWS is the following. So we have maybe the question might be how we are working with other partners to get the AWS cloud rich with different QPUs. Actually, what we do is the first. First, we see on the market and we see on our research what are the QPU that are mostly asked. Okay, that's why we have started the service with D-Wave, rejected IonQ. They are quite mature, and there's also we have users and researchers asked. Then we expand. So we try to expand the offering. That's why we have seen that we have offer now from Oxford, and we have also from Riccardo Atoms for the special processor here. So this doesn't exclude the possibility that we work with other partners and get it integrated in the cloud. The same also, we are working on our processor, and this will be also provided in the same way. So in the unified environment with the software that is Bracket and unified cloud environment, we try to work with the partners and make this as accessible. So this is how we work and how we work and how we think about integrations.
Thank you very much, Fabio. One very last question, because otherwise it's going to be too late. Is Amazon working on developing its own quantum computers?
Yes, I think I can confirm that we work on our quantum computer. So they've been, if you are interested to learn more, just pinging, I can share all the information. So we have a research paper that is actually the hardware that we are developing is almost in 90 pages of archive paper, quite interesting one. So I can confirm it. So we work on superconducting qubits and error-corrected qubit directly from, and we use a special cat qubits development just to reduce the dephasing and on the device. Again, this is a long journey, as you know, but this is something that we have announced also 1 week ago during our reInvent, and yeah, this is very exciting.
Yeah, it's public right now, so okay, we can confirm. Okay, so thank you again, Fabio.
Thanks, Riccardo. Thanks, Daniele.
Thank you for being here. Great presentation and great news. I think okay, we reached the end of the first session of the first day, and yeah, we can go to lunch, and we're gonna see each other in 1 hour at 1:15.
Yes, exactly. Thank you, Riccardo. We will see each other in 1 hour with another session about the relationship between QC and HPC in Europe. Thanks a lot. See you in 1 hour.
Bye.
Bye. Hi, Ariana. Good afternoon.
Hi.
Thank you for being here. We will begin in 15 minutes.
Yeah, perfect. Can I just try to share my screen just to make sure
Yes,
it works?
Of course.
Give me just 1 second. Can you see it?
Yes.
Okay, perfect.
Perfect.
Let me unshare it and yeah. All right, perfect. Then in 15 minutes, well, 10 minutes or so, ready.
Thanks a lot. See you
Bye.
later. I can see you. Very good.
Okay. I have done nothing. I just reopened. Okay.
But you turn it off and on again. It's our secret.
Okay. It's a secret of
the whole IT world.
Yes.
Hi, Andres.
Hello, how are you?
How are you?
Very well, and you?
Fine, thank you. Thank you for being here.
Thank you for inviting.
Not a problem at all. And okay, we will start in 7 minutes or something like that with Ariana. Now I'm looking if there is somebody else. Hi, Jean-Philippe. Can you hear me?
Yes. Oh, it seems I can. Oh, yeah.
You I have already give you permission to speak and to show yourself, and also to share your screen. Thank you. If you want to make a try right now, it's a good time. Okay, also Luigi is here. Perfect. Hi, Luigi.
Hi.
I was.
I got the right to do that.
I was answering you. Don't worry for this morning. We will have the recordings.
Oh, this is great
website.
Because it was not mentioned anywhere. So having the recording will be great.
Yes, we didn't mention it, but thank you for saying this to me, because it was not, of course, on purpose, because we put our records every year in our website. So this year we gave it for granted, but thank you for saying me that. So we will say it later to the audience. Great. Very good. Thank you for being here. We will start in 5 minutes. Okay. Okay. Welcome back, everybody. Hi, Enrico. Hi, Ariana. We are ready to resume our afternoon session, and let me start the recording. Okay, recording is started. Perfect. So, thank you, everybody, for being here also in this afternoon. This afternoon, we will assist to a very interesting session that is dedicated to the relationship between quantum computing and HPC in Europe. For this purpose, we invited a lot of European supercomputing centers in order to explain their vision about quantum computing and, of course, high programming computing. So the first speaker is Dr. Ariana Torres-Knoop, that is advisor and project manager of quantum computing area at SURF. Thank you, Ariana. Thank you very much for being here. I leave you the floor.
Yeah, thank you. I will start by sharing my screen.
Yes.
I hope you can all see it.
Yes, we can see it.
Perfect.
Thanks a lot.
Thank you for the invitation. I'm quite happy to be here in this
pleasure.
edition of 2021. Yeah, as Daniel was saying, my name is Ariana and I work at SURF. So I guess the first step is to really tell you what SURF is, because I am not assuming you guys know it. So SURF is basically the Chineca of the Netherlands. It's a bit smaller, but it's the collaborative organization for ICT in the Netherlands. And we do different things. So we do data storage and management, network infrastructure. We also are involved in a lot of educational tools, but maybe more relevant here, we are the managers of the HPC system, so the high performance computing system. Here's like a picture of the high performance computing system. We actually got a new one recently now in September, so we're quite happy, but it's having a lot of issues, as it happens when you get a new one. We're located, as mentioned, in the Netherlands. The supercomputing center is in Amsterdam. But we actually have also an office in Utrecht, which is about 20 km from Amsterdam, and that's our main office. And if you want to know more about it, feel free to go here. So let me start by, I'm going to try to describe a little bit the process we went through from, being completely quantum ignorant to try to get somewhere closer to quantum knowledgeable. I'm not claiming we're there, but still getting closer. And the story started because a couple of people some years ago began asking, hey, when is a quantum computer going to be in your high performance computing center? Are we going to get access? And we were, to be honest, we didn't even know what to answer. So the first step was to really figure out what this quantum computing was about and try to be able to reply to these questions. So we figured out, we realized we were probably several years away from that. So, we're a bit relaxed. But on the other hand, we also realized that if people are asking for this, is because it's maybe an interesting stuff to put our attention. Most importantly, because as IT centers or businesses, we need to understand and grow and update with the users or with the customers, because it evolves so fast that we don't want to become obsolete. So we really need to hear what they want and where they are evolving towards in order to move with them. So we started just wondering, is this quantum computing really like the thing we need to move towards? So let me just share with you, this is an old plot, but it's still like quite representative of, let's say, the fields that use our HPC center. And what I can tell you is that this a big chunk or a big portion of the pool is users that use the HPC cluster for chemistry and material science simulations. And another big pool of users, so let's say some earth science, climate, astronomy, bioscience, those are fields that are more and more using machine learning tools to solve their problems. So we really, if we want to stay relevant for our users and support our users, we really need to understand where these two fields are moving. And so suddenly quantum computing wasn't such a strange thing to learn and to try to invest in, because these two are in principle, let's say, the killer applications of quantum computers. In particularly, chemistry is really expected to be the application. Why is this? Because quantum systems are very difficult for a classical computer to simulate. The fact that the quantum systems have this uncertainty makes it very complex to simulate in a classical computer. as opposed to a quantum computer where the intrinsic quantum nature of the qubit makes it a very easy map. Well, easy, let's not claim that. So chemistry is really expected to be the killer application. And just as a little intermezzo, some of the problems that people are really expecting to solve with quantum computers are things like photovoltaics, solar cell materials, nitrogen fixation, high temperature superconductor. And even though quantum computers do not solve any other problem, if they manage to solve these problems, that's already a game changer worldwide, because they have a really big impact in today's world. So anyway, we decided, okay, we have a lot of users that might move into the quantum computing technology eventually. So let's try to understand a bit more. So our question was, what is the role of an HPC in the quantum era? Because it wasn't really clear to us, right? So we just dig in this a little bit by doing, by asking, by researching. And we came with the following. I apologize for this thing at the top. I don't know how to remove it. But we basically came with the following. Let's try to understand our role, let's say, today, when we have only small quantum computers, our role, let's say, when we have 1,000 qubits, and our role when we have 1,000,000 qubits. And you can see that I was very smart not to put times, because, well, we don't really know when this is happening. There are, of course, already some roadmaps from IBM and Google, but let's not put time. Not putting time is a bit safer. But anyway, today, what is our role here? Or what is the role, let's say, of quantum computing versus classical computer? So quantum computing nowadays is not used really to show quantum advantage, because there's still too little the systems. But what we are doing when we use quantum computers is we are trying to understand and characterize the hardware. So really see how the algorithms work, how reliable it is, how do they perform, how do they scale, etc. Classical computers, on the other hand, in this scenario, they're used mostly for emulation. And this is important because this can help for a simulation-driven co-design. So we can really sort of use these emulators to debug our algorithms and to develop and test further. The other thing what classical computers are still used for is what is called quantum compilation. I'm not going to go into the details of that, but it's basically preparing the circuit for the quantum computer to take it. So then this is more or less here, right? So we need a classical computer for emulation, and in particular, we need an HPC the moment we pass a certain amount of qubits, because we have a memory issue. So beyond, let's say, 25 qubits, that doesn't fit in your laptop. So you really need something with much more memory. So then we ask, okay, in the future, let's say we have 1,000 qubits. Well, then we are assuming that quantum computers maybe are able to already show quantum advantage by performing, for example, hybrid algorithms. So we might be able to already offload some classical tasks. So that's what quantum computers will be for, together with everything that they were used before. And classical computers will most likely still be important, for example, for pre and post processing of data. So really to prepare the state, to analyze the outputs, to do the quantum error correction, and so forth. And then the question was, okay, and what happens then when we really have like fault-tolerant computers, hopefully? And so then, you know, what is quantum computing going to be for? Again, we're going to be offloading tasks for fault-tolerant algorithms, and the classical computers are still going to be used for all the above, but maybe also they will help to accelerate in some way the quantum circuit. So maybe in this case, the classical computers will become the coprocessor. So basically there are like, there are like three main scenarios that we see how quantum computing is going to be, like how HPC and quantum computing are going to interact. The first one is that they're going to, it's going to be for quantum accelerated classical computers. So when we offload some tasks that are classically difficult into a quantum processor. The second way that we see it is that there are going to be classical accelerated quantum computing. So this is the use of classical resources to accelerate the execution of quantum circuits. This is, for example, the approach that a startup called EPIC has taken, where they take the circuit and they propose it should be subdivided in circuits, and then those parts of the circuit can be executed either in a quantum computer or in an HPC simulator, emulator, because maybe that could give some advantage. For example, if you have very sparse circuits or Clifford-based circuits, this could be a way to go. And then the third scenario we see is that classical computers will be used for supported quantum simulation. So really use classical computing for pre and post processing of data beyond state preparation, beyond quantum error correction, which we can consider part of an algorithm. And in all these scenarios, what you can see is we're always talking about this sort of feedback between classical and quantum computers, right? It's always this hybrid computing that comes into play. So then the next question is really, okay, these are two hybrid things. We have really two completely different technologies. How are they going to interact? So this is something that we came up. It's by no means official, but we thought, okay, let's try to understand how they will interact. So we thought these hybrid workflows are going to be either local HPC, local QPU, HPC, QPU. Now, what does this mean? This is basically where you're going to execute the classical part, where you're going to execute the quantum part. And here, local, we refer to anything that fits, let's say, in your laptop. So I'm just going to claim smaller than 20 qubits, depends a lot on your laptop. An important thing is that every quantum or every hybrid workflow, every quantum execution will always have a bit of a classical, a bit of a quantum part, and it will always fall in one of these scenarios. And what is important about these scenarios is that depending on how they are coupled, it says a lot of how you need to orchestrate or how you need to manage this communication, right? Like it's not the same if you have local, where everything is happening in your computer. So you have the classical part in your computer, the simulation in your computer, and then you basically know all the resources very easily. It's easy to orchestrate. It's not the same to do that to use something, for example, like a local HPC or local QPU, where you really need to figure out how to share the information about the resources available in the different places. In particular, keep in mind that for the quantum computers, it's not yet clear how we will couple this, right? I mean, of course, it would be nice to have our quantum computer in the HPC centers, but this is there has a lot of issues as well. So most likely this will maybe be like a cloud-based service. So you can imagine that the way that the classical and the quantum part are coupled really will change a lot how we have to execute these workflows. And just to mention it, I'm not saying any of this is exclusive of each other. In fact, we should have codes that are portable through this whole sort of workflow, because the way they are displayed, it's also a bit like the developing cycle, right? So you start with a small experiment in your computer, then maybe you want to increase the number of qubits, so you use an HPC, then maybe you want to test how does it work with an actual quantum computer, so then you move to the next one, then maybe you want to test several different parameters, and then you move to an HPC, and so forth, right? So we want codes and we want orchestrations that are sort of portable through the different scenarios. So with all this knowledge in mind, this is what we had learned about quantum computing, among other things. We thought, okay, what do we need to do then? How do we help our community to jump into quantum computer? And then we came up with a couple of ideas. We decided that we needed to support the access to emulators and simulators, as well as classical quantum computers, We would need to support the integration, so really this orchestration and how do you integrate the quantum and classical ecosystems. Stimulate the development of quantum applications, because this is still missing a lot, and this can help us a lot figure out how to integrate things. We wanted to support, obviously, also the development of tools and everything that is needed to transform classical applications into quantum applications. And in general, we just want to help our community and our users to take advantage of quantum computing. So some activities that we took in order to do so, we bought some high memory nodes. This is important for quantum simulation, because you very fast reach problems in memory. We also gave access to emulators, access to some QPUs. We had the QLM Atos for a while. I'll go back to that in a second. We started close collaborations with a couple of QPU developers to really study, like, how do you access, how do you schedule, how do you do a standardization with different platforms. Then we also started doing, for example, working with universities, because we do not claim to be the most knowledgeable place in quantum computing. This is in the research centers and universities, but it's important to interact with them to really gain knowledge from them and share our knowledge from HPC with them. So yeah, we participated in a lot of different activities. As shown here, some worked, some did not, and let me just say a bit why. So the QLM Atos, we had it for a while. We still have it actually at SURF, but we never really had enough users. So we had maybe of the order of 3-4 users, and that for us was very difficult because obviously it requires maintenance, and it wasn't easy to justify doing all this just for 3 or 4 users. So at some point we decided we needed to let this go. This was before my QLM, which for those of you who do not know, my QLM allows to use different languages. Before that, you really had to use the Atos sort of like programming language. So that made it very difficult. But what we did instead is we bought these high memory nodes, right? A bit to sort of compensate for the loss of the QLM machine. The second part that also didn't work out very well is to offer sort of standard HPC access. Most of us are used to maybe connect the terminal SSH, but actually the quantum computing community, they are not that familiar with HPC centers, and they also don't want to go through the trouble of understanding. So what worked out very good for us was to create a Jupyter hub where they could really just work the way they were used to, but then the Jupyter hub was connected to the nodes, these high memory nodes. So they really liked that, and that was actually very successful. Some other things that didn't work for us, we created a Singularity container with a lot of emulators and other packages that we thought were useful. The problem with that is that in quantum computing, again, there's still too much development going on. And the problem with the Singularity container is that you have it sort of isolated, so you cannot really play with it too much. So people were not that happy with it, but what they did appreciate was the usage of easy build installations. I don't know, I'm not going to go into the details of that, but it's basically optimized installations of specific software or specific simulators. And then we had a couple of other good things that work out from the beginning, like internships, collaborations with quantum providers, financial support for use cases. I will showcase that in a second. And we're currently basically working on how to give access to actual QPUs, and we hope that this is successful. So let me just mention a bit about this financial support for use cases. So what we did, we wanted to learn quantum, and we wanted to have use cases. And well, the researchers, they always want to have funding. So we thought, okay, let's try to figure out if we can do a win-win situation. So what we did is we worked together with Leiden University, the FU and the University of Amsterdam, and we came up with a proposal to work in quantum chemistry algorithms. So the deal was basically we would give HPC resources and support. We would give my time to some extent, and we would also finance a postdoc for a year. And so we did this. The idea was really to support the development of algorithms in quantum chemistry, and it was pretty successful. So what we did is four things. We were working in interfaces to classical software using OpenFermion. We were working in improving the classical optimization, the ANSATS optimization, and the fourth step of the proposal, of course, was how do we disseminate this knowledge to really justify doing this investment. I don't have all the results yet, but there was definitely one paper that came out of that, which is reinforcement learning for optimization of variational quantum circuit architectures. And overall, it was a really great experience. We learned a lot, they learned a lot, and we're still collaborating further on these projects. And in the same line, we actually, because it was so successful, we started 2 more projects in these lines. So one is ray tracing for atmospheric simulation. So again, we're working with quantum algorithm experts, with the providers of the problem, and with us, and all together we're trying to figure out how to tackle this. The second one we have is about pattern recognition and ray tracing in high energy physics. This is together with 2 universities here in the Netherlands and CERN. And beyond that, we have also our own sort of internal projects, which are tackled by our employees, but also by interns and master students and so on. And yeah, we're just trying to learn as much as possible, get as much knowledge as possible. And in general, we try to also create Jupyter notebooks that are accessible for the public. I would add here the link, but I'm still working on it. So if you jump in the surf link, maybe in a couple of months, you will get a lot of notebooks for different projects that we have worked on. So just to finalize and keep this on time, I think as HPCs, we need to get ready for quantum. We need to understand our users. We need to understand that some users might benefit from this, and therefore we should be able to at least give some level of support. There are some simple initiatives that we can start to learn as HPCs, but also to stimulate and support our users. And I think it's important to also acknowledge that it doesn't matter even if it's now or when actual quantum computers are fault tolerant. Quantum computers will always be hybrid to some extent because you always need the support to some extent of the classical computers. So I think it's very important to focus in how to enable this communication between the different devices to really get the best possible performance. And with that, I would like to finish, and I hope I'm on time. And I'm open for questions, obviously.
Yes, you're more than on time, Ariana. Thank you. Thanks
Well,
a lot.
it's always good, right? I mean, normally.
Yes, no. Always good. And let's wait for some question. And I want to remember that everybody can also ask questions, so simply raising their hands. Oh, we have a question. So it says, can you give us more details on the RLL approach, the restricted learning approach?
Yes and no. I mean, I'm not the big expert on this. Yeah, I'll try to answer I saw the two questions in the chat.
Okay.
So I would like to refer you to the paper. I can paste the link in a second in the chat. But the main idea is really how to create the ansatz instead of trying to use the hardware-based ansatz or a hardware-fog-based ansatz, like really create it by exploring the space of ansatz using reinforcement learning with certain. So the main idea is to really how do we create smaller circuits, because the problem with ansatz is normally is that they create really long circuits. So this is something you want to minimize, but I can put I'm not a machine learning expert, to be honest, so I'm not going to attempt to explain the methodology. But yeah, it's quite nice, good results. I'll share the paper in a second.
Thank you. I'm interested too.
Yeah. So the second one, is there an open source repository for projects in ray tracing? This is a project we're starting actually now in 2022. As soon as we have a repository, I'm happy to share it. I mean, we work open source in general. We have a couple of ideas, obviously, on how to do ray tracing, and there are a couple of papers also there, about ray tracing, treating the problem either as a sampling problem or as a just linear algebra problem. Depends how you want to see it. But we haven't started the coding, let's say. But yeah, if you keep an eye for the SURF website, we probably will put a link as soon as possible. But we are pretty excited about that project. We think it's, we have already worked in ray tracing with the Wageningen University using machine learning. So the idea now is really like, how can we now extrapolate this into something else? See if we can do something.
Very good. Let's see if there's something also here in YouTube. No, YouTube, we have no question here, but okay, I want to ask you a question. Okay, we have
was Python used for those chemistry applications on Atlas machine?
For hybrid application.
What do you mean? So the chemistry project was mostly written using Open Fermion and Circ, I think. So that's related with the QC4QC. So this project we had with Leiden. They didn't use the QLM as far as I'm aware. So that's part of our problem that, I mean, maybe other HPCs have had a different experience, but we just never got enough users. Having said that, nowadays with the Atlas machine, using my QLM, maybe some other people can comment on that, you can really program in different languages, right? So you really can do Qiskit or Circ or different backends. So that has helped a lot to get more people interested. Because the problem is that before it really needed to be the QLM language. And so, you know, convincing the researchers to use that was a bit problematic. And I see Luigi has a question. So
yes, so since I can connect, I didn't want to jump without raising my hand. Well, very nice talk, first of all. I've seen many similarities with the same questions that we have also, which I'm going to discuss in the next talk as well. it's not really a question, maybe just of comments, a couple of comments on the things that you discussed. For the QLM, we could see as well a sort of a slow start with the users. Now I have to say we get to a regime where we have, I would say, a total of 20 users and maybe half of them running on the machine or a bit less, but with some constant rates. So now it seems like we got a critical mass, but I can see, as you do, some peculiarity in the way the typical users approach the HPC environment. So researchers in quantum computing are more used to work with Jupyter notebooks than with typical SSH, and this poses a challenge also because this is not typical to be done on a HPC center. And I see more or less you showed the same thing. We were also thinking in terms of containers, for example, for making the deployment easier for such users that have less exposure to an HPC ecosystem. And yeah, so I could see many similarities, as I said, with things that we have worked on.
Yeah, I think in general it's a bit of trying and seeing what works, right? I mean, as you mentioned, it's difficult. The quantum computing community has not been yet an HPC community, right? So it's just recently that they're starting to jump into the HPC, and they don't want to add, or let's put it differently, we want to make it as barrierless as possible, their integration to HPC, right? So yeah, sometimes that means using your Python notebooks in an HPC, which if you are from an HPC background, you will frown upon, right? Seems like the wrong usage of it. So there are a lot of different issues that we have encountered where we thought this is a great idea, and then it didn't work. Another thing we tried at some point, so a lot of the codes that the quantum computing users were bringing were Python written and very inefficient. I mean, already the emulators tend to be quite inefficient in some ways, and then the codes were very inefficient. So we thought, okay, let's then create some sort of a profiling tool, so at least they can use that. So, you know, you just constantly try to think, what can we give them? What tools do they need? But it's very difficult to try to guess and see what works and what doesn't work. And I think as HPCs, it would be really nice to try to exchange this information, right? Like what worked for you? What was your strategy? How did you communicate it with the people? Because for me, another thing that has been difficult, interested in your experience, is convincing the quantum computing community that they need HPC. I mean, it's not that I want to force it, but it's a bit, you always get the answer, I can run everything in my computer. And then you're like, yeah, up to a certain point, and eventually this will be an issue, so why not start, let's say, the onboarding now? But this is something that I'm always interested to hear, like how have different people tackled, because I don't think it's that straightforward. So yeah, I'm glad that we all experience, I mean, I'm glad to hear that you also have these problems.
Yeah, well, you mentioned another one that I'm aware of, the fact that there might be software that we can make available for the community. We can make available, I would say, on our login interface to the HPC system, but this software itself, most of the time, is not really HPC ready. Yeah. So we have this friction of, yeah, we want to make something available, but what we give is not something that can be run efficiently on our systems.
Yeah, I don't know you, but I get a little bit of a heart issue whenever I see one node of 40 cores with one core in usage and then full RAM completely. I mean, as an HPC background, sort of, it's painful. It's very painful.
Yes, I agree.
Yeah.
No, you're totally right. Thank you, Ariana. Thank you, Luigi, for your intervention. It was very interesting. So
yes.
Thanks for the invitation, and I
thank you for being
here. Pass the floor just to be on time.
Yes, you know, perfect timing. So let me introduce
now, unfortunately, I hear my daughter out of the door without keys. So if you allow me 30 seconds, and I will be back for giving my talk.
Not a problem. Not a problem at all. Thank you, Luigi. Okay, maybe in this time, yes, no. You know, it's a real problem to convince quantum computing users that the HPC is really useful in this area. But maybe when we will have the first quantum advantages using hybrid algorithms with HPC, they will see it. But I'm looking right now. I'm seeing that time is passing as going, but people is understanding this particular thing.
Yeah, and I also think that the moment they start using it, they really are like, "Oh, this is great. Why haven't we used it before?" Right? So that's also pretty funny. But yeah, I give you the floor. Sorry.
No, not a problem, Ariana. Not a problem at all. Thank you a lot. See you.
Yes, I will try to share my screen now.
Yes, let me introduce you. Just a moment. So our next speaker is Dr. Luigi Iapichino. It is the lead of quantum computing at Leibniz Supercomputing Center. Thank you for being here, Luigi, and the floor is yours.
Thank you. Just trying to share my screen right now. Okay, so where is it? Okay. So now you should see this in full screen.
I'm not seeing anything right now.
Okay, then probably I have to try a different construct. Let me see with that.
Now I'm seeing your slides, not in full screen, but in normal mode, let's say.
Okay. Let me try just another time for the full screen because I think will be beneficial, but otherwise yes, we will go as we are able to do that. So maybe last up 10.
If it's not working, try to put full screen when you are in normal mode, but you're sharing.
Exactly.
Just an idea.
Yeah. Okay, now let's try now.
Perfect.
Oh, wow.
Thank you, Luigi.
This is good.
Thanks a lot.
Very nice. So
give you the floor.
Perfect. So thanks for the kind invitation today. I'm happy to be here, and if I'm lucky, I will also be able to change from the first slide. My goodness, what happened now? Okay, now. Okay, so my name is Luigi Iapichino. I'm the team leader of quantum computing at the Leibniz Supercomputing Center and the co-founder of the Bavarian Quantum Computing Exchange, which I will talk about in a few minutes. And today I wanted to discuss with you how quantum computing can be approached from the viewpoint of high-performance computing and how this can be important for HPC centers. We already had a talk in this direction with the previous talk. I've seen that the whole session goes around this topic, and I would like to share how we are going in this direction at the Leibniz Supercomputing Center with the so-called Quantum Integration Center. So just to introduce the topic, I will make a very short introduction of LRZ, what we are doing, what is our mission, and why. So just trying to motivate why quantum computing in an HPC center. What are the directions of our strategy in this field? And in particular, I will focus on the integration between HPC and QC. And I will give a brief overview on the current projects that we have in the Quantum Integration Center. So talking about the Leibniz Supercomputing Center, this was founded nearly 60 years ago. So next year we will celebrate 60 years of support to the scientific environment in Munich, where it was born, then in the state of Bavaria, and to higher levels. So we are one of the 3 national supercomputing centers in Germany, and we are part of the European infrastructure. We are part of the Bavarian Academy of Sciences and Humanities, to be, say, at the same distance from the two big Munich universities. And of course, at all these levels, what is relevant here are the services that we offer in the HPC space. In particular, our top system is SuperMOOC-NG, which in the latest top 500 is number 23. So it's a system which is more than 2 years old, with more than 300,000 Skylake cores and Limpak performance close to 20 petaflops. Now the question is, having a system like this, or having one of the successor systems of SuperMOOC-NG, why it's interesting to understand how we can relate such systems with the quantum system. So this is a question that before being addressed about quantum computing was already taken for other fields that emerged in the community in recent years. So we know that HPC is based on modeling and simulations, discretizing and basically coding into equation what we can observe in the natural world, writing these into algorithms for computing them, getting some data out to analyze. This paradigm of getting knowledge is complemented by other paradigms like AI machine learning, where we learn from data, big data, the same. So there are different paradigms with the same outcome, which is gaining knowledge. And we see in this innovation circle that also quantum computing can perform a role. It's very important for us to state, and this has been done already several times today, I assume, quantum computing is not an alternative to HPC, but there are specific cases where an integration can be very favorable for both fields to advance. In particular, as we see HPC systems moving towards the sustained exascale performance, we need new ways of gaining performance without hinting the energy floor, and quantum computing could be, in specific problems, one of them. So quantum computing has attracted lots of interest in the research community, and we know has attracted also lots of interest in the funding agencies. In March this year, we could open at the Leibniz Supercomputing Center our Quantum Integration Center. So here is the inauguration with the Minister President of the State of Bavaria, together with the Minister for Research and our Director. This was an endpoint of, and the starting point, of course, of an effort which is ongoing in our center in this direction. And we would like to understand why quantum is important for our approach. And we see this starting from our main role. So as an HPC center, we are a user facility and a service provider for research. So our role is to provide access to quantum resources, to consult the researchers and support them, and to support also with education and training, as we do already in HPC in many areas of this discipline. We have a supercomputing center, so for us is a natural outcome to host quantum hardware at some point, to understand how this can be related to HPC hardware and how we can educate the next generation of technologists to operate quantum hardware. And as part of our user community, we want to create awareness on this technology through tech scouting. We want to understand what are the requirements of our community, and we want to support its networking. In 2020, we created the strategic plan to try to summarize all these viewpoints, and the Quantum Integration Center is the tool that can address these needs, which are highlighted in our strategic plan. Our strategy in quantum computing is organized into 4 main directions. The common trait of these directions is to do research on these topics. So our final goal, of course, is to create services in quantum computing for our users. But these services, of course, they are something so modern that they should grow together with applied research in this area. Going through these 4 strategic directions. So the first one is having on-premise quantum systems. There are research and development projects that I will discuss, the DAC project, the QEXA project, and our involvement in hosting system in the framework of the Munich Quantum Valley, which is a very rich funding framework in the Munich area. Second direction is how to combine high-performance computing and quantum. So high-performance quantum computing is how we call this. In this direction, I will show our Atos QLM and also the software simulators that we can make available on our HPC systems. Another direction is to provide practical services in quantum computing. And this, on the one side, means which kind of software, for example, is necessary to our users, as we have just discussed before the talk, but also how our users can access quantum hardware remotely. So as a matter of fact, we know that all commercial solutions which are available for quantum hardware, they are not on the premise of HPC centers, they are in the labs of our vendors, of our partners, and the question is how to make them available to our community and how to understand, and this was also mentioned before, how to make the workflow of our users optimized to work in an HPC environment. And the last direction, of course, is about the user community and the education. In this direction, I will briefly mention the Bavarian Quantum Computing Exchange as a platform for networking for our community. As I said, the main focus that we have that basically unifies these 4 directions is the research field of HPC-QC integration. We want to understand how quantum computing can be integrated on HPC as we move towards exascale. To which extent QPUs can be seen as a new class of accelerators. And of course, this is a challenge under many viewpoints, from the hardware side, but also from the software stack side and for the programming models. We try to streamline our current efforts in quantum in this direction, and we try to understand how our HPC environment can develop synergies with our quantum projects just to go into this direction of integration. Then now I will go, as I said, through these 4 main directions. For the first one, I will describe some of our running projects. We have a number of projects funded either at the federal ministry level in Germany or at the level of the state of Bavaria. The ones that I can mention here, they are, I think, 3 to 4 where we are involved. There are other ones in the pipeline. As I said, this field is very dynamic at the moment. There is lots of momentum also from the viewpoint of the funding agencies. And it's just important to have these efforts somewhat streamlined so that it goes to a specific point. So the first project that I would like to talk about is the DAC project. DAC stands for Digital Analog Quantum Computers. And this is aimed, so this is funded by the Federal Ministry of Research and Education in Germany, and is aimed to the development of different generations of quantum systems out to 54 qubits with a technology that potentially can be scalable up to order of 1,000, and how to integrate these systems into an HPC environment. The partners of this project are listed into the left-hand side of my slide. I can just mention that because of this project, we finalized the procurement of a cryostat on our premise, and we are setting up a lab space for hosting a test system on our HPC center. This is the first of a number of other systems that we aim to host in the near future. And of course, we know that at the moment this kind of hardware is a research object rather than a research tool itself. So in the first phase of the project, at least this will be operated just for the project partners. But of course, the long-term goal for this project and the other ones that will come will be to make this possibly available to early users. Yeah, in the framework of the DAC project, and this is a slide courtesy by a colleague working in my team in this project, there are a number of questions and the challenges about the integration. I would say this slide is just a list of such questions, and I think that also after listening to the previous talk, we are reasoning about the same question in the community, and now that the point is how we can address this in the best, the most useful way. For the hardware, we all know the limiting factors right now are that we have few qubits, that the decoherence time are really short, that we have no solutions for long-term storage. And this is something very, very limiting at the moment, but also on the application level, we still see some big limitations. Basically, having a demonstrator of a problem that can be from HPC offloaded to quantum, this is something still quite demanding. The software stack still is widely missing, and there is still some work to be done on the side of the algorithms to understand what are the ones most promising for doing this kind of work, and what can be exactly be run on the HPC side, what on the quantum side, how to develop these hybrid workflows. And also the rest of the software stacks, all middleware, this is still at a very rudimentary level. So the only basically abstraction which is accepted from the community is the one available as quantum circuits. We still have no real clue about how the future architectures would look like, how to make these abstractions, and these are all three fields of work in the field of integration. Second project that I would like to just have a quick overview for you is the quantum computer extension for exascale HPC, in short QEXA. So this is a co-design and cooperation project funded by the German Federal Ministry, together with IQM Germany, which is a vendor of superconducting qubits, Atos, and HQS Quantum Simulations, which is a startup specialized in software for quantum computers. The main goal of this project is to provide to LRZ the integration of a demonstrator of 20 qubits together with an emulator and a software framework, and to have these three items integrated within HPC environment and also the HPC infrastructure, and try to work on all these items in a co-design fashion and in cooperation to bring all these three elements forward together. And yeah, here, of course, the the viewpoint of advancing the hardware together with the software and to see how a simulator, an emulator can work on the same field. It's something that is very promising on the way to understand how this technology can be useful for the next generation of systems. So in the direction of practical quantum computing services, this slide, I will not go through all details. The only goal here is to demonstrate that right now, in terms of programming languages, platforms, libraries, the environment in quantum computing is very rich and very diverse, probably even richer than it is in HPC to some extent. And it's important for us an HPC center to understand which kind of tools, which frameworks are the ones which are necessary to our user community to work in this field, and also which hardware they need to access. So the second goal, of course, is also which system we want to provide access to remotely. In the framework of the Munich Quantum Valley, we got very generous funding from the state of Bavaria until 2025. The Munich Quantum Valley, as I said, is an alliance between the Bavaria Academy of Science and Humanities, the Fraunhofer Society, the Max Planck Society, and the two largest universities of Munich to develop Munich as a center for quantum science and technology. So the scope is even larger than quantum computing alone. If we just look at the efforts in quantum computing, we can see that the whole way from the hardware to the applications can be structured in such a way that one can identify several items to work on. And the strategy of the Munich Quantum Valley was to identify consortia working on specific parts of this whole stack. In particular, LRZ will coordinate the consortium called K5, which is based on the programming layer at the interface between the quantum hardware and HPC. So this consortium is called Quantum Development Environment System Software and Integration, in short QDESI. And this is at the interface between quantum and HPC, and to develop the ecosystem and integrate what we develop within the HPC ecosystem. The main goals of this program is to work on compile-level tools, multi-user environment, resource management, to interface with the platform that exists with HPC system as an accelerator, and to work in main focus areas, which is the programming environment, the operating system, microarchitecture, firmware, and how this can be integrated also with cloud systems, not only with HPC. Then in the third direction, we have the so-called high-performance quantum computing. We know if we want to work on algorithms in quantum computing, the quantum hardware is very experimental. So the simulation is an invaluable asset for researchers to prepare their codes, to test them. And this is for, in terms of algorithmic complexity and memory footprint, a challenge for HPC systems. So we have three main categories. So the hardware simulators, which are special purpose hardware for running quantum algorithms. Atos Quantum Learning Machine is an example. Software simulators, so applications which are HPC ready for running such quantum algorithms. The Intel Quantum Simulator is an example, and software emulators. For the software simulators, as I said, Intel IQS is a simulator developed by Intel. We have a strong collaboration with Intel on this field. The method paper of IQS has been done with test run on SuperMOCA-NG, we could see very good scaling on our system up to 42 qubits, where 1/3 of the machine was used. Without going into the detail of the figure on the right-hand side, you can see that basically all these curves nearly overlap each other, which means in this case that we have very good scaling. Our aim here is to work on the optimization and development of this software, as we have done in a project with Intel already. We had some tutorials before the pandemics. We aim to have other activities on this field as soon as this will be possible, and to make some works not only on the simulator but in other items of the software stack that Intel is developing in this field. And in terms of hardware simulator, the Atom's QLM. Now, we had a QLM38, which is pictured on the right-hand side of the slide. We had these installed in early 2021. Right now, we are still in test user operation because we are doing the last settings for making the system generally available to our users, hopefully in early 2022. Then this will be the first official LRZ service in the field of quantum computing. As I said, we have a number of stable users on the machine that use them for research projects. And most of all, we are developing synergies with other parts of our HPC environment where the QLM is involved. Sorry, I think I'm missing a slide here. Yeah, well, what I'm missing was on the Bavarian Quantum Computing Exchange, but this I can tell you anyway. This monthly forum that we set up in July 2019 to make the local community have a platform for discussion. The community involves people from HPC centers, researchers of the academia at all levels, vendors, startups. We have talks, we have focus groups, we make technology awareness here. And this whole effort goes in the direction of community alignment. So as an HPC center, you know, our role on the one side is try to anticipate what the technology direction can be and to follow what our users would require. So we are in a sort of feedback cycle where we go in both directions, and we try to connect in this way to our users and to identify together with them which kind of funding opportunities we can have to work together. And with that, I will go to my summary. So quantum computing is a very interesting research field, also from an HPC perspective, among many others. The systems that we have now, the hardware, are still research objects, and they are very challenging to be operated in a data center. However, we see that the first service in this area start being offered and start being requested by the user community, most of all. And to address this, we see that the integration of HPC and quantum is a big milestone to be reached in the next year. And the open question is, what can be done to make the experience of our users even better in this field? And yeah, with that, I leave just here my contact and I open for questions. Thank you.
Thank you, Luigi. It was a very, very good talk. Yes, I can say I am a little bit envying you for all the projects that Germany is funding, but they are very interesting. I'm happy that somebody has this opportunity to go deeper in these fields. So we have some questions, and one is from a colleague, Fabio Finito. Maybe you know him. And he's saying, he say that I think it's very intriguing the idea of co-designing for quantum computing. So Luigi, do you have already in mind on what kind of application / use cases your co-design will be based?
Well, maybe if I can try to stop sharing so that you can see me while I reply. Well, which kind of applications? The applications are probably the same which are most interesting for our users at the moment. In that specific case, the co-design will be based most likely on the software which is made available also from our project partners in this case, and the main use case of that software, I think it's in the field of computational chemistry and materials. So this is probably the first family of applications that we would address. But of course, anything else depends mostly on the request from the side of the users. But we know that this family of application is very promising for quantum applications.
Thank you, Luigi. We have a question from the audience. Rupesh, you can unmute yourself and you can speak.
Luigi, great talk. But my question is around the user community. Who are the users that you speak of? Are they mainly academic, mainly industry, the ones who are specifically asking about quantum computing?
Yeah, this is a good question. The mandate of the Leibniz Supercomputing Center is to collaborate with academic partners, with academic users. This is the mandate that we received from our funding agency, but however, there are projects where we think to partner also with subjects from industry. In particular, we have a funded project with the Fraunhofer Society that in Germany is providing this link between the academic research and the industrial application. And since we are collaborating with them, somewhat we will be also in the direction of providing support also to industrial applications. This is a field where I can see lots of interest from industry. So just from the very first talks we had at the LabSet before the pandemics, we had a number of attendees from industry, which was much, much larger than similar courses given in the HPC space. So there is already the indication that there is lots of attention in that field from the industry.
Okay, very good, Luigi. Thanks a lot. And then I think that it's time to move for our next talk. Thanks again, Luigi, for your very interesting speech. Our next speaker is Dr. Artur Garcia, that is the lead of quantum computing at that is recognized quantum computing researcher at Barcelona Supercomputing Center. Thank you, Artur. Sorry. And I leave you the floor. Thank you, Pioneer. I can't hear you. Is there a problem with your mic? Because I see you unmuted. Ah. Okay, let's wait a couple of minutes. We hope that this problem will. Now I see Artur unmuted, but I can't hear. I can't hear you. You have not another microphone, something else?
Maybe we can arrange a connection by telephone. You can call the dial-in
or by telephone, or yes, maybe.
Yeah, if the microphone is not working, you may call the number, and Daniele will enable you.
We can try. I have another user logging in with my laptop.
Can you hear me now?
Yes, now
okay.
We can. Fantastic.
I switched computer actually, so that's the easiest way to solve problems.
Well,
okay, now
a very good
let me
way.
try to share my screen. Sorry.
Mm-hmm. Very good. Perfect.
Okay. Finally.
Thank you, Artur.
Okay.
The floor is yours.
Thank you. Thanks a lot. So I'm Artur Garcia from the Barcelona Supercomputing Center. And I'll be discussing mostly about this ROSNet code, this library for quantum simulation on a supercomputer. But I'd like to use it as an excuse to discuss mostly the general topic of the relation between a supercomputing center and quantum computing. And this is, I think it's an interesting topic because, and it has been mentioned before that actually supercomputing centers have been in charge of justifying why do we need more powerful computers and which application need this actually new supercomputers in the exascale, for instance. And I see that it's a very similar problem to finding applications for these emerging quantum devices. So actually, it's the starting point of our research, where we were discussing, okay, we may not have like a really powerful quantum computers today. They are noisy. They are of not like a small size, but still there's a lot of interaction that may be interesting. And our solution to this interaction has been developing our own library for simulating quantum circuits, which is this ROSNet code that has some particularities. I will be not discussing in detail. We can discuss it later. But the general topic will be how to approximate the difficult problem of simulating a quantum circuit. Okay. So first, a small introduction about the techniques we will be using, and also these underlying problems. And the idea here is that the Hilbert space where quantum states are living is huge. It's exponentially large. So that means that we have to keep some exponentially large information related to the size of the problem that we want to simulate. And this is something that if we want to fully exploit quantum properties of a quantum circuit or for a quantum device, we have to take charge of, and that's a big problem because there is no shortcut to this fundamental representation of quantum mechanics. So the idea is that, okay, then why do we develop quantum simulators if they have some kind of limited lifetime? And once we get around 50 or 60 qubits, most of these simulations will no longer be possible even with exascale devices. And the idea is that actually we can compare simulations with the results of real quantum devices. And this is actually really helpful because we have fundamental limitations to accessing the information on a quantum device because of the measurement problem in quantum mechanics. So we gain a lot of insight of what happens in a real quantum processor. And I think that's also very interesting by itself. But also we can test new algorithms before we have proper devices, reliable and with really huge depth of these quantum circuits that I'm depicting here. We can test these algorithms beforehand. And actually using these simulations, we have discovered that some proposals for algorithms, once we stress this simulation to large sizes, start having problems that we couldn't see on small simulators of the order of 10 to 20 qubits. And then also what I mentioned here by optimal strategies, I mean mostly addressing the problem of quantum control. So we may have this device that we simulate on the supercomputer, and then we can simulate some quantum noise as well. And then we can devise some auxiliary agent or system that will be controlling and trying to reduce this quantum noise. And this can be simulated in this paradigm of a dual simulator and also a control system. So the underlying technique that we are going to present for our simulator is the tensor network picture. And the idea is that there is a close connection between tensor networks, which is a mathematical technology in order to simulate or operate over objects that are tensors, which are somehow similar to matrices. And so the idea is that we transform quantum circuits as tensor networks, which is very convenient once we think that these simulations will be run on a supercomputer because they can be easily parallelized. So instead of addressing the full state vector of representing the computation, we will be actually dealing with these small tensors at the beginning, representing the state and the gates. And then afterwards, we will be combining these tensors in order to obtain the outcome of this quantum circuit. Whenever we go to the exact simulation of the quantum state, we see that actually there is an exponential growth on the memory that we need, which is also the case in the exact representation of tensor networks in the worst case, but with some interesting differences. For instance, we have to combine the size of the tensor of the circuit, both in the number of qubits and also the depth of the circuit. So sometimes we are able with tensor networks to simulate larger circuits in the number of qubits, but with less depth or shorter depth of the circuit, which for some applications may be interesting, especially when I was mentioning simulating real devices. These normally happen with a reduced number of gates, but may have a lot of qubits. So that's a particular application that may be interesting. And then the good thing is that we can perform some approximative techniques into these tensor networks representations in order to provide approximate solutions or approximate simulations. And we actually control the accuracy of these approximations, meaning that actually we can go to even larger systems as long as we relax the need to be very precise in the outcome. And there is an underlying physical motivation for that, which is interesting to discuss with physicists, which is as long as the state that represents this computation has not a large amount of entanglement among different parties, then this tensor network approximation is feasible, and it's quite good actually. And these techniques have been extensively used in other fields of quantum simulation, especially with low-dimensional systems at low temperatures. So I will not go into the details, but basically there is a very handy graphical representation of tensor networks based on these small circles that represent tensors of different indices that we depict as some kind of outgoing lines of each tensor. And we combine these tensors by joining these lines, which means they have some common index, which basically you can refer to like vector matrix product, for instance, and then you have some vector which has only one index, and a matrix tensor which has two indices. And then whenever you combine them together, is similar to performing some matrix vector operation, some matrix vector product, and then the outcome is a single vector, which is depicted like this. Okay, so this is the basic representation that is very handy in order to understand also the topology of this tensor network, which will be very important in order to assess how difficult some computations are. So the first step is just take the quantum circuit and then move to this tensor network representation, and that's a very trivial step. So there is no overhead in computation here, and so that's something that happens actually in a natural way because we can represent always these gates as matrices. Okay. So there is total equivalence among these two problems. And whenever we want to compute the outcome of the measurements of this quantum circuit, then we have to see what happens when we operate over this full tensor network and whenever we perform some contraction. So basically, the idea is that we transform this quantum circuit, I'm picking here the sycamore circuit, into this complex tensor network, and then, and then we will optimize the contraction path. And this is interesting. It's not the same to start contracting this tensor network and operating tensors among them in different regions, because intermediate representations can be large. And this is the major limitation of this approximation to the simulation problem. So we have to be very careful selecting this contraction path, and that's a very hard problem. So there is no free lunch here. I mean, we have to solve that problem in advance before starting even to contract the tensors by themselves. But this can be done actually exploiting parallel resources. So that's interesting from the point of view of a supercomputer. Always trying to minimize this intermediate representation. And then once we know this contraction path, then we perform the actual contraction of this tensor network, and then we can sample over a reduced subset of tensors at the end in order to obtain the outcome of this quantum circuit. So I'm summing up this part. Basically, there are some techniques that actually we need to develop in order to be able to store these tensors in memory of a multi-node system, because sometimes these tensors, these intermediate representations, will grow very large before getting the final set of tensors as the answer. And then we have to use some different techniques in order to be able to manage these tensors that will not fit into a single node. So I have to say that this approach has been exploited by different groups. So it's not that we are bringing this for the first time into the simulation of quantum circuits, but our approach is based on a particular parallelization technique based on tasks, which we think is very interesting, in a way to bring all these resources to a general set of users or developers that probably are not that interested in the internal workings of all these tensor network manipulations, but they are interested in running simulations in HPC systems. So basically, the methods that we are addressing, this family of techniques in order to manipulate the tensors are, I'll give you an example just to be really explicit. And what we call slicing is basically once we have set up some given tensor network, then we can eliminate some of the links of this tensor network, which is equivalent as reducing the memory requirements to represent and operate this tensor network. But as a trade-off, we need to perform this contraction or this operation over the tensor network in parallel with some time overhead. But the good thing is that this is totally parallel, so we actually forget about this link, and then we perform this reduced contraction of, many times, and then this can be done in parallel, and at the end we can just combine the results. So this is like a general approach that may allow you to reduce the cardinality of these tensors and thus reducing the memory requirements. So basically the picture will be, okay, we have these two tensors that we want to contract, meaning that the outcome should be a single tensor combining all the indices. And then we just remove this link, making this like a common index that is not explicitly represented in the tensor network. But as a trade-off, what we have to do is to operate this in parallel. All the possible combinations of these two tensors that will be equal to the operation represented before by this link disappears, and then we operate over these tensors. Okay, and the basic idea is that then we can have tensors that are arbitrarily large, and the only thing we have to do is to split them in blocks, and then all the operations related to the big tensors are actually done in these reduced tensors or these reduced blocks. And you can see, for instance, here we are contracting two tensors, and this should be the outcome. And then for each contribution on the outcome, there is a lot of like different combinations of these blocks that have to be done separately and can be done independently. That's the interesting thing to be done in a supercomputer. And then once we have all these blocks together, then the operations on the subblock level are combined together in order to bring each of the components of the final tensor. That can be also represented in a multi-node way. So that's also interesting. There is no requirement to have everything sitting on the same node. How do we do that? I mean, there are many different approaches. All these different blocks can be done, can be contracted sequentially, which has a lot of time overhead, but it's very efficient in terms of memory. There is some structure as a tree that may be very convenient if all these, if there is a lot of work to be done at the beginning, when there is a major level of parallelization. But actually, in many situations, the big cost of the contraction of the full tensor network happens at the end, when there is a lot of parallelization. So it's not surprising to see that actually this approach is not very efficient. What we discovered is that actually something called commutative reduction is very efficient. And I don't have to be very precise here, but the idea is that this approach has some benefits. In particular, we can compute each of these contractions in parallel, but the common composition of all these solutions will happen sequentially. Okay. So the idea is that we have this trade-off between how small these blocks have to be and bringing more parallelism, and also the overhead that we will have both splitting and joining these blocks computation. So there is some kind of middle spot where we know this approach will be very, very efficient. And also, actually, beyond this heuristic, there is another thing which might be interesting, that these block sizes can be related to some particular architecture that we will be using in order to perform this actual contraction of the tensors. Meaning that, for instance, if we have a lot of GPUs, we can just optimize this spot to be so that each of the block operations will fit into this GPU memory. Just like boosting a lot then the algebraic operations. Okay, so we program these over a library called PyComs that will take care of most of the parallelization demands of this approach. And basically, it's task-based, and it will distribute all these tasks in different nodes by itself. So the idea is that we are going to develop the code just with a sort of decorator that will tell when when there is a dependence on data as input and output of each of these functions, and then these PyComs will take charge of the full dependency graph all these tasks in terms of data, and also the parallelization will happen inside the runtime of PyComs, which is very convenient. Also because these PyComs has been developed mostly at the Barcelona Supercomputing Center, so actually next door we have the people developing this library, and this interaction has been very interesting for us while doing this ROSNet code. So just to finish, I'd like to show you some of the results that we have done for very large circuits, actually. So somehow naturally in the community, the sycamore circuit has become some kind of like a objective or very useful benchmark in order to try libraries. And we start checking our code with 53 qubits simulation of the sycamore, and the combined depth is of 12 levels or 16 levels. Let's say that the Google experiment is down to 20 levels, and there are simulations also using similar techniques at that level, but that will require like the largest supercomputers in the world today. And what we have been doing is mostly a scaling analysis of this approach in our system in Mare Nostrum 4, down to a few number of nodes. But already we were able to simulate the sycamore circuit down to quite a significant depth. And overall, the main interest was to check if these both sequential or commutative approaches were interesting and feasible with the memory requirements that we had for a particular given number of nodes. So using trace analysis, and this is also a nice feature of using PyComs, we have access to all this information of what is going on in the full supercomputers. We actually know that our current version of the ROSNet code is already let's say, efficiently distributing all this load into different nodes, into all the available nodes. And also the runtime that may be under stress in some situations, as you can see here, is actually can manage to distribute all these tasks and also to perform the actual contractions of the system. Where is all the computation time going? So basically, it's this tensor dot operation. So we basically are all the time contracting tensors, which is very similar to multiplying matrices. And these matrices can, in the worst case, grow exponentially large with the system size. So there is this fundamental limitation of the quantum simulation is already here in these operations, in this tensor dot. But nicely, we can see that actually there is some overhead, significant overhead, but not a lot of overhead on the way we manipulate the data using this PyComs library, basically converting the serializing and deserializing the objects into the disk space where we store all the information. So there is this is to complete this picture. We have to write and move data among different nodes, and that will take a lot of time. But it's done transparently for the user using these PyComs, and also it may happen while other nodes are actually performing contractions. And just some weak scalability analysis for given number of nodes and different increasing sizes of these matrix or these tensors objects, we actually see a nice efficiency along growing system sizes. You can see some drop in the performance here, but this actual point we've been studying it, and we know that the major problems were the bottleneck was actually on the runtime of this PyComs library, and that has already been solved, meaning that actually having this interaction with people developing the underlying libraries is also very interesting. What is not very clear here is that actually by using the commutative approach, while it may be slightly slower than the sequential, allows us to reach to larger experiments with the same amount of memory, which is interesting. There is some overhead by the sequential approach that doesn't have the commutative, allowing us to reach a larger system. And well, this is a very similar analysis, just changing the block sizes and for different number of nodes. Okay, so let me just jump to the conclusions. And the first part, I try to justify that actually it's very interesting to have a tensor network-based code on supercomputing centers in order to approximate or simulate quantum circuits. And while there is a lot of work being done on this optimal contraction ordering or suboptimal with using heuristics, this is already a hard problem, and it's very interesting by itself. But I've been addressing mostly the second part of the problem, which is once having this contraction ordering, how do we perform the contraction manipulating these tensors that can be really, really huge? And our solution for that is using this library we have developed at this supercomputing center in Barcelona, which is called ROSNet, and basically it's an out-of-core data allocation based using this PyComs runtime. Allows us for having like tracing and profiling, and that has been very useful in the development and the first experiments that we run on multi-node systems, and also the potential for using heterogeneous architectures, meaning that these final constructions can be performed in GPUs or different architectures actually. And the basic tool, and in order to manipulate these tensors, these very large tensors, and going beyond the limitation of a single node, is using these tensor slicing techniques that minimize the memory usage. So thank you for your attention, and I'm open for questions.
Thank you, Artur. Very interesting. Your emulator seems really interesting, and also the fact that I want to tell you that the fact that your strategy to parallelize the tensor slicing strategy is very clever. My congratulations. And is there any question for Artur? If not, I have a question, and I think that okay, I can say it. And you used ROSNet also for some simulation, okay? But I did not understand, maybe I missed it, but I don't know. Did not understand how many qubits did you manage to emulate with ROSNet, with some try that you did. That was I missing this information, or?
I mentioned for this particular experiment that we were showing that we were on the same setting as the Google experiment. So these are 53 qubits.
53, okay.
Yeah, but
with what level of approximation? Because what amount of RAM did you use for emulate 53 qubits with the tensor network method?
So the point here with tensor networks is actually the important thing is the combination of both the number of qubits and the depth of the circuit.
Yes.
Because if I have a very trivial circuit, I can simulate hundreds of qubits. Okay, and that's interesting for some situations. For instance, if you want to simulate low depth circuits. In our particular case, we were let's say halfway the full sycamore circuit of the supremacy experiment. So this is called number of cycles. The full experiment of Google was 20 cycles, which involved different quantum gates among neighbors. And in our case, we were between 12 and 16. But it was an exact simulation. So we were not assuming up to any truncation or any approximation. So the interesting thing, let me say, about these tensor network methods is that actually you have some level of tuning all these properties of your simulation, which may be very handy for different scenarios.
Very remarkable. Congratulations. Okay, and so okay, and so you said that you made an exact simulation for this experiment, but just to say, if you make some approximation, how much qubits that you can added qubits you can emulate for the same circuit?
That depends a lot on the properties of the quantum gates. And the hand-waving argument is that if these gates are really entangling gates or create a large amount of entanglement between any partition of the system, then my intermediate tensors are going to be very large.
Okay.
While if I have very slightly entangling gates, and the amount of entanglement along all this simulation is reduced, then I can perform a lot of truncations of these tensors while having still a very good approximation. So there is this trade-off, which is very difficult to quantify, but I can actually run different simulations with different cutting numbers and see if they are consistent. So there is a way of proving that actually your results are consistent.
Very interesting. So We have not only the state vector emulator, but we have also other techniques, HPC techniques to emulate quantum computers in a very efficient way. Okay. Yes, if there is another question, I think that we can thank Artur. Thank you so much for your very interesting talk.
Thank you very much.
And then we can move on to our to next speaker. That is Jean-Philippe Nominé from CEA. He is HPC Strategic Collaboration Manager at the CEA, and also ATP for HPC Steering Board member, and also Vice Chair for Research. Lot of titles.
Thank you so much, Daniele. Thank you so much. Now comes a dangerous moment of activating some screen sharing. So tell me whether this is fine.
Oof. Very fine.
Oof.
At the first attempt.
Oh, it's not so frequent. Okay. Good afternoon, everybody. First of all, thank you very much, Daniele, and the other organizer for the invitation to such a nice and rich event, and for the nice logistics and moderation too. Okay. For this welcome. Let's move forward for the last talk of this session. Back to some, I would say, less technical and scientific presentation. First, I would like to credit my colleague and friend Guillaume Colin-Verdière for co-authoring this presentation. In practice, Guillaume is the main contact point for us when it comes to HPC and quantum computing, and is principal investigator for this. I am more on the side of general management of European and international collaborations, but happy to work also on quantum aspects. First of all, let me quickly remind from where I'm speaking. CEA, Alternative Energies Atomic Energy Commission, is a large research and technological organization in France with 4 main areas of activities. Carbon-free energies, including more and more renewables, global security and defense, technological research for industry, and I would say some cross-cutting underlying fundamental research in universe and life sciences mostly. And for this all, we use a lot of HPC-enabled simulation, data analytics, and artificial intelligence. So not surprisingly, with time, we've developed activities all along the value chain of HPC, infrastructure, technologies, applications. For instance, we operate large-scale HPC facilities. I will show you afterwards briefly. We develop pieces of technology from I would say microelectronics, semiconductor components, up to software, system level co-design with industrial partners, etc. And including also a lot of software from, I would say, all aspects of stacks, middleware, up to applications. And of course, we are, for all our missions and programs, a heavy user of HPC together with many scientific and industrial partners. Okay. So this is for a general setting. When it comes to quantum research, a quick word, because we also have fundamental and technological research on, I would say, quantum elements that are useful for quantum computing. I would mention 3 teams, 3 main teams. We have some more, but you may know some of them. Historically, we have this Quantronics group in Saclay with Professor Esteve, and still very active. In the early 2000s, he was a pioneer in supraconducting technologies for qubits, Josephson junctions and Cooper pairs in particular. And now they are developing new things which are quite fundamental on nuclear spin-based qubits, for instance. More recently, and growing and raising, we have the group of Nicolas Sangoire, Institut Physique Théorique, Saclay as well. I recommend you this very nice recent paper by Nicolas and colleagues on reflections on possible models, need of memory for quantum computing, not only computing resources, etc. And Nicolas will be involved in the project I will mention further on. And last, not least, we have in the Technological Research Directorate this time, Maud Vinet and teams who work on CMOS qubit, silicon-based quantum computing together with CNRS, University of Grenoble, and other institutes, of course, but Leti is more or less leading and coordinating this with, I would say, a number of nice either quantum flagship or ERC projects, and you have a few references and pointers here. Just to say, we have those people who are upfront, and when this feeds the maturation of technology, and when startup can then follow up on this and start developing products, we are very, very happy, and this contributes to the global, I would say, European momentum in quantum computing. And then, when it comes to HPC by itself, we do operate those infrastructures in single site. This is near Paris, south of Paris, Bruyères-le-Châtel. All the big supercomputers operated or owned by SEA are grouped here in 2 facilities. So we have Big Defense 1, around 60 petaflops as of now, currently. We have the Public Research 1 together with GENSI. This is GENSI's Joliot Curie machine, 20 plus petaflop currently. And we have also a third one, which is a separate, I would say, system and machine and room, machine room, meant for industrial use of HPC with industrial partners. And it's around 10 petaflops as of today. It's called CCRT, and I insist a little bit on this one because it's very original. We have a co-funded, actually, a co-funded computing center, mostly co-funded by industrial partners with around 20 private or semi-private or public-private partners, with a separate machine meant for industrial confidential use with specific access data management, etc. Because it's industrial production runs they do on this machine. And as early as 3 years ago, we installed a QLM for them, mostly for industrial partners, to have early access and to be able to investigate as early as possible use cases in quantum computing or hybrid HPC quantum computing. And this is a 31 qubit, not so recent QLM, but still up and running. Voilà, for the global picture. Now, let's come to our global vision and standpoint when it comes to HPC plus quantum computing. Alors, beginning of this year, this is politics, very briefly, but as a reminder for setting the stage, we had the President Macron announcing a French plan in quantum computing, quantum technologies at large, including quantum computing, including a specific project called PNCQH. Okay, in short, that would mean hybrid quantum computing platform. And this is the project on which I will now focus a little bit more, because this is starting just now. I mean, these days, these weeks, after some preparation phases. So what is this project? It's meant to develop usage of collaborative quantum HPC computing. It's both to develop progressively a friendly environment for end users, plus a test bed for research. It is meant to be an agnostic platform, hybrid HPC quantum elements. The CEA TGCC center, the one for research and industry I just mentioned, is a reference center selected by France for this. It will be based on a quantum emulator or quantum emulation environments, mostly using Atos QLM or MyQLM that were previously mentioned, and many of you know or use. We intend to install a diversity of QPUs progressively. Pasqal, very likely the most mature one and interesting one currently in our idea, but other will come, French or European technologies mostly. This will be aside or coupled or together with TGCC agency research supercomputers in our big open research center. And we want to develop elements of agnostic with respect to hardware, software, a diversity of the best breed software for users to develop algorithms and applications. 4 axes, acquisition of QPUs, this will be done with GENSI, the National Agency for HPC for research equipment, with research, academic and industrial players to develop software and application, develop hybrid use cases, scientific and industrial ones, and of course, there will be also an activity of dissemination, training, developing skills and competencies. Okay, it's a 5-year program, 88 million, starting now, end of this year, first actions are being put in place right now. So CEA, INRIA, Agency are leading the different tracks together with other public or private actors. And our first, I would say, concrete action is coupling this with EuroHPC HPCQS project, which just started, was kicked off a few days ago. I will say a few more words, but probably later on in the afternoon, Christel Michelsen will explain you HPCQS more in detail with a Yuri standpoint. And for us, this is the first step of this program. We combine it with HPCQS, but more will come, combined as well as much as possible with future efforts supported and co-funded by EuroHPC in the coming years. For CEA, for any further question discussion, we can put you in touch with the main contact point on this. For us, it's Jacques-Charles Lafaucrière, our HPC program director at CEA. In short, we will work in the research environment together with GENSI in our TGCC center, and we will start with a combined French, European effort, a multi-country effort through HPCQS, EuroHPC project, 6 countries involved in this project. A word on the regional level, we are leveraging this as well because Île-de-France, Paris region, Paris greater metropolitan area, if you will, is very dense in terms of scientific and technological activities. So it's a very good place where, with many labs and industrials to put people and actions together. So we have a number of local initiatives for this. The one called PAC Quantique, supposed to support industrial in the use case exploration together with academic partners and directly working with the technologies developed by quantum startups. This is supported by the region. TerraTech is another association born in our region, but with now a national and even European dimension, but they have a strong club of very large advanced industrial users. So putting that all together is virtuous. It helps connect local levels with more global, national, European levels, and combining efforts. You have pointers if you want to learn more about those initiatives. So the first technology of interest for us is clearly, as a first step, we want to endeavor Pasqal, with whom we've been in touch for a while already. There was a very nice talk by Sebastian this morning, so no need to repeat everything. I would insist on a couple of things. I saw this rather confidential and discreet announcement a few days ago related to a Q Quantum event and on LinkedIn, some announcements that Pasqal, together with their usual research partners, Institut d'Optique, etc., reached 500 qubits in the lab, which is extremely nice and promising. And in the meantime, and in parallel, they are developing their product. They are productizing their technology. On the left, you have the lab machine, we know well. And on the right, you have the mock-up of the future product. This morning, Sebastian, if I am not wrong, even showed a real picture of the real industrial prototype. They are moving ahead very nicely in engineering and industrializing the prototype, and we are very, very impatient to see that and possibly install and deploy that. Voilà. And last part would be a quick overview of our role in this HPCQS project. Like I said, kicked off on December 1st. It's a EuroHPC project, so-called pilot quantum simulation project from Work Program 2020 of EuroHPC, where it took some time to put all in place, grant agreement, etc., co-funding. But now we are ramping up and starting for real. So very quickly, we have 6 countries in this project: France, Germany, Spain, Italy, and Ireland. You see the partners here. The idea of HPCQS, supported by EuroHPC, is to set up the foundations of a hybrid quantum HPC infrastructure, starting with a dual installation of systems, one in Jülich, Supercomputing Center, one at CEA together with GENSI. So in 22, we will start with I would say, installing, deploying, or complementing emulation environments, mostly based on QLM, for people on applications to be able to start studying algorithms, workflows, etc. And then in 23, we would install 2 systems, which would be procured in the meantime, one at ULICH, one at SEA, and similar systems. And we want to develop together software stacks, elements, user interfaces, tools, etc. And that would really be for us the spearhead. We want to further share in the future of a pan-European infrastructure for quantum and HPC. Our mission in this project, SEA in particular, is twofold. We will be one of the 2 sites integrating, deploying, like I said, the emulation environment, then the real quantum system, the quantum simulation system. For us, it will be TGCC aside, coupled to Joliot-Curie Tier 0 system, Gen6 research machine. And we have Nicolas Angoire's team in IPHT, which will develop a number of things regarding benchmarks and applications. So on computing center side, that is my side, we will have some coordination, technology watch, infrastructure, integration, system related issues, operations teams will be involved, etc. Main contact is again Guillaume Colin-Verdière, and I'm proxy on this project. So don't hesitate to have any time to talk with you if you're interested. And on the application benchmark side, that will be Nicolas Angoire's team working on that. And to give you a flavor, a teaser, because we will need another workshop in the future for the real experts to comment their developments. The SEA people will work on 3 of the use cases identified in HPC QS. First, it will be on certification and performance analysis. Roughly speaking, it will be about certifying quantum properties and accurately evaluating performance of quantum systems. And this will be together with CNRS, developing that witness-based, device-independent, analog randomized benchmarking, this kind of stuff. And Nicolas Angoire is really a well-known expert in these areas in particular. Then there will be an activity on QA/OA. In particular, SEA will study, other partners will contribute to these activities, but SEA will particularly focus on factorization applications. And the last one will be in VQE. Then on this, SEA will work more particularly on catalysts for nitrogen fixation, which is a very promising potential killer application for quantum computing and HPC plus quantum computing. Beyond using the machines for the partners for these use cases, the project, HPC-QS, intends to open resources as much as possible to the wider European communities as soon as possible, and when we set up the platforms. Voilà, to finish with some teaser and advertisement. On our side, together with TerraTech, we've been organizing workshops as well since years. This is within the scope of so-called TerraTech Forum, which is a two-day event traditionally taking place in June in France, which is becoming more and more international. We started quantum workshops in 18 with some, I would say, prequels as soon as 16. Last year, we had a nice one together with Christel Michielsen on hybrid computing. And in 22, we intend to come back to technologies and do an updated tour of European qubit technology. So as a teaser, we started talking, or we would like to invite a number of European companies. So Guillaume and I will take care of that, and some of you may hear from us soon, so as to try to organize a workshop, and everybody will be welcome. It's open, free registration, etc. So hope to see some, or if not most of you, next June. Hopefully face-to-face, but well, we'll see. And last advertisement would be, I would recommend the reading of this nice paper we wrote from within ETP for HPC with a bunch of friends and colleagues. Some of them, if not most of them, I think are in this session today, like Daniele, like Mikael from CSC, like Christel, etc. And that's all for me. Thank you for your attention.
Thank you, Jean-Philippe. Very interesting talk, and glad that you spoke also about ASPCQS and our white paper for ATP for ASPC. That it was a pleasure to participate in both of the projects that you mentioned. And of course, we will help you also on the side of the use cases and on other things that you will need. So, is there any question for Jean-Philippe? Don't be shy.
No, I was a bit. I prefer to be. It's always better to be shorter than longer. So I was maybe a quick fast. What I can say, I was not too technical. First, I'm not the best expert in many of these areas. So next time, maybe some real experts could be speakers to give better insights on their progress. But I can tell I really appreciated a lot a number of things I saw in previous presentations, in particular from Elerset and from Luigi and from Sarah from Ariana, because when it came to discussing coupling modes, workflows, how to associate, combine classical HPC, quantum HPC, I really appreciated what they showed. It is very interesting, and this is exactly the same kind of questions and reflections we have or want to have. And I think we must really foster further discussions, exchanges all together, because this has to be really a collective effort, and we already share a lot of ideas, and we have to more practically share, I would say, efforts and actions on these topics.
Yes, I agree. So, okay, we have some question here in chat.
Yes.
We can read the first one, the second one, because the first one is only it's not a question. It's please, Fabio, brought your question. And the question is, what are the main universities France involved in quantum computing? Yes. You mentioned Grenoble, but there are any other?
Okay, when it comes, right, quantum at large, we have strong teams. I mentioned Grenoble University because they are partners of our LETI colleagues and Institut Néel in Grenoble. So this is clearly to be mentioned. And I would say a very strong team is with École Normale Supérieure, Laboratoire Kassler-Brossman, LKB in Paris. But it's from fundamental physics and now up to quantum computing. It's broader. You know, École Normale Supérieure, they have the Nobel Prizes. They have Cohen-Tanucci and Haroche. Okay, but this is the fundamentals of quantum physics that made possible our discussion today. Without these people, we wouldn't have today the capacity to consider the manufacturing of qubits. Though we really need this fundamental research. So there is a strong activity around École Normale Supérieure, but universities in Paris are also involved. Can be Paris-Saclay, the group of universities around Paris-Saclay has different teams working on that. And and then you have a strong group around. It's a mix of university and engineer schools in France. We have a quite particular system. We have a very strong group around Institut d'Optique in Palaiseau, which is not far from Saclay, not far from Paris, but it's still a bit different. Pasqal is coming from these teams, Institut d'Optique. This is an optics engineering school. They are extremely strong in optics and now quantum computing. And from this Saclay, Palaiseau region, you have Pasqal coming, you have Candela startup and more. And from École Normale Supérieure, you have Alice and Bob startup. This shows this is very vivid. And I will eventually mention École Polytechnique nearby. They also have good people, and they are very good education and training in quantum physics and quantum computing, to name a few.
Very good, thank you. And we have another question. So it says, I see that many initiatives, with some notable exceptions, are at regional and national level. What is your opinion about the perspective at the European Union level, also for the Euro ASPC commitment?
We need to pull efforts. It's not so easy. My hope we've observed that in HPC, conventional HPC, I've been working that for 15 years, so I know a little bit the issues and what was improved or not over the last 15 years. It was quite difficult and still to align and pool efforts. In quantum computing, we desperately need to align some efforts and pool efforts. I am a bit more, it might be a bit easier because it's a new area. We don't have too many legacy issues or problems or background to handle. The history is a bit new. We write more or less a new page, a blank page. So I'm a bit more optimistic that we can, thanks to good research by the quantum flagship, part of it leading to startups developing qubits. Now your HPC pushing efforts on quantum equipment and hopefully related software. I think we have good ingredients. We need not be already 100% all agreeing on everything, but we have good chances that with quantum flagships efforts, some articulation of your HPC, we have good chances to really leverage a number of national initiatives, assets, talents in different European countries and maintain a diversity of effort. I think it's a domain that still needs to remain very open, exploring a number of options, because nobody can tell in 2, 5, 10 years what will work, what will have survived. And we are in a good position in Europe. We should really, really be aware that we need to work all together. And we probably can find enough sufficient common ground to work together positively.
Okay. Thank you for your answer. And okay. Also, Fabio, thanks to you. If there are no other questions, I think that we can thank everybody, Jean-Philippe, and then we can anticipate the 5 minutes of our break. And I think that can be a good idea. And we will restart at 15:30. So thank you a lot, Jean-Philippe. It was a very nice talk. See you in another occasion. Thanks.
Yeah.
See you, everybody, at 15:30.
Okay, if there are the speakers of the next session to test the microphone, maybe now is the right time to do it.
Hello, Enrico. Hello, Daniele.
Hello. Yes, I can hear you. Okay.
I believe I might be the next one if I'm not wrong.
Okay, perfect. Yes, you are. You are. Thank you so much. Okay. Is there anybody else?
Okay.
Is Michael Johansson?
Yes, yes. Hello.
Okay, we can hear you. Okay, the test
Okay.
is done. Okay, thank you so much.
Right.
What about Andres Gomez? Are you in? Okay, maybe he's having a coffee. And Crystal, are you online? Are you connected? Maybe not. Okay, I see you then.
Okay. Welcome back, everybody. We are ready to resume. Okay. Our next speaker will be Venkatesh Kannan from ICHEC, and he is the Center Technical Manager, Platforms and Technologies Program Manager in the Iris Center for High-End Computing, also known as ICHEC. Thank you, Venkatesh, for being here. It's a very pleasure to give you the floor. Thanks a lot.
Thank you, Daniele. I'll just take a moment to share my screen. Okay, could you confirm if you can see my screen all right?
Yes, we can see it.
Thank you very much. So good afternoon, everyone, and thanks very much for this opportunity to share some of the work that's happening not just at ICHEC, but also at a national level in Ireland. So since probably this is, we have a lot of speakers in the past I saw today who covered a wide range of topics. So most recently, JP shared the range of activities happening in France, but also the technical depth in terms of tensor network-based approach. It was very interesting to see the breadth of work that's happening. So I would like actually to take this opportunity as maybe the first in a series, as Daniele has been very industrious in continuing this engagement, this conference, this workshop, so to say. So I'd like to take this as maybe one of the first instances in which we are presenting what's happening in ICHEC in Ireland. So I'll keep it not too technically deep. To a certain level, I'll present the technical details, but in a broader sense, maybe give a notion of what's happening in the Irish ecosystem and where we are actually headed to synergize our national efforts in terms of quantum computing and its positioning. So in that respect, so a quick note on ICHEC, as Daniele pointed out, we function as the National Center for providing high-performance computing platform and expertise capabilities at a national level by mandate from the government. So we engage with the academic researchers, the enterprises, and also public sector in their requirements for computational and data platforms, and also support them developing and deploying their solutions on these platforms, whether they are national platforms or on-prem or cloud platforms. And in that sense, the quantum computing part comes in because we've always had a tradition of looking at emerging technologies. So 8 years, 10 years ago, it was general purpose GPU computing, and then it became a lot more mainstream thanks to both the hardware, but also the algorithmics, such as neural network based approaches that kind of brought them more mainstream, just beyond visualization and graphic processing use cases. So we have a tradition of looking at these emerging technologies and bringing them into mainstream national service. And quantum computing is naturally one such. It's one of the stronger emerging technologies, alternate computing models that we see. And naturally, the focus there is at a national level to drive the adoption of quantum computing, to evaluate it, track the monitoring of the progression of the technology, and then enable its adoption both in the scientific and research and enterprise communities. So the focus pretty much of the Quantum Programming Ireland initiative, which has been around since mid-2018, is it brings together industry, academia, and public sectors, and ICHEC kind of drives and tries to synergize all of the efforts, and with focusing on the positioning of quantum computing and simulation systems alongside HPC systems. And naturally then looking at the software and algorithmics research that can potentially be done at the current TRL levels on these kind of platforms, and then feeding both of the first into national skills development programs around quantum computing and programming. So we are very conscious of learning from the classical HPC experience that we have had in developing a national skill force. So there was a huge surge in data science and machine learning and AI skill sets in the market 3 years ago, and the government and agencies and ICHEC, for example, we rushed together to put in place different forms of skills development program, because it's just not about creating master's or PhD degrees, but being able to address a comprehensive workforce development program. And so we take that learning into engaging the community in skills development in quantum computing and programming from a very early stage. So skills development is a very significant aspect. And all of these are funded by a combination of projects and programs at national and EU levels. So a quick outline of the Quantum Programming Ireland initiative. The first is basically, as I mentioned, the requirements of developing and deploying hybrid systems, and naturally it started with us in developing a quantum learning platform at a national level. So this is in the first phase, it's not a quantum mechanical device, it's a software emulated device which we have been putting in place since mid 2019, and COVID has delayed stuff, but we are bringing it as a part of our national service to the users from 2022 Q1 onwards. So this would allow a portfolio of quantum programming and software development toolkits, which can be used for both education purposes, skills development purposes, as well as by the research community. And naturally, the HPC QS project that JP mentioned most recently in the last talk, but also possibly touched on more by Crystal going forward. That's a project in which Ireland is engaged through ICHEC, and one of the parts of the project is to use the Phoenix interface infrastructure to connect, so to say, the quantum learning platform for users to migrate from the national platform to eventually when the twin pilot systems are deployed to provide a seamless transition in the environment. But then the journey for ICHEC in terms of quantum computing started with the algorithmics. It was the smaller step that we could take with minimum investment. So to say, back then in 2018, 2017, it was to look at the algorithmics and software development, and primarily, naturally, the usual suspects. We started with systems that were more congenial in terms of scientific systems, molecular systems, machine learning, and optimization problems. So we are engaged in both quantum flagship EuroHPC, but also national projects with industry and academic partners. And then from there, it progressed to looking at the software stack as a whole, and looking at how, so to say, QPU awareness can be brought in the classical programming toolkits, particularly parallel programming toolkits that are primarily associated with HPC systems, and Quantex. So Quantex is basically an exascale targeted tensor network simulation framework, which has been under development since PRACE 6IP WP8. So currently we are testing them on some of the petascale systems that are coming up. And that is done in partnership with Luigi and team at LRZ as well. So ICHEC and LRZ work together on developing the Quantex framework, and it's being developed as a package within Julia YAO module. So we'll be disseminating more about this by the end of PRACE next year as well. And thirdly, as I mentioned, the skills development program. Currently, we work in conjunction with national agencies in skills development and are creating a portfolio of, so to say, training programs that complement and also bridge the gap to the more academic research deep dive programs that are available in higher education institutes at a national level. So this also works in conjunction with EuroCC. So going forward a bit more, this is where ICHEC was trying to drive the capabilities and skills development and some of the at least R&D programs within Ireland. But what we saw increasingly was Ireland as a whole has a tradition of scientists, engineers, as well as programmers who started working on quantum systems. So the Tyndall National Institute, for example, has a tradition of working on photonics and even ion-based quantum mechanical and device manufacturing. And there are a few other spin-offs from the University College in Dublin and other institutes where people work on semiconductor-based quantum device engineering and manufacturing and the science and physics behind it. And naturally, ICHEC, we focus on hardware upwards. And there are a number of enterprise and academic researchers who focus also on the algorithmics in terms of error correction, cryptography, and QKD, and the application areas as well. So we saw that this is going to be important to bridge the community at a national level by bringing together these end-to-end capabilities at a national level. So the High Choir is basically an initiative that is due to kick off soon, and it is meant to be a hub of excellence within the Irish island. And I say island because Northern Ireland is also targeted here to bridge the communities there. So a hub of excellence in the island of Ireland to develop the research activities and systems and applications for hybrid HPC and quantum computing simulation systems. So at a very high level, the focus areas are around eventually leading to creation of a testbed platform that is essential for researchers and students from academia and the user community to independently and collaboratively work on R&D and experimentation and skills development. Then all of this requires naturally a very strong scientific and fundamental research and innovation activity that addresses throughout the stack, the hardware, system, software, the programming environment, hybrid application workflows as well. So this is the core area where we expect most of the work to happen. And then we also realize that this kind of a problem clearly engages experts from a wide range of backgrounds, people with physics background, with semiconductor background, with engineering, device engineering background, both from the quantum mechanical side and the classical computing side. And then we naturally have the HPC community, and then we have the algorithmics communities, domain experts, both students at different levels of expertise. So we saw that it's going to be really important to not just have the communities work on their individual expertise areas, but actually have this cross-domain skill set being built across the community. A very simple example is anyone working on modeling molecular systems in quantum computers. We realized very quickly that we need people with molecular systems and chemistry background, with quantum algorithmics background, programming background, DevOps, and so on. So, and it's always a blended team we end up with. So we saw that there is a significant need and opportunity to kind of twin the researchers and students from across the community, so that 5 years down the line, 10 years down the line, we'll have people with these blended skills more apparent. And naturally, we see this as in the emerging program that is being planned of EuroQCS. We see this is going to be the pathway that will kind of ease Ireland's participation and contribution in the EuroQCS activities in a complete level. And community enablement. Now, this is not probably entirely technical, but what we see is, at least at national level, quantum computing, the overpromise of quantum computing, what QC can do, is sometimes scary for us. So the messages are promising in engaging the community, but we see that it's really important for both the government, the researchers, as well as the general population to be aware of where quantum computing as a technology is currently and where it is headed, and not follow the hype, so to say. So a continuous enablement of the community's knowledge building is something that High Choir targets as well. So this is where the program, the Hub of Excellence, is going to function, the space, and then it's envisioned that this will start in 2022 going forward and bring the complete capabilities from Ireland together under a single umbrella. A bit more details. So the establishment is targeted through national seeding in 2022 starting, and this will formalize, so to say, the ecosystem and serve as the precursor. Naturally, the progression there is then to start looking at partnership and engagement more formal engagement with European programs. So currently there are a number of projects in which the partners of HiQuire are engaged. So ICHEC, for example, in HPC-QS and a couple of Horizon 2020 projects. Tyndall naturally participates in a number of quantum engineering related programs as well. But then in a formal sense, what we aim to establish is across member states a direct collaborative channel and take advantage of activities such as the multi-country projects and others that are emerging through the Digital Compass program going forward, that the European Commission strongly believes will benefit direct member state to member state engagement as well. And finally, what we want to see is basically a sustained end-to-end activity within Ireland, with a strong engagement in Europe and global engagement. So that's where we see HiQuire going over the next 5 to 10 years timeline, but this is under plan and progression already. Very quick, so I probably don't need to make the case for this, but all of this started, meaning the hybrid, why focus specifically on hybrid HPC and QC, started with the current ecosystem that we had to face in terms of when we demonstrate or teach or do our own research with the currently available quantum computing systems and software stack. So we noticed very apparently, very quickly, that the QC applications or the QC systems naturally reside mostly in a sandboxed environment, in a closed environment by themselves. There are naturally efforts on integrating that at different levels of coupling degrees, either loosely or weakly or strongly, irrespective of it. They still remain currently at large as isolated systems. That's not the worst part. You might be using Python for programming, but for two reasons. Python may be not the most HPC-friendly performant programming language, but also the libraries and tool suites, they kind of still remain quite disconnected from the usual HPC programming models that we have so fine-tuned, and also the data management software that we are so much tuning going forward. So what we see is there is going to be an increasing need to synergize and connect the languages and toolkits that are focused on the quantum computing and programming landscape and bridge them to the classical HPC programming model, and also that applies to the system software level, for example, to schedulers and performance monitoring frameworks to be aware of QC systems and QPUs, so that eventually where we want to go is have different degrees of different models of coupling QC or QPUs with classical processing units and systems. So at the bottom layer, we probably are looking at deploying quantum computing systems as, so to say, nodes of larger clusters that may be on-prem co-location. And then there would also be naturally a federated remote access. But then potentially there are also works that we have at a national level, and definitely broader international level, where co-location of QPUs and classical processing units on a single die or a single chip is also being investigated. So we see that there are going to be at least a few different modes of integration of quantum computing and programming systems happening at a hardware level, and the interconnect around it. Naturally, on top of that, the system software and programming environments need to be bridged so that we can eventually have, within a single streamlined application workflow, have, so to say, library calls that are more seamless and latency aware, that leverage these underlying integrated software environment. That's where we are headed. A bit more in detail, in HiQuire, what's happening is we naturally start, we look at this from a co-design perspective, and what we mean by that is we start at the use cases level. So typically we are used to looking at quantum computing use cases where it's optimization or looking at molecular systems and physics systems, and pretty much done in isolation. What we want to push for going forward is to look at application workflows where it's just not mapping a kernel to a quantum computing programming model, but actually taking a larger HPC demanding workflow and offloading a part of the kernel to quantum computing and then feed it back basically to the classical one. So we are indeed looking at workflows, for example, in physics systems where the diagonalization or post-processing is suitable for classical HPC, and then there is a part of naturally the simulation that is offloaded to the QC. For example, in larger chemical systems, we work on a project where we look at really large chains of CF carbon fluorine bonds under a category of molecules called per or polyfluoroalkyl substances. They are a class of environmental pollutants. And what we see is it's a systematic chain, a really large molecule. So definitely it's not going to fit under the NISQ factor of NISQ scale of devices. But then the molecular fragmentation, the chemistry community believes that we can have a systematic way of fragmenting or breaking down the larger molecular system into subsystems and then offload the subsystems in an iterative fashion onto a quantum computing system and calculate the energy levels of the subsystem and then aggregate them in a classical space again. So VQE, if we take VQE as an example, it's already a hybrid loop, but then if you put a more classical loop around it, which deals with fragments, then it becomes a really HPC and QC warranting approach there. Now, it's not straightforward to just add up the energy levels of the systems from the fragmentation. So there is going to be naturally a chemical or a chemistry validation of the aggregation and fragmentation system. But that's where the classical part comes in as well. And we are also looking at AI-related applications from the perspective of developing AI-defined quantum programs for automatic synthesis, for example, of hardware designs and software design, particularly, for example, in the areas of wireless communication, where training an AI model is better to be done on QC, on HPC, because naturally we're not going to get the entire training data set into a quantum computing system. But then the parameter optimization or the parameter search is where it makes more benefit. So the use cases, we're increasingly looking for use cases where it warrants a hybrid workflow and not just a classical or a QC workflow. And all of this feeds into then, based on studying the use cases, we believe that we definitely are at the cusp of being able to define more complex algorithmic constructs and programming primitives. So we already have kind of efforts in the YAO framework in Julia, for example, where quantum computing friendly data types and operations are being packaged as libraries. And so we are looking at building more abstract programming constructs and libraries incrementally, and also domain-specific application libraries. So this is very apparent in the NISQ project under Quantum Flagship coordinated by Atos, where we develop a suite of technical libraries or application programming libraries. And they, for example, that's one category of libraries that focused on chemical systems or molecular systems. That's one that focuses on optimization related problems. There's one that focuses on NLP. There's one that focuses on probabilistic safety assessment and rule-based systems. So there are going to be different levels of abstraction of these algorithmic constructs that are built, and we are looking at that as well. The programming models, what the focus there is going to be, it's on basically looking at the classical HPC programming models like the MPI or OMPs, the primitive-driven ones, and looking at how we can have routines or directives that can demarcate or label basically a kernel needs to be offloaded or can be offloaded into a quantum computing system. And then what we eventually will have is something like we had in classical world, where we might have different implementations of the same kernel, and at runtime the runtime might actually decide based on the computer and data characteristics whether a kernel is suited to be offloaded onto a classical system or a quantum system. So extension of programming models is something that we're definitely looking at going forward. Third is compilation and verification of circuits as well at runtime. And then all of this would need a more system software support, which is also strongly coupled. So the dynamic mapping of these kind of hybrid workflows has to be addressed in the runtime of these programming models as well. So we are actually looking at how LLVM, for example, the intermediate representations in LLVM can be extended to accommodate translation to circuits that are, for example, specified in OpenCASM format and others. Naturally, there are already efforts that had been initiated in this domain. So EXAC and I think Microsoft had also integrated their Q-Sharp framework to be able to leverage the intermediate language in LLVM. So going forward, we're actually looking into how LLVM MAR extensions can be formally specified to allow translation and optimization of OpenCASM quantum circuits within the classical compiler library as well. And performance measurement is something that's very unknown to us as well, because we have a good understanding of the metrics and the mechanism of measurement of performance metrics in the classical systems. It'd be at a compute level, at a network or a bus level, or an I/O level, or a storage level. We understand what the metrics are likely to be and how to measure them both at the hardware and software level. But when it comes to the quantum computing systems performance, it's still very early stages, rightly so. But we want to have a foresight as to what kind of metrics would we be looking at and how they can be collected through a software-enabled mechanism, and more importantly, how the performance metrics are going to be added to the performance reporting mechanism that we have in a classical HPC system. So how performance reports and performance analysis can be done in a more streamlined way when it comes to hybrid systems. So that's again a part of the research that we target doing. And as I mentioned, at a hardware level, it's different levels of integration there. And the top-down, it's a core-defined approach that specifies the requirements of each of these layers. And bottom-up, it's going to be the demonstrations of the systems as we build them incrementally. And naturally, all of this feeds into the skills development, and it's heavily research-driven program here. So I am aware, probably I have just 4 more minutes. So what I might actually briefly touch upon is something called a quantum programming certification course. I'm afraid I probably will not have enough time to present the details of it. But this is something that ICHEC has been working with the National Skills Development Agency and a Scientific and Industry Advisory Board at a national level over the last 18 months. It's been in consultation and development. So what this is not is actually, it's not a PhD program or a master's program. We leave the experts to actually develop the scientists and the academic community for that. What this is actually is to bridge the gap between someone that has a purely physics and mathematical skills to look at quantum computing and programming, and similarly someone from a classical ICT background who wants to kind of incrementally or increasingly get into quantum computing and programming. So it's supposed to be a bridging course that introduces the learners in an iterative fashion to come on board and build their math and physics and quantum mechanics fundamentals, and then start looking at the algorithmics and programming and application areas. So this is something that we are building at a national level, but we're very keen actually to work with the rest of the efforts around Europe and our partners as well to bring this to a European level through different channels that we already have in EuroCC through praise training programs and going forward. So we'll be happy to actually leverage all of both of these, the certification course and the HiQuire initiative to formally start more concrete engagements at a national and member state level going forward. So with that, I'll probably finish for now. And I hope in the next opportunity, we'll be able to share more scientific outcomes of the work that we are doing at a national level. Thank you.
Thank you, Venkatesh. Very interesting. Is there any question for Venkatesh? We have a couple of minutes. Let's wait if somebody has some question, or if not, maybe I can. Okay, and just a curiosity, Venkatesh, the last program that you mentioned is something that I didn't understand. Is something that you do after your PhD? You have to be. What is the level of the?
We have it's an entirely customizable program. People can choose different pathways depending on what their learning outcomes are meant to be. So on one extreme, it can be for technical managers in different organizations so that they can have an outline of the ability to track technology development and its application. On the other end of the spectrum are going to be developers and scientists and engineers who want to actually get into the algorithmics development and application development. So it's a a la carte, so to say, of modules, and we expect people to take different trajectories in the learning path, and we expect people to take it before their PhD or leading to their PhD as a bridging course, so to say.
Very interesting. Thanks for sharing. Okay. If there is not no any question, I think that we can move to the next speaker. That is Professor Mikael Johnson, Quantum Strategist at CSC. And Mikael, thank you for being here. Floor is yours.
Thanks for having me. It's a great conference so far, and I'm sure it will continue. Maybe if we skip this next half hour. Yes. No, the program is really excellent, and I'm really enjoying this.
Thank you.
Anyway, my topic today will be on pooling HPC and quantum resources across borders from a Nordic perspective, and we'll see what it means. Okay, so switching next, but maybe a quick background to CSC and what we are. So we are maybe the Chineka of Finland in a way, but Finland is a smaller country, so we are the only supercomputing center in Finland, and of course these days we do much more than supercomputing as well, or provide computing services, but that's where it all started 50 years ago, and the UNIVAC 1108 was the first supercomputer we were hosting for our customers, and these days we have grown a bit more, and still last week we had a very nice round number of employees. We were 512, which in binary is very nicely round, but this week we got one more, so now we are 513 people. But in general we are a non-profit company owned by the Finnish state and higher education institutions. The topic of today is Nordic Quest, and that's a cross-border collaboration and integration, and we have 7 partners from 5 countries, and it's a project that starts soon in March next year. The general idea here is to combine several HPC resources and quantum computers into one unified platform in a type of an HPC plus NQC service, if you will. The main hardware components in the beginning will be the Cal 9000 computers in Sweden, developed by Chalmers and the Wallenberg Center for Quantum Technology, and the Finnish quantum computer by VTT in collaboration with IQM, and the HPC resources will be Lumi, the Euro HPC pre-exascale computer, and EX3, an experimental platform for high performance computing that we have in Norway. In a bit more detail, the partners here. So as mentioned, we are 7, and it's Chalmers, CSC, the Danish Technical University, and Simula and Sintef from Norway, University of Tartu in Estonia, and VTT again from Finland. And all of this is funded by the Nordic E-Infrastructure Collaboration, NAIC, that in general wants to promote Nordic collaboration in the field of E-infrastructures. The background motivation for Nordic Quest is that individually the Nordic countries are relatively small, at least if we compare to Germany, France, UK, traditional strong quantum countries within Europe. But by pooling these national resources we really can create something that is larger than the sum of parts. And even if it is a cliche, it is true in this case, because one needs sort of a critical mass before one can start actually achieving something useful. And another motivation for this is that the Nordic region, also including Estonia, has a solid and established competence in traditional software development for standard computers, and on average, actually 1.6% of the population in the Nordics are software developers, and that's about 60% higher than in, for example, Germany or the US. So sitting in front of a computer and coding is popular here up in the north. But to support the extension of this traditional software industry towards also quantum software development, access to a mature and easily approachable quantum computing infrastructure is crucial. It needs to be easy for the people. One is not supposed to be a quantum physicist in order to actually be able to start programming and developing programs. And NordicWest aims to really provide this low barrier access to quantum computing and HPC plus quantum computing, with the idea of reaching students at various levels as well as professionals. So we also actively want to go in for getting quantum computing already at high school level and maybe even earlier, at least introductions. And being a Nordic collaboration between and under an umbrella organization of rather low bureaucracy, we also hope to be easy to approach. And one thing that helps here is also that we really are spread out all over the region, so one can contact your local representative in an easy way. And I think this really is an important aspect of getting users engaged. It is always easier to get in contact with someone from your own country, even if it is an international collaboration. That's just a fact of how things go, in my experience. Okay, the tasks of NordicWest, well, these are just directly from the work plan. So, but it starts with charting the needs and interest for a Nordic quantum computing platform, both for education and for science. And then the idea is that we customize this platform to the needs and requirements of the Nordic region and really to the customers, the universities, the industry that we have here. With limited resources, one cannot do everything, so one has to choose, and then we want to choose something that is as useful as possible for as many as possible of our potential end users. And then part of it is also to, well, create these algorithm and example program libraries, so it should be easy to start exploring this field. On the more practical side, of course, also connecting and integrating these physical quantum computers to this common cloud-based platform is really central to the whole project. And we also want to integrate quantum computer simulators / emulators. So as this is really important for understanding how quantum computers work, and Luigi gave also already mentioned why actually simulators are important as well. So that's part of the project. And naturally then dissemination and communication, because we also want to really tell our users and the community what is going on and then attract more interested users here. And we go for this distributed approach to high performance computing and quantum computing, and this decentralized approach, among other things, so it really enables diversity by just in the end easily connecting several different quantum computers under the same platform. This also means that this hybrid HPC plus QC is built in from the beginning when we really attach it to pre-exascale machines or platforms. And we'll get into this a bit more, but also low latency algorithm will be enabled by classical hardware co-located with the quantum hardware. So, but we'll get into discussion of that next. But first, an overview of different ways of connecting HPC and quantum computing. So I've divided it here into three main ways. I'm sure one can divide it in different ways as well, but I would say that these at least represent somehow the different approaches. So we have the standalone cloud access, the co-located or on-premise way, where you have the quantum computer sitting next to the HPC infrastructure servers, and then we have the distributed one where the QPU or QPUs and the HPC resources are physically distant. These come with different levels of complexity for the software stack. So the first one, the standalone, is the easiest to implement, but it also then comes with a medium to high latency between quantum and classical part, which might be a problem. The co-located and distributed parts require more integration work for the software stack, but then the advantage is that then one really, in both cases, get low latency applications to run. And the importance of latency should not be overlooked. So here's a recent report, or well, expert opinion on quantum computers for high performance computing by Oak Ridge and AQT. Well, here they have divided typical tasks that one would run and the times, execution times they take, and well, we see that for the low or fast algorithms, we in principle here in this figure only have error correction. And error correction, I will not consider that today. That is something that will anyway have to be at an extremely low latency and then built into the QPU already at low level. So that is separate from normal applications, so to say. But that is of course something that it doesn't help if you have your standard classical computer 1 meter away. So it's still too far. You really need to do this on chip or something. But otherwise, they consider here mostly quantum circuits that would take on the order of a second to run. And well, with 1 second execution times, of course, latency is not really an issue anymore. But I would say that in hybrid algorithms, and I think most agree, then latency can become an issue. And here's just, I find this article very, very nicely written, and then the figure is, you have, of course, seen a similar figure many times, all of you, before. But the idea, anyway, in the hybrid algorithm to having a tight loop, quantum block and a classical block of a calculation. So here, when both the quantum block and the classical block are fast, the communication has to be even faster to avoid bottlenecks. So if the quantum block is very short, then latency has to be low. Otherwise, you run into well, artificial lengthening of the runtimes. And now with present QPUs, decoherence forces the quantum block to be fast, because we have to have very short algorithms, very low depth circuits, because otherwise we just get noise out of the quantum computer. So for quick loops, the standalone approach creates too much overhead, so that's dead. We really need a classical processing unit, a server or a node of an HPC system that is physically close to the QPU, so it keeps feeding it with new input. But it's important to note that this is not an HPC task. So a powerful server here in connection with the QPU is more than enough for the foreseeable future, at least. And another point to note is also that when QPUs mature to this point where they actually provide some quantum advantage, runtimes of the quantum blocks will also increase. One popular hybrid algorithm, the QAOA, is expected or estimated to require circuit depths that approach 1 million gates. And that's well beyond what can be done on present-day quantum computers, but at one day, I'm sure that it will be possible to do this. But when it becomes possible, then latency is not that important anymore. But one can see that from a simple calculation on the execution times of this algorithm. So here's just some typical execution times of gate operations on both superconducting and trapped ion on systems. So 2-qubit gates are usually the most important ones anyway, and even the fastest we are talking about 100 nanoseconds or so. But if you compute from this what the execution of 1 million gates would take, even if you would just consider the fastest 1-qubit gates of 20 nanoseconds, then this circuit would take 200 milliseconds to execute. And this still doesn't include any readout or initialization of the qubits, which would add, at present time, plenty to this estimate, but hopefully those times will also go down. But a signal in a light cable fiber travels at around 200,000 kilometers per second, so we get around the Earth in this time. So this means that the classical server doesn't really need to be that close here. So here, even the standalone model again becomes relevant when the quantum computers are powerful enough. Another example here, just from the IBM and Goldman Sachs collaboration, where they looked at derivative pricing. So well, first of all, we see that quantum advantage is still some time away. So they predict one is 8,000 logical qubits and the T depth of 54 million, and that execution of these programs would be on the order of a second. And of course, this also means that latency is not important. But variational quantum eigensolvers and that family. So this is one where latency really can become important. This is there's big efforts towards reducing the gate count for VQE, because VQE is promising, is one of the most promising ones for near-term quantum advantage. And this is just a recent paper from Cambridge of one of the more successful implementations of VQE, a version of Adapt VQE. And here's an example that they had on beryllium hydride calculation, and to get a moderate error in the energy here with respect to the correct answer, one would need about a 40 qubits depth here, and that's doable without problems. So that also is very fast. But when we increase the system size here, well, the worst scale scaling is n to the third with the amount of basis functions, for example. And now we have to remember that beryllium hydride is a trivial computation for a laptop, and supercomputers can easily handle thousands of basis functions for routine electronic structure calculations. And to reach this, it again requires millions in depth of the circuit. So we again increase the time of the execution of the quantum block to something that doesn't really make latency an issue. But if you have strongly correlated but low electron number systems, then this method, I would say, is very promising. You can get highly accurate energies, and even when one has a low number of electrons. And these highly correlated systems, again, are difficult for supercomputers. So as long as the dimensionality of the problem doesn't grow too much, but it's still a tricky electronic structure, then I think that here VQE really can provide something useful in the near term, and then latency becomes an issue. So low latency between the classical quantum can be important also in the future, even if one is able to execute long circuits. There might be plenty of algorithms that also can be run with shorter quantum circuits. And here then one can either use this separate server or one HPC node to take care of the classical computing that requires the low latency, so optimizing the parameters in QAOA or whatever. And well, so we have these two different models left, the co-located or distributed, and the straightforward approach is, of course, to co-locate the quantum computer with the HPC center. And in this case, the server is just an HPC node. It becomes more involved if we have the distributed approach for low latency, because then there's a bit more work, as we will see soon. But there are other advantages to this, I would say. And this is the approach also that we are in the end aiming for in Nordic West. The software stack for a distributed approach requires somewhat more work than the co-located approach. So this is because we have to take care of one additional communication step between classical and HPC. And this does not exist in the co-located approach, because, well, then this orange node here is just one of the blue ones, so we don't have this part here. This is not completely trivial. So it requires a bit of work to take care, because now the orange server here has to communicate in two directions. The low latency one to keep feeding the QPU, and then keeping the connection also to the rest of the HPC. And also user authentication needs to be done twice, but that is a rather trivial step, of course. Another thing that this requires is that we have to have personnel at more than one physical location, because we cannot expect that either the HPC systems or the quantum computers will run without supervision. But why should one make this distributed approach work then? Well, when the software stack is in place, it becomes easy to add additional quantum computing resources, because what we need then is only the location of a classical server next to the QPU, wherever that is, plus of course a fiber connection to the HPC center. And this increases diversity of the platform and also inclusiveness, because one can't really access several QPUs from the same platform without much hassle, and also from a collaboration point of view, it's easy to time share quantum computers or just test out quantum computers. One doesn't have to buy your own quantum computer to locate it. One can share one quantum computer between many users. So, and with limited resources, one can of course not buy everything, but one can share more. Another reason is that well, the quantum computer and the HPC system can be optimally located, separated and separately. HPC needs large data centers with sufficient and optimally also affordable electric power. Quantum computers don't really need much power and will probably not need much power in the future either. But quantum computers do need shielded environments, either for temperature or other sources of noise. And one slightly worrying study came out last summer where it was found that cosmic radiation already now starts to be a problem for quantum computers and qubit coherence. So of course, if one starts to dig down the quantum computers below ground, it's easier if one just puts a small part there and doesn't need to dig down the entire HPC system. or even try to just build a cellar in existing premises, HPC premises might not be trivial either. Okay, so the conclusions for this is, I would say that, and also one of the driving spirits of Nordic West in general is collaboration, and we need to collaborate and share know-how across the quantum computing and HPC disciplines and communities. And I'm happy to see that there is coming a convergence now in Europe, and these two fields are approaching each other. But there is still work to be done. But I think that everyone starts to see that this really is important. They will not be separate. In the future, they will be intimately linked, and it will stay like this. At the same time, collaboration with the end users needs to be equally important. We need to keep in mind what we are doing this for, and it is so that the end users can run their applications faster. In the end, they are not interested in what the hardware is necessarily. They can be interested out of curiosity, but the deciding factor is, do they get some new interesting science done with the new platforms? And collaboration across national borders is crucial for Europe. It's crucial for the Nordic countries, but it's also for Europe. To keep up with international developments, we really need to all collaborate. And also all three modes of this HPC plus QC integration depicted here again on the right need to be set up in Europe. The standalone model is simple to set up, but it's already useful for many tasks, and especially just for getting people to try out HPC plus quantum computing and see that it is a technology that works is important. And this is rather straightforward. And the co-located approach is a straightforward method for low latency algorithms. And algorithms that require low latency between HPC and quantum computing can emerge, even if we don't see it now, but we never know what comes up in the future. It might really be that the quantum computer really needs low latency to a very powerful classical computer, and not just a server like in the distributed approach. But the distributed approach is needed for setting up this framework for a low latency multi-QPU setup. And in a way, it also future-proofs for when a working quantum internet comes, because then it would be great to connect quantum computers that are physically distant just to build up one big whole where the quantum computing power would really increase exponentially. And in general, as with just QPU implementations, also the HPC plus QC implementations need to be diverse. All eggs in one basket is seldom a wise strategy. With this, I thank you for your attention.
Thank you, Mikael. Very interesting talk. And is there any question for Mikael? If not, I have a curiosity that is really a stupid thing that I maybe don't understand very correctly. But the difference between the distributed and the standalone technique, because with the co-located method, you have the QPU and the HPC computer in the same location, and you can connect them using wires or something like that. But in the distributed approach, how precisely do you connect the HPC computer with the quantum computer? Via internet? Did I understand correctly?
Yes. So the quantum computer would be connected to the classical server mainly, and that is the one that keeps the algorithm running for the most part. But then that classical server is then connected over fiber to the HPC, and here then the parts of a larger workflow that require HPC resources would then be done at the HPC center, and as well also, of course, user authentication and all of this that comes with just setting up things would be at the HPC center. But mainly for the really heavy HPC tasks would be taken care by the HPC system, but the middleman server there would take care of running the actual calculation.
Okay, so it's sort of standalone, but an evolved standalone situation, we can say. Okay, thank you. And just another curiosity, and I saw the difference in for the trapped ion and superconducting qubits in terms of time of applying qubits gates. And so it seems that the superconducting is very better in terms of time.
Yes, for a single circuit, but of course, what is important is how many gates you can execute in procession. So if you really, in the end, it doesn't matter if the quantum computing time takes 1 second or 10 seconds if you actually get much more done. So it is the ratio between gate time and decoherence that is the important one.
Thanks a lot. This is the answer that I was looking for. Thank you, Mikael.
Thanks.
Okay, so we are perfect on time, and we can introduce our next speaker. That is Andrés Gómez, administrator at CESGA. And thank you, Andrés, for being here. And I leave you the floor for your presentation.
Okay, good afternoon, and thank you for inviting me to present our activities in quantum computing. I hope that you can see my screen now with the presentation. If you can confirm.
Yes, we can.
Okay. Well, the problem of being one of the last speakers in this session is that almost everything that I want to say has been said before by the other speakers. So maybe you cannot learn nothing now, except maybe a few details or our vision about that. So let me first introduce my organization. CESGA is a supercomputing center that is located in Galicia, in the northwest of Spain, with a public foundation with the board of trustees composed of members of the regional government and members of the National Research Council of Spain. So we are a national facility that is part of a bigger national facility that is the Spanish Supercomputing Network that covers many places in Spain and is led by the National Center that is located in Barcelona. Our mission, and this is important to stress here, is to provide services and make research in the application of high performance computing and communications. But what is important is that we do everything in collaboration with other institutions or entities. Because we are a small foundation, we are only around 40, 50 people, depending on the number of projects that we are running. And we provide services to our users that are mainly universities and research centers around Spain, but also to small companies and big companies that want to make research in high-performance computing. And we have to adapt our infrastructure to the needs of our researchers, to the needs of our users that come from a lot of different productive sectors or research area, from bioinformatics to the high energy physics. So the number of needs and the type of requirements that we have is completely different. So we provide completely different resources from high performance computing, cloud environments, big data, or high performance communications. As many other centers in Europe, we have in the future, or in fact currently, 3 main challenges. One of them is the big data or the industrial data, or what you want, the research data, that we are creating a lot of data that we have to process, and we call high performance data analytics. Of course, the artificial intelligence or machine learning, deep learning area, applying this technology both to create numerical models or to process data. And finally, in the last years, we have the next challenges, the quantum technologies, both quantum computing and quantum communications. In the last 5 years, we started to work in quantum computing. Of course, the first step was understand and learn quantum computing because we didn't know nothing 5 years ago, and make small internal research projects in order to understand the algorithms, the techniques, the technologies that are behind this new concept of computing. The second one was to leverage a local community. This means to train local researchers, to train local people from universities, from companies, in order to transfer them the things that we learned about quantum computing and about the state of the technology. We deploy, as other centers as we have seen today, several emulators or simulators like QuizKit, ProjectQ, TensorFlow, Quantum, Kibo, others. Everything that can run in our supercomputer. We are lucky because we have a large memory in all the nodes, usually between 128 gigabytes to 4 terabytes of memory. So these servers are really well suited or well fitted to the execution of these simulations. We collaborate with the training students from the university with courses and internships at CESGA. We offer them to be here between 1 month and 2 months working with quantum computing in our supercomputing facilities. And of course, we are pushing companies and public institutions in our region and in Spain to work with these quantum computing technologies. Last year, we started to work in the European project NEAS QC. I will talk later about that. And finally, this year, we deploy as other centers one QLM of 30 qubits in order to start to have a dedicated platform for quantum computing. Currently, we have between 6 and 7 users from 3 different institutions, plus researchers from CESGA, of course. So we hope that we can create a community around this simulator. But at the beginning of the year, we started to define a strategic plan that we call in Spanish Polo of de Tecnologías Cuánticas, or this means something similar to the Quantum Valley. This means the idea is to have here a set of companies and institutions to work together in quantum technologies that can create a community so our region and in fact Spain can be a European reference in quantum technologies by 2013. This strategic plan has 4 pillars that are important. First of all is the academy, the universities. They have to create the new technicians, the new researchers that understand better than us the quantum technologies and can develop the future in the next 10, 20 years. The second one are the research and technological centers that from our point of view, they have to learn also this technology and create new products, new services based on these technologies. Of course, we cannot create anything if we don't have in board our companies, our local enterprise, the economy that leverage this technology and create products for the future based on the new wave of quantum technologies. And finally, the society. We cannot forget them because they are funding us. They will use this kind of services or this kind of products, and they will create a new researchers in the future because they have to transmit to the young people that quantum technologies are really important for the future. The mission of this strategic plan is to achieve a disruptive impulse in the quantum technologies in our region, especially in quantum computing and communications. The first step of this plan has been started at the end of this year. We had the initial seed funding of our regional government coming from European funding. And the idea is to deploy an initial infrastructure composed of one integrated system that join 3 devices or 3 pieces. One is, of course, a quantum computer, a QPU, or at least one QPU. The second one is a classical simulator or emulator of quantum computing. Currently, as I said, we have an Atos QLM of 30 qubits. The idea is to increase this capacity. We don't know if with QLM or another one. And finally, an HPC system exclusive for quantum computing, both for simulation but mainly to work in the new kind of algorithms, hybrid algorithms that we use the QPU and classical algorithms together. We learned today from many presentations that the hybrid computing is really the future. And in this, we believe in that. And I think that it's important to take into account that HPC distributed or collocated with QPU is really the future. And finally, we started with deploying a small infrastructure that is a quantum random generator that is there since November this year, and it's only for making experiments about this technology, understand this technology. Other research projects that we are involved and will start next year, one of them is Quantum Spain, that maybe you have some news about that. We are part of the consortium that is proposing this project, and that initially will start next year. The proposal, the aim of this project is to create the first quantum infrastructure around Europe based on the national supercomputer network with at least one computer that developed in Spain to be deployed in Barcelona, but also to create separate infrastructure with people in all the centers with the skills to support our users, our researchers. This is one of the most important things in one supercomputer center. And of course, to make research about algorithms, especially quantum machine learning algorithms, in the universities that will collaborate with us in this project. And we are involved in another second national initiative to develop quantum communications technologies that has 3 goals. The first one is to research and deploy quantum communication infrastructures. In this case, our idea is to deploy a testbed between Santiago and Vigo, that are 2 cities in our region that are close. So near enough to deploy a network, an experimental network, 100 kilometers, and to research and of course also leverage quantum algorithms, taking into account also these quantum communication networks for the future. Our participation in NEAX QC, that is a project that is focused on use cases from industrial users in order to understand better the needs and the capabilities of this new technology in different areas, is around 2 use cases where we participate with other institutions. In the first one is the quantum natural. Sorry, it's not this one. Should be another one. I'm very sorry. Let me correct because it's not this one. It's this one. Oh, sorry for this mistake. Now it's correct. We are collaborating with the University of Coruña and with one hospital in order to develop quantum rule-based systems that leverage the capacity of quantum computing in order to include in these models the uncertainty of the rules that we have to apply.
Sorry, Andres. Sorry, but I think that we lost the sharing,
Okay.
the screen sharing.
Now it's working.
No. Okay. Yes. Now, yes. Thank you. Sorry for the interruption.
Sorry, because I did a mistake in the presentation and.
Don't worry. It happens.
And the second one is that we are working in financial applications with one bank that is the HSBC, and or again with the University of Coruña, to understand better the quantum algorithm for financial applications. In the first 2 years, we are working in quantum accelerated Monte Carlo for financial applications, and we did an initial state-of-the-art report, and we are now developing the first 2 set of algorithms that we think that will improve the previous results in the area. But the third activity is one that is related with all the use cases, that is to develop a benchmark suite. A benchmark that using the cases, using the information that we can extract for the cases and from the needs of the cases, the idea is to develop a benchmark that is a suite, because we don't believe that we can define a single metric in order to understand, in order to analyze and to help the developers of the hardware to fit really the new developments in the needs of the users. This is a typical approach that we have in classical computing, and I think that we should do also in the quantum computer area. So the first idea is to try to understand better the future. It's very difficult, as we can see before, to forecast the evolution of the quantum computer, but clearly we think that in an initial step, the quantum computing will be something similar to an accelerator of the high-performance computing, maybe with one node sharing one or several QPUs. These nodes, a classical node connected with a typical low latency, or maybe a distributed network, as the previous speaker presented. Maybe in the future, because we have this year some initial results, having a quantum network or a quantum internet connecting the GPUs. If we have in mind this broad architecture for the future, and taking into account that our user really, the most important part is to solve the problem, not to develop a quantum algorithm. It's not, they have to solve a problem that they have in chemistry, or in physics, in logistics, in one area. Really, the approach is to have a hybrid classical quantum API, or a set of based on a set of kernels with a quantum part that is more important than the classical part of in the opposite way, classical more important than quantum, and with several stacks that usually maybe they are mixed, as for example Venkatesh presented. So taking into account this architecture is really very important for the future, and is really important for the design of this quantum benchmark suite that we want to develop in next. And let me explain a little bit what's happening with the hybrid classical quantum, and why we cannot forget the classical part. Let me explain, for example, one small example that we developed during the COVID lockdown in 2020, thinking about how to calculate eigenvalues of an Hermitian matrix. Our question is, what is the definiteness of the matrix? You know that this is an important problem for many classical algorithms, and that the idea is to know if the eigenvalues of these Hermitian matrix are all positive, all negatives, some positive and some negatives, or maybe one is zero and the rest are positive or negative. In this case, we can define the matrix in 5 categories: positive, positive, semi-definitive, negative and negative infinite and indefinite. Indefinite, this means that some of the eigenvalues are negative and another one are positive. Solving this problem classically is really very heavy. So one possible solution is to use quantum phase estimation that can be used to calculate the eigenvalues. So you know is that you have an eigenvalue of the matrix M. Then you have the E to the this eigenvalue plus the I is an eigenvalue of the exponential of this matrix with the same eigenvectors. That is important. So if you know the eigenvectors, you can calculate for each one the eigenvalue using the quantum phase estimation. One thing that usually we know or we learn in the quantum algorithms is that if we want to use the quantum phase estimation, we can or we need initially that this phase has to be between 0 and 1. So if we don't know exactly the value of this eigenvalue that can be higher or 1, we can divide this eigenvalue by a value, so we can transform the eigenvalues to the range that we need between 0 and 1. But the problem is what happens if the eigenvalue is 0, is so lower than 0. Well, this is the trick of this algorithm, and I will show later. But the problem is that usually we know the matrix, but we don't know the eigenvalues and the eigenvectors either. So it's very difficult to do that. If we know the eigenvectors, we can solve the problem in parallel, creating a superposition of all the eigenvectors and achieve or return all the eigenvalues at the same time in superposition. But the problem is, as I said, what's happening if the eigenvalues are negative? Well, in fact, you don't need to be this eigenvalue positive. You can make a quantum physics estimation that can work between minus 0.5 and 0.5 because you have a rotational sieve in the algorithm. So really that we need is the absolute value of these algorithms divided by the constant should be lower than 0.5. But again, which is A in this case. Well, in this case, we can use the classical algorithms. There is a classical theorem that says that you can at least put some limits in the eigenvalues, the low eigenvalue of a matrix and the high eigenvalue of a matrix, only calculating the trace of the square of the matrix. And in this case, if you are lucky, you can classify the matrix as negative, positive, or indefinite, depending of the values of these limits. As I said, for example, if the high limit of the maximum value is lower than 0, in this case, clearly all the eigenvalues are negative. The same happens when we have the limit, the low limit of the minimum value higher than 0. And the third case is that we have the maximum value of the low minor than 0 and higher than 0, the other one. In this case, is clearly indefinite. This needs around n square operations because in fact we have to only calculate the trace of the m square, but we have to calculate only the diagonal elements of this m square. If you are not lucky and you have to use the quantum phase estimation, in this case we can calculate our A, and in the previous algorithms using these values. If we calculate A as using the absolute value of Cmin and Cmass, in this case we are compressing all the eigenvalues to be between 0.5 and 0.5, and we separate. And we don't know exactly the eigenvectors, but we can use several random vectors that will be combinations of the eigenvectors. Because we don't know exactly if we are generating all the eigenvectors, the idea is to generate several random values and calculate only the expectation value of sigma z in the last qubit, in the most significant qubit, that is the sign of the eigenvalues altogether. So we did this second step algorithm, and the problem is that we have to decompose the matrix in a set of Pauli strings, because it's the only method that we know. Maybe there are other methods that are better than this, but this is the method that we know. But the problem is that this decomposition needs order 9 to the 3 operations to calculate all the values that we have to introduce in our algorithm. This means that initially it's higher than the number of operations that we have in the classical part of the algorithm, but is initially of the order of the operations that we have in the classical algorithms for calculating these definiteness of the matrix. So the quantum phase algorithm for this algorithm, and with the characteristic that we have used, have this other number of operations. The problem is that when n is large, mainly the classical part of the algorithm is more expensive than the quantum part of the algorithm. This means that when you analyze a quantum algorithm, you have to take into account both parts, the quantum and the classical part. You cannot say, okay, the quantum algorithm part is faster and the scalability is better than the classical part. You have to take into account what's happened with the classical pre-processing and post-processing that you have to do with the algorithm. Only to say that we did an experiment with 1,500 matrices. Around 60% of them can be classified with the classical part, and around 30% has been classified with the quantum phase estimation algorithm. This is another use of the HPC centers, because we had to run more than 3,000 simulations in order to take into account different number of qubits in the auxiliary part of the quantum phase estimation. And this is a very large number of simulation that needs a lot of memory. So HPC can help you, if you are a user, to analyze this kind of algorithm better. Finally, let me introduce the hybrid classical benchmarking that we are developing in ICHEC. We have defined four objectives for this algorithm. One of them is the first one is to help computer architects, programmers, and researchers to design the future quantum computers. The second one is to understand the evolution of the quantum computers. This is the typical objective of benchmarking. Compare the performance of the different platforms and consider other metrics that can be important to understand the quantum computing advantage. For example, if they consume less energy, they can produce better results, they are more scalable, the throughput of the algorithms. Of course, we don't believe that we need or we can achieve a single metrics to define an algorithm. Maybe, for example, this morning we had the IBM proposal for quantum volume and side flops. So we are defining a JSON schema in order to report the information that will include information about the hardware, about the execution, about the stack that has been used for the compilation, and of course, technical details about the QPUs, like the placements, the elapsed time, the total elapsed time, the classical elapsed time, the quantum elapsed time, and other metrics specific for the algorithm to understand the performance or the quality of the solution. So to end, because I am 1 minute late, quantum computers in our idea can help HPC to create 4 different quantum advantages. Usually here quantum supremacy. That is when we don't know a classical algorithm that can solve a quantum problem that can be solved using quantum capabilities. But we have other quantum advantages. For example, when we can solve problems that really we know how to solve classically, but faster, because our users usually want to solve the problem as fast as possible. The second one is that we can get better solutions that the classical algorithms can provide us. You know, in many optimization algorithms, they are heuristics, and maybe using quantum algorithms that are not exactly heuristic, but at least are probabilistic, we can produce better solutions, systematically produce better solutions. This is, I call, better quantum advantage. And finally, they can solve the same problems and produce the same solutions of the classical computer, but using less energy. That is important for any HPC center at the moment. If you compare, for example, the quantum supremacy problems and the energy that consume a classical computer to solve the same problem that a quantum computer can solve, we are taking that the classical computer needs between 1,000 and 10,000 more power to solve the same problem. In my opinion, and our opinion, always the algorithms will be hybrid in the future, with some parts accelerated with the quantum computers. So quantum computers, in our vision, will be quantum accelerators of an HPC infrastructure. And the speed up of the quantum algorithm should be analyzed, taking into account the classical part, the pre-processing and the post-processing, and understand if really we can have a quantum advantage and what is the bottleneck of the algorithm. And of course, the benchmarking has to take into account all the full quantum stack in order to understand the capabilities of the quantum computer. And that's all. Thank you to these people that has helped me in the developing of this software and this stack. And I open to questions.
Thank you, Andres. Thank you for your view on the hybrid quantum HPC computing. And let's see if there is any question for you. I'm not seeing any question, but it's a little bit late. I can understand. We are talking about, okay, there is a question. So have you already evaluated your benchmark suite to real QPUs?
Not yet. We are developing inside the project the first cases, and after evaluating then using emulators, we will move to evaluate the suite in quantum computers, maybe in 1 year or 1 year and a half.
Very good. Okay. Thank you, Andres. If there is no any other question, I think that is time to move on with our last speaker. That is Professor Christer Mikkelsen, leader of the Quantum Information Processing Group at ICHEC Supercomputing Center. Thank you, Christer, for being here. I leave you the floor for your presentation. Thanks a lot.
Thank you very much, Daniele, for the invitation. So I hope that you see my slides.
Yes.
Yes. Okay, good. So I will say a few words about UNIQ, which is the HPC quantum computer simulator infrastructure for practical quantum computing at the ICHEC Supercomputing Center. Now, as we all know, we have various communities in high-performance computing, and they want to solve all kinds of hard computational problems, and they are usually dealing with complex systems. Now, the hope is that quantum computers can help in solving some of these challenging problems, And actually, it's the belief that they can help to perform quantum simulations. And then one can think of applications in quantum chemistry. They are also hope to be good in solving optimization problems. And optimization problems we have everywhere. One can optimize drug design, one can optimize traffic flows, and so on. And as optimization is the starting point for machine learning, one also has quantum machine learning as a potential application of quantum computing. Now we have a huge variety of quantum computing devices. Not all of them have the same technological maturity. They all differ in size, and we have different platforms. We have superconducting qubits, we have ion-trapped quantum computers, we have molecular spin qubits, we have semiconductor qubits, neutral atoms, and so on. So a few years ago, Thomas Lippert and I decided maybe we have to come up with a scheme that describes the quantum technology readiness level of each of these platforms, and this can then be used to describe their technological maturity for quantum computing. Now, this scheme is inspired by the scheme of NASA, and it also has 9 levels. Now, we could say if we have these more experimental qubit platforms, then usually these qubits are not so perfect, and we have only small systems. And then we say, okay, they have a level of 3, maybe 2 or 3. If we go to the commercial ones, then we can say they have level 4 or 5, because then usually the quality of the qubits is better and we have more of them, but still we do not have error correction, because in order to have error correction in these gate-based systems, we need a huge amount of qubits. So then, to put it on the same scheme, we also put here the annealer. We know there is one annealer commercially available. This was discussed this morning by Andy Mason of D-Wave. Nowadays, they have a system with more than 5,000 qubits, and we gave it level 8 because we can say it's scalable. Almost every 2 years, the size of this quantum processing unit doubles. And not only that, also the connectivity of the qubits is increased. Because we have here such a big amount of qubits available, this machine is also useful for prototype applications. Actually, more than 250 potential applications are known for the D-Wave quantum annealer. But it remains a huge challenge and opportunity for practical quantum computing, because we have to develop these prototype applications and use cases for these different types of quantum computers. We have the gate-based quantum computers, we have the quantum simulators, and we also have the quantum annealers. Now, in our vision at the Jülich Supercomputing Center, we have this vision for a long time. We think quantum computers have to be linked with high-performance computers to solve problems in an optimal way. And here we have on this side our high-performance computers, and we know that we can use them very well for emulating quantum computing, simulating, and annealing devices. Then here on the other hand, we have our quantum computer simulators and annealers, and these emulations here can help us to understand how these quantum computing devices operate. If we more or less understand how they operate, We can also find out where they make their failures, so then we can hopefully also help in improving the design of these devices. And what it's definitely also useful for is benchmarking. We can emulate not only the hardware, but we can also emulate carrying out certain algorithms on quantum hardware that is emulated on these HPC systems. But the final goal should be that one comes to this hybrid high-performance computing and then quantum computing and simulators for this applications. So this connection is for practical quantum computing required. So, as I mentioned, on this one hand, we have the HPC systems. On the other hand, we have this large variety of different quantum computing platforms for quantum computing and simulating and annealing. So the question is, how can we connect both? Because we have a lot of experience in high-performance computing, we can use the HPC ecosystem and its three ingredients, namely the users and their applications, the software and the hardware. Now, if we look at the intersection between user and applications and the software, what we have to do is to come up with new algorithms and software. The intersection between software and hardware, we need to develop a QCS full software stack. We have to go from the firmware up to the user interfaces. And then on the intersection between the hardware and the users and their applications, what we have to do is develop use cases in a co-design approach, just as we do it for our HPC systems. Now, let me say a few extra words about these hybrid quantum classical computing systems for realizing the full potential of quantum computing. First, we have these hybrid quantum classical algorithms. They already have been mentioned today. So we have the variational quantum eigensolver, which can be used for solving problems in quantum chemistry. We have the quantum approximate optimization algorithm, or QAOA, which is used for solving all kinds of optimization problems. And then we also have, for example, a quantum support vector machine, which can be used for classification and clustering in machine learning. Now, having these algorithms is nice, but what one really has to do is a proper benchmarking. And for this proper benchmarking, one can use emulators on the HPC systems, but one definitely also has to implement them on real devices and carry out a cross-platform benchmarking. Then I come to the hybrid quantum classical hardware, and I would say we have two big groups here. One can make this hybrid connection by using a cloud access, or we can go to a more deep integration. And what one has to take into account here are latencies and execution times. Let me come to an example, the example of the quantum approximate optimization algorithm as a hybrid algorithm. It's also a variational algorithm. And in this case, I will use the Jülich Universal Quantum Computer Simulator, JUX, to first emulate this algorithm on an HPC system, and then later on do a benchmarking with quantum annealing on a DBEF quantum annealer. First, QAOA. So this relies on an iterative process. So one iteratively applies a series of parameterized unitary transformations to a quantum register. Then you measure the resulting state of the quantum system, and then one evaluates the energy expectation value. Now, for the optimization of the parameters of the unitary transformations, one uses a classical optimization algorithm. So you see, one has a part which one can run in principle on a quantum computer, and one has a part of the algorithm which runs on a classical system. Now, when we do the emulation, we run this part of the algorithm on the GPUs of the Jewels booster. So this means that the GPUs of the Jewels booster play the role of the quantum processing units. And this classical part we have run on the CPUs of the Jewels booster. Now, it's always good to look at a simplified real practical problem, and in this case we looked at a simplified tail assignment problem. This is a problem from the airline industry. So what one has to do is one has to assign aircraft to flights, and then one has to minimize the overall cost for aircraft and the flight crew while one is respecting operational constraints. So this is a quantum, or this can be translated into a quantum optimization problem. And if we consider a small and reasonable problem, then we can consider a problem with 40 qubits. Now, for these 40 qubits, we can carry out a simulation on Jewels using the emulator for a perfect gate-based quantum computer. And then you have as an outcome these dashed lines. And then one sees that if one goes to 40 qubits, that one has a success rate of approximately 1 in 1,000 for the perfect gate-based quantum computer. Then we implemented also a quantum annealing algorithm. We carried out on the D-Wave quantum annealer for this 40 qubits, which is actually a rather small system. And then one sees that if one carries this out on the advantage system, that one has a success rate of about 70%. Now, on the D-Wave advantage, we could also simulate larger problems. We also did this, but for the cross-platform benchmarking, I mentioned here only the 40 qubit results. So this particular example shows that in this particular case, we used for the gate-based quantum computer, the CPU for the optimization in the Quaioa algorithm and the GPUs for calculating the expectation value of the energy for which we use a quantum circuit. Now, what we can also do in the modular supercomputing architecture of the GSC is to use the cluster module of the modular supercomputer, which consists mainly of CPUs, to do the optimization, and then use a QPU of the quantum module to run this quantum circuit. So, and then let us have a closer look into this quantum module. So here the plan is to have a seamless quantum computing HPC integration with the final goal to come to these quantum classical hybrid computing models, so that we can build here in this modular supercomputer architecture different workflows. So this quantum module, their unique is the most important element, so the unified infrastructure for quantum computing. I already mentioned it's a user facility for science and industry in Europe. It installs, operates, and provides access to different types of quantum computers. And for that, it provides the users with a unified portal for the access to quantum computing emulators. That is JUX, the simulator or the emulator I have been talking about, and also an Atos quantum learning machine. Then we have, or we provide access to various quantum computing devices that have different levels of technological maturity. We have experimental devices like the superconducting quantum computer from the Open Supercube project of the Quantum Flagship. We will provide access to the digital analog quantum computer of the DAC National project. We have a D-Wave quantum annealer installed. We are looking for commercial access to other gate-based quantum computers. And on the 1st of December, we started a Euro-HPC joint undertaking project called HPC-QS, in which the aim is to couple a quantum simulator to an HPC system. This the HPC system at CA in Paris and Jules in Jülich. Then apart from providing access to this hardware, together with our users, we develop algorithms and prototype applications. From our long-term experience in HPC, we know that it's very important to provide our users also with services, training and user support. So in UNIQ, we will give this both for HPC and quantum. And then, of course, of UNIQ, the final goal is to have this modular quantum HPC hybrid computing. And that's also why we have here this connection to the modular supercomputer. Now, in Europe, one can say one has come from vision to reality. If you look at this history here, we had quantum computing, more fundamental research in the hardware in Quantera and the Quantum Flagship. I'm not talking here about quantum communication and sensing. So, but the goal here in Europe was to come to quantum computing and simulation infrastructure called EuroQCS. And we can say that with Euro-HPC joint undertaking funding for 2021, the first hybrid HPC quantum computing infrastructure in Europe become close to this goal here. So as I mentioned, we have started on the 1st of December this HPC-QS project. Actually, I'm having the honor of coordinating this project. Here you see all the partners, and actually, as I mentioned, we started on the 1st of December, and this project will be finished on November 30 in 2025. Now, with this slide, I would like to conclude by telling you once more that in our vision, the key to come to a successful development of quantum computing applications and therefore to practical quantum computing, one has to come to a hybrid usage of high performance and quantum computers. So these big machines have to be coupled to these, at the moment, machines with different technological maturity, but we have to start with this connection soon, and therefore we in Jülich already started with this. So thank you very much.
Thank you for your talk, Krista. So let me see if there is any question. I think that no, but the reason is the same before, because here is a little bit late. But I have a curiosity for you. It's a really stupid curiosity. Do you have also quantum annealing emulator installed on your machines, or only the gate-based a state vector emulator?
Which the one that is free or that will be accessible first for the users is the gate-based emulator. We ourselves have all kinds of simulation tools to simulate open quantum systems, and there we can also simulate a quantum annealer. There the issue is one can only simulate a small one, smaller than the gate-based quantum computer.
Smaller than gate-based, so you can simulate a quantum annealer smaller than a gate-based quantum computer. Did I understand correctly?
Yes.
Okay.
Because one then has to simulate the full dynamics of the system.
Okay, understood. Thank you, because I'm also interested in this topic. And okay, is there any other question for Crystal? Seems not. If not, I think that maybe we can thank again Crystal for her beautiful talk, and thank you. And I think that we can close the meeting here 5 minutes before for 15 and 30, and we will. Okay, we have a question, last minute question. It says, is the collaboration open to other partners?
Yes, the collaboration is open to other partners, and we will have also peer-reviewed access to the machines.
Very good. Okay. So.
Okay. I would also like to thank all the speakers of today. Unfortunately, my camera stopped to work
again.
At the beginning, again, for the concluding remarks. But okay, doesn't matter. That's Teams world. Okay. So thank you so much. We're going to meet again tomorrow at 10.
Exactly.
So see you tomorrow. It was a pleasure having this day with you all today. Bye-bye.
Also for me. Bye-bye. Have a beautiful evening.
Thank you. Bye.
Thank you so much for being here.
Thank you.
Bye-bye.
See you tomorrow.